7.2 Non-locality in the conventional interpretations. Non-locality is usually discussed in terms of the EPR experiment. HOW. Ever, EPR emphasized not on ly the question of non-locality, but also that an unlocality 135 of whether the quantum mechanics was what they called complete. By this they did not mean that 1T should cover everything that could ever be known, but rather that it had all the concepts necessary for its coherence as the basis of an ontology. The result of their analysis was that it was not complete in this sense. We shall give here a brief resume of their analysis, as it would apply to a spin experiment involving a molecule of total spin 0, EACH of whose atoms HAVE a spin of 1/2 3. Their discussion was based essentially on what they meant by an element of reality. In general terms, this signified some feature of the world that is real, independently of its being observed or otherwise known by us. In particular, they proposed a sufficient criterion for such an element of reality. If, without disturbing the system in any way, one can predict the values of a given quantity with certainty, i.e., with probability equal to unity, then that quantity corresponds to an element of reality. Clearly this fits in with our general intuitive notions of WHAT is to be meant by an independently existent element of reality. We now consider an experiment in which the molecule is disintegrated, so that the atoms are separated by a large distance. Suppose that the spin of atom A is now measured in the z direction and that a given result is obtained. We can then predict that the spin of atom B is opposite. Of course, atom A will be disturbed when its spin is measured, so that we cannot conclude THAT its spin was defined beforehand as an independently existent element of reality. But our predictions of the spin of atom B can now be made without disturbing atom B in any way at LL. Because measurements of atom A do not disturb atom B in any way, it follows from the EPR criticism that THEZ component of the spin of atom B must have been an element of reality even before atom A was measured, and that indeed it was always an element of reality. But now we could have measured any other component of the spin of atom A instead, and by considering such a measurement it follows that every component of the spin of atom BH has always been an element of reality. From this EPR concluded THAT the quantum theory is conceptually incomplete. For one of its basic principles is that when two observables do not commute, they cannot be defined together. Therefore at most only one of these could be an element of reality at a given time. But if two or more are elements of reality, then this means that the mathematical form of the theory cannot reflect this in any way at all. To take this into account, we would need new concepts not contained in T.E present theory. So EPR would argue that while the results of the quantum theory are statistically coercive, this theory does not give an adequate account of the actual reality of the individual system. Although it is postulated that there is no interaction between the party 136 the undivided universe through forces of known kinds, one could evidently 888 UME that THR was a new and as yet unknown kind of force that connected the two particles. Then when particle A was disturbed in its measurement, this disturbance would communicate itself to particle B in such a way as to bring about a result opposite to that of A for its spin. If such an interaction was operating, then the criterion of EPR for an element of reality would clearly be irrelevant, since by hypothesis a disturbance of atom A can now bring about a disturbance of atom B. However, EPR did not seem to regard this sort of interaction as worthy of serious consideration. To see why, we note that there are two possibilities. 1. The force is transmitted at some finite speed less than or equal to that of light. In this case, the statistical predictions of the current quantum theory would, of course, have to fail for measurements of A and B that are space-like separated. But EPR assumed, as we have pointed out, these statistical predictions are correct, and thus they did not even envisage such a failure of the current quantum theory. 2. The interaction is transmitted instantaneously. In this case, the interaction would have to be non-local, i.e., to operate directly and immediately between the two particles with a strong force even at very large distances. Evidently, this would violate the special theory of relativity. However, Einstein felt there was an even more fundamental objection. Because independently of relativistic considerations, he thought that all action had to be local, while he regarded non-local interactions as spooky, and thus in some way unacceptable for. Nevertheless, he did believe that a suitable low-scale explanation of this sort of experiment could eventually be obtained, perhaps on the basis of a new theory containing additional concepts that would represent new elements of reality. It is clear then that EPR did not make an explicit discussion of the question of non-locality and focused instead on that of completeness. Bohr 5, appreciating the penetrating criticism of EPR, took great care in formulating a response. Essentially, this consisted in pointing out that his own approach of complementarity still applied, even when the particles were separated by large distances a, ld, when the results of experiments are separated by large intervals of time e. The main point was that the attempt to analyze the process in detail, and in doing so to attribute independent reality to the properties of the particle B, for example, was not permissible in the quantum mechanical context. This is because the form of the experimental conditions and the content, meaning, of the experimental results are, in Bohr's view, a whole that is not further analyzable. Therefore there is no legitimate way to think about the properties of particle B apart from the experimental context in which THEY are measured. The context needed to think about the Z component of the spin of atom B is therefore not compatible with that needed to think about its X component. This signifies that even though we can predict the properties of atom B from those of atom A without disturbing atom B, there is no experimental situation with regard to atom B in which both of the above predictions could have meaning together. The crucial point here is that Bohr is using a different notion of reality from that of EPR. For Bohr, a concept represents reality only insofar as it is in unambiguous correspondence with the whole set of possible phenomena. And these phenomena are necessarily such that they have to be described in terms of the concepts of classical physics. For Einstein, however, concepts are a free creation of the human mind, and their correspondence with reality is at first assumed and then tested by the phenomena they predict. Therefore there is no problem in assuming the simultaneous reality of all the properties of particle B, even these cannot be simultaneously observed. Bohr regards this as a totally inadmissible way of using concepts in the context of quantum theory, in which these have to be ambiguous and mutually exclusive, but nevertheless complementary. The above constitutes the essence of Bohr's answer to the emphasis of EPR on the question of completeness of the quantum theory. However, from this it also follows that it has no meaning, in his view, to talk about non-locality. Indeed, according to Bohr, nothing can be said about the THIRD behavior of individual systems at the quantum level of accuracy. There is only the total unanalyzable experimental phenomenon and no way to discuss in detail what this could mean ontologically. Therefore it also follows that there is no meaning to talking about locality either. All that we can do is to use the quantum algorithm to calculate THE probabilities of the various experimental results. Nevertheless, it still seems that some kind of non-locality is, at least, implicit in Bohr's approach, because the phenomenon itself, which is spread out over space and time, is considered to be an unanalyzable whole. Rika LL, however, that THE most common approach to quantum theory is along the line-ness of von Neumann 6 rather than that of Bohr. To show how non-locality is implied in this approach, let us consider the wave function for a system of two separated particles with total spin 0. This is 1. IIT equals Vj. F, Ra, G, Rb, 1/I plus, A, L/I, B, 1/J underscore, A, L/I plus, B, 7 1. Where F, Ra, is THE wave function of particle A and G, Rb, is the wave function of particle B, and the expression in the square bracket represents the 1/3 J undivided univary spin part of the combined system. F, Ra, may, for example, represent a situation where particle A is a long way to the left of the original center of mass of the molecule E, while G, Rb, represents a situation in which particle B is equally far to the right. We then assume that the spin of particle A is measured by means of an apparatus whose relevant coordinate is represented by 11. The theory of measurement that we have given in Chapter 2 can readily be extended to the case of spin. Before the interaction with the measuring apparatus, the total wave function is then 1. Il equals /2 Ra, G, Ra, cent 0, 11, 1 plus, A, L B, 1 A, L plus, B, 7.2. Where cent 0, 11, is a wave PA representing the initial state of the measuring apparatus. We then introduce an interaction H Hamiltonian which depends upon the spin of particle A in such a way as to separate the wave functions of positive spin from those of negative spin, as shown in the discussion around equation 2-4, and using a similar notation we obtain for the final wave function ILJ 1/2/ Ra, G, Ra, cent 0, 11, T, TL plus, A, L B, cent 0, 11 plus dot T, L A, L plus, B, 7.3. As we have seen in this discussion, cent 0, 11, T, and cent 0, 11 plus dot T, will not overlap after the interaction is over. When an observation is mod DE, the apparatus will be foo ndi in one or the other of these states as if the wave function had collapsed to the state in question. We will be left essentially with either or 1. Iloi equals /2/ Ra, G, Ra, cent 0, 11, T, L plus, A, L B, 7.4. 1. I/LJ equals /2F, Ra, G, Ra, cent 0, 11 plus dot T, 1 underscore, A, 1 plus, B. 7.5. After particle A is measured, particle B is in a well-defined spin state. Even though there is no measuring apparatus that H has interacted with this particle. A similar result would HAVE been obtained if we HAD measured the Component in any direction designated by 11. With regard to atom A, 1 can say that its interaction with THE measuring apparatus was responsible for the collapse onto the eigenfunction of its spin in the direction TL. But if there is no connection between A and B, how can the latter know WTHAT? It too must collapse into an opposite eigenview NCT ion of the spin in the same non-Lika/ITY 139 direction, even though this direction was chosen arbitrarily when someone decided to measure A when the atoms were far apart. Particularly, if this choice is made too rapid Ly to allow a signal to pass from A to B, it seems very reasonable to suggest that A and B are directly connected, though in a way that is perhaps not yet known. And so one sees the need for some form of quantum non-locality when we analyze the EPR experiment in terms of the von Neumann approach. If THR is a non-local connection between distant particles, what can we say about the possibility of using it to send signals from one of these particles to the other? Within the essentially statistical framework of the current quantum theory, this would require that there be something that we could do, for example, to particle A, which would change the statistical result of measurements of the spin of particle B in one or more directions. We shall show that this is, in fact, impossible, from which it follows that EPR correlations cannot make possible the transmission of signals of any kind, including, for example, those that are faster than light. To show this we use a simplified form of a proof by Eberhard 7. Let us suppose an external system with coordinate y is allowed to interact with the spin of particle A. The initial wave function for THE combined system will be E 7.6, where A represents the standard spin indices and TT dot plus A represents the wave function for particle A corresponding to a positive spin in any chosen direction, while 1 colon A represents a negative spin in that direction. The most general possible result of this interaction will be represented by a unitary transformation on the subsystem consisting of y and A, because, by hypothesis, we are assuming our interaction does not directly disturb B. If it did, then this would not constitute sending a signal from A to B, but would just be a direct disturbance of B by its interaction with Y. To represent this unitary transformation, we assume that for O, Y is the first term in an orthonormal set for n, Y. The most general unitary transformation can be expressed as the matrix U0, where A and O represent, respectively, the initial and final spin indices. In this notation the initial wave function, 7,6, can be written as, under the unitary transformation, THIS goes over into 140 W undivided uni verse. Let us now consider spin averages for any spin U8 for particle B. In the undisturbed state this average can be written as 7.9. This will be constituted of 4 terms, of which 2 may be called diagonal, and the other 2 called off diagonal. A typical diagonal term will be, since 0 colonnes and wf A are normalist, THIS reduces to 710. A typical OFF diagonal term WILLB. But because P and 1 slash, colon dot underscore 1 are orthogonal, this term is 0. We then get the familiar result 7, 1, 1, which is 0 because the second term cancels the first. It is well known that a unitary transformation will not change the scalar products. It follows then that because this transformation acts only on particle A, the diagonal terms remain the same as before, and that THE off Diagonal terms remain 0. Therefore the average of 17b will be the same. After transformation as before, and we conclude then that nothing that we do to particle A will change the average spin properties of particle B. 7. 3 Bell-LS inequalities. We have seen that non-locality is conta in ed in all the I enter ratio ns of the quantum theory that we have discussed so far. As we have already pointed out in chapter 5, our own ontological interpretation also contains non-locality as a basic feature. In considering the non-local implications of THIS ontological interpretation, Bell 8 was led to ask wh either non-locality was necessary for all possible ontological explanations of quantum mechanics. He did this by No NL Ockley 14.1. Considering the EPR experiment in more detail, representing the states of elements of reality by a set of hidden variables A. These, together with the combined wave function of the observed system and the observing apparatus, will determine the results of each individual measurement process. In the case of the EPR experiment T, we suppose the apparatus that measures the spin of particle A is characterized by an orientation parameter A, while the apparatus that measures the spin of particle B is characterized by the orientation parameter B, so that they need not, in general, be in opposite directions. As shown in chapter 6, we may, in general, expect that each individual result of the spin of particle A will depend on hidden variables associated with the corresponding piece of measuring apparatus, while results for measuring particle B will depend on the hidden variables B of the second piece of apparatus. In addition, there will be some further hidden variables. There may be a set of such variables A and B belonging respectively to particle A and B by themselves, and a further set A which may be associated with the observed system as a whole, rather than just one of The particles. We Thn introduce a symbol to represent the result of measurement of the spin of particle A, with A equals +1 for a positive spin, and A equals 1 for negative spin, while B is the corresponding symbol for the result of a measurement on particle B. It is clear from what has been said above that in general, there may be a set of such variables. 712. A and B also depend on the wave function of the combined system, but we suppress this for the sake of conciseness. At this point we have to ask how to take into account the context dependence of the results of quantum mechanical observation that are discussed in Chapter 6, Section 6.5. It is important not to confuse the question of context dependence with that of non-locality, even though it is difficult to separate the two. To put the question of non-locality for this experiment, we may assume that only a local context is allowed. In other words, the result of measuring particle A depends only on the context of particle A, i.e. the apparatus that measures its spin, and not on the context of particle B. The interaction between A and B will be a local IFTHE result A depends only on A and not on B and AB, and vice versa for B. Therefore, and 713. 142 the undivided universe. If the above is satisfied, i.e. if each result depends only on a local context, then we may say that we have local hidden variables. In this connection, however, let us recall THAT, as indicated in section 7. 2. It would be quite possible to conceive of purely local explanations of the EPR experiment by means of forces that are transmitted at the speed of light or less, provided that the predictions of the quantum theory failed. When measurements were made with space-like separation and held only when THR was sufficient time for signals to be transmitted back and forth between A and B. One might explain such a behavior by assuming an ambient field that connected both particles. By passing back and forth between A and B a number of times, this field would guarantee that B would know W which properties of A were being measured and would behave accordingly. This sort of explanation has always been open to consideration. And in fact we have discussed its possibility in some detail in Bohm and Hilley 9. But Bell's work is based on the assumption that there is no time for a signal that would allow the results of a measurement of one of the particles to depend on the context supplied by the other measuring apparatus. Equation 713 THN shows that local hidden variables will inevitably satisfy this requirement. To proceed WITH derivation of Bell's inequality WE must now consider the distribution of hidden variables. Locality implies that the distributions over A and B are independent. It further implies that when we rotate the apparatus from one orientation to the other, its hidden variables will rotate with it, and that such a rotation will not significantly alter the hidden variables \A, \B, \, of THE two-particle system. This means that THE hidden variables, 0, can be taken as having the same range independently of the orientation of the apparatus. We may therefore replace the symbol A by A, which denotes the fact that the same set of parameters can be used regardless of the orientation of the apparatus. Similarly, we replace B by A. We therefore define three distributions: PA, A, PB, B, and P, \A, \B, The foo and CTI on P of \A, \B and is able to express the statistical correlations that may be present between the two systems, even though THE measurement of one of the systems does not affect the other in any way. We can then define the averages of A and B over the hidden var IA bless A and B respectively. This gives 714. Non-locality 143. Since IT follows that IB, B, I equals : 1. 7.15. We then go on to consider the CORRL at ions of experimental results for A and B with various orientations A and B. These are what can be readily measured, and they will provide the test for locality. A typical correlation is. To obtain the Bell inequality, we begin by considering P, A, B, P, A, C, equals J, P, A, B, X, A, B, 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 A, B, C, B, JD, AD, BD, equals JP, A, B, A, B, 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 1 plus or minus A, D, A, B, C, B, J, A, B, C, B, L plus or minus A, D, A, B, 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 D, AD, BD. Taking THE absolute value of both sides and noting that we obtain IA, B, 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 IA, B, C, B, I1, IP, AB, P, AC, I.S2 plus or minus, P, DC, plus P, DB. From TH's IT follows that IP, AB, P, AC, I plus IP, D, plus P, DB, I.S2. 717. The above is Bell's inequality, which must be satisfied for a local hidden variable theory to apply to our system of two particles with spin. These inequalities make possible a test for locality on the basis of measurements of four sets of correlatio ns. T his SYMMETRICFORMOF. The Bell inequality was phi rs T proposed by Clauser et al. 10. A. Figure RE7. 1. Angular relation between the axes of various spin measurements. The predictions of the quantum theory are that P, AB, equals, AB. 718. There is a range of angles for which, 718, does not satisfy the inequality. 717. For example, consider the set of axes shown in figure 7. 1. Here, A equals B, A/3 equals C, D n/equals D, C. Putting these in, 717, we find IP, A, P, A/3, I plus IP, plus P, /3 plus I2. Now if A equals 60, /3 equals 60 and /equals 0. Then the inequality on THE left hand side is 5/2 which is certainly not less TH and 2, so THE inequality is violated. Bell's inequality has been tested in a large number of experiments and, generally speaking, the inequality has been found to be violate D. These experiments do not use particles with spin but instead use correlations of polarized photons produced in atomic cascades. It can be easily shown that TH's case is mathematically equivalent to that of SPIN. The first experiment of TH's kind was performed by Friedman and Clauser 1-1. The latest, and perhaps most THORO set of experiments, has been performed by Aspect et al. 1-2. In particular, the latter were able to test whether the correlations were maintained even when the events of detection of the two photons were outside each other's light cones. ASPICT et al. Found the inequality was still violated. This implies that, independent TLY of QUA entum mechanics, we have an experiment TAL proof that if there are hidden variables, they must be non-local. ASPICT's experiments have been criticized by some physicists. 1-3. The main criticism is TH at Bell's inequalities could have been absolutely proved to have been violated only if the photon detector had an efficiency CLOs to UNIT. With the actual RATHER low efficiencies of these detectors, their non-locality 145 seems to be room for assumptio ns concerning the hidden variables of the apparatus, which could still preserve locality in spite of the experimental results. However, these assumptions seem rather arbitrary and artificial, and, in FACT, they give the impression of being contrived just to save the appearances. The least we see and say is that there is a strong prima facie case for non-locality. As we have seen earlier, the whole notion of taking Bell's inequality as a test for locality is physically relevant only in a context in which we are dealing with measurements on A and B that are outside each other's LIGHT cone S. Aspect's third experiment 1-2 is the one that provides strong evidence that this inequality is still violated in this context. For included in this experiment is a switching device that could randomly change the orientations of the detectors in a time too short for a light-like signal to P as SB between them. Of course, one could suppose along the lines we have discussed earlier, that there was an ambient field that could pass signals not only between the particles A and B, but also between these and the random switching device. The particles A and B could then know what the random switching device was going to do, and they could adjust their behavior accordingly. But this does not seem to be very plausible, especially since the switching device co-ULD, in turn, depend on other random devices going on in an indefinitely proliferating cha-in. This could even include the human being who chose to set THSA devices up in a certain way. If, for example, measurements were made when A and B were separated by millions of miles, giving the experimenters the chance to change the apparatus in an arbitrary way, we would then assume that the ambient field would have to inform the particles A and B of these changes so that they could add a PT accordingly to produce the proper correlated behavior. Of course, it is possible that somewhere along this chain quantum mechanics would fail, but then it is the whole purpose of Bell's inequality to show that any local hidden variable theory which allows for any kind of independent disturbance of a system from outside itself must imply the failure of quantum mechanics. In our treatment we have only discussed purely deterministic local hidden variabilities. There has been a great deal of work done on obtaining inequalities of the Bell type for stochastic hidden variable theories. 1-4. Although the details of this work are more complex, the results are essentially the same. We will discuss a theory of stochastic hidden variables in Chapter 9. 146 The undivided undivided. 1.4 Extension of Bell's theorem to three particles. Recently there has been developed a new proof of the impossibility of local hidden variables based on the consideration of three or more particles. In this proof it is directly shown that even the states of perfect correlation lead to a contradiction with quantum mechanics, so that no statistical criteria are required and no inequalities are involved. We shall use here the very concise and simplified version of this proof, presented by Mermin 1-6, who considers a system of three spatially separated particles which we denote by 1, 2, and 3 respectively. The argument of Bell was based on choosing a particular state, the singlet state, of a combined system of two particles, and showing that under the assumption of locality the correlations of these particles are not compatible with those predicted by the quantum theory. However, to obtain this result, Bell had to work out certain features of the statistical correlations of the two particles. There is no way from the correlations observed in individual instances to show a contradiction with locality. But when there are three or more particles, one finds that even the perfect correlations cannot be assigned consistent values under the assumption of locality. And so the impossibility of local hidden variables is demonstrated without the need for any further statistical measurement. Mermin begins by considering the three mutually commuting operators 0-1R02YOJV, 0-1Y02ROJ and U1Y02YOJR. He supposes that the wave function CT is an eigenfunction of all three of these with eigenvalue 1 CA, and then immediately obtain a fourth operator, U1R02ROJR, which is the negative of the product of all THE above and therefore commutes with them. It clearly has the eigenvalue 1 for the state CL. We can then write M1R M2Y M3Y equals 1. M1Y M2Y M3R equals 1. M1Y M2R M3Y equals 1. 1N1R Tn2R M3R equals 1. Where the ms are the eigenvalues of the corresponding individual spin-up errators. From these equations, we can obtain a set of perfect correlations. For example, if we measure U1R and U2Y, then the value of OJ is completely determined, and so on. If we multiply the four equations together, we obtain 1 on the right hand side, but plus 1 on the left hand side. Therefore there is a contradiction with our initial assumption that these values for any one particle are independent independent of what is measured for the other particles. From this we see that the assumption of locality is directly violated. A weaker implicit assumption, namely, that of simple locality, is THATTHE. Spin variables are at most locally context dependent, INTHE sense THATTHE. Non-locality 147. Apparatus that measures a particular spin variable is indivisibly linked. That spin. H.O. Weaver, what follows from the above proof is that each particle is also indivisibly linked to a context determined by the pieces of apparatus that measures the other particles. EACH values such as M1R appears twice in the above equations, combined with different values for the other particles. In this case M2 11 cubic meters. 11. And M2R M3R. Therefore we are in essentially the same situation as that treated by Merman for THE case of two particles as discussed in Chapter 6, Section 6. 4. Although the three operators U1R, U211, and OJV all commute as do U1R, 02R, and OJR, nevertheless we cannot in general obtain THE same value of M1R when ITIS measured along with U1.R and 0 feet 3 inches. 11. As when IT is measured along WITHU2X and OJR. As we have already pointed out, the reason is that the operators other than U1R in one set do not commute with those in the other. In the ontological interpretation, this kind of context dependence would be evident because the measurements of non-commuting operators require different and mutually incompatible pieces of apparatus. Therefore there is no reason why U1R should have the same value no matter what other operators could be measured simultaneously by the chosen apparatus. Therefore, there is no way in which THE contradiction obtained in the proof could arise. 7.5 The EPR experiment according to the causal interpretation. It will be instructive to show in detail how an EPR type experiment is to be understood in our approach for the case of two particles. No, essentially new principles are involved in the case of three or more particles. Strictly speaking, to compare our results with the discussion that has been given here, we need to use the causal interpretation for SPIN. Although we do develop this in chapters 10 and 1-2, we shall, for the sake of simplicity, consider here the C as E of a molecule of total angular momentum h. This will give an EPR type correlation very similar to that obtained with spin. Although the Bell inequality Ca not be directly applied to this case, an extension of Bell's idea to systems of higher angular momentum h as actu alibin Ca read out by Merman, 1.7 and yields similar but more complex results. Let us consider atom A whose center of mass is represented by Ra and whose NAL electron coulombed INATE is represented by Ra, while corresponding qualities for atom B are Rb and Rb. After the molecule has been disintegrated, the wave function of the WH system can be built out of wave function S of the separated atoms. We assume the center of mass of these atoms have wave functions given by Tpa, Ra, and Tpb, Rb. We choose internal states with angular momentum h, which can be represented by 148 The undivided uni verse 9.a, Ra, Tp, Ra, and dga, Ra, T/J, Ra, where T/J1, Ra, Xa, plus E.A, V12 Ra, T/Jo, Ra, Z.A, equals F.A, 719. Tp1, Ra, X.A, E.A, HRA. The above evidently represent the three possible eigenvalues of the angular momentum operator along the z-axis. The combined wave function is then it equals n cent dot a, ra, cent n, rn, 9 dot a, ra, 9n, rn, x, 1, x, v3t slash j, 1, rah11, rn, 1 slash jo, ra, l slash jo, rn, plus 1 1, ra, plus 1 1, rn, a, 1 ra rn, n cent a, ra, cent n, rn, 9a, ra, gn, rn, 2, b, v3r dot a rn, 7.20, where n is a Normalisa T ion constant. The above, being a scalar, corresponds to TAL angular momentum 0. We assume for simplicity THAT all the cent and g are real so that both particles are at rest. As explained in chapter 4, this means that the quantum potential is balancing the total classical potentials that are responsible for the stability of the atoms. Suppose now we made a measurement of the angular momentum of particle A in any direction. Because of the isotropy of the wave function, we can always choose this as the z direction. Using the theory of measurement described in chapters 2 and 6, we may assume an interaction H Hamiltonian. H1 equals L, JJ slash OI, 7.21. Where y is the relevant coordinate of the measuring apparatus and where is a suitable constant chosen so large that the measurement will be impulsive. The z component of the angular momentum operator for particle A is L A equals zxa oya yat oxa equals z 8 cents a, where cent A is the azimuthal angle of particle A. 722. If 41.a, y, represents the initial wave packet of the apparatus, then the total initial wave function will be non-locality 149. During the interaction, the wave function, x, will be proportional to euro equals L phi, ra, tf, dash, ra, a, y, jo at j. 7.23. Where O is a constant proportional to backslash. To obtain a measurement, O at must be large enough so that the a, y, j O at do not overlap for differ. And j. In this C as ETH there will be no interference between terms of different j, and the apparatus particle will enter one of THE packets corresponding to a certain value of the angular moment umjh. Thereafter it will remain in THAT packet and THE quantum potential will be determined by the corresponding wave function phi, 1, Ra, if I, R8. As explained in chapter 6. This means that everything has proceeded as if the wave function of the system had C elapsed till phi, Ra, Ely dash, 1, Ra. Not only will particle A have the angular momentum jh, but particle B will have the opposite angular moment umjh, so that the two angular momenta will be correlated, and this will happen for an arbitrary orientation of the apparatus. Thereafter, particle B will behave in every way as if its angular momentum had been measured and found equal to jh. As we all show, this correlation is evidently both context dependent and non-local. Indeed, we will find that B is dependent on the apparatus that measures A, which provides the non-local context for B. Of course, both A and B are context dependent in the sense that the angular momentum of each is a potentiality Th at is realized according to the orientation of the apparatus that measures A and the state of the hidden particle variables. Ya belonging to TH's apparatus. The Ca use of the correlation between the particles is evidently TH equan. Tum potential. It is interesting to follow in detail how TH's comes about during the period of interaction. However, to do this we shall use the GUID ANS conditions which, as we recall, imply the quantum potential. This potential can indeed be calculated from S/at, but it is very complicated. And it is more perspicuous to use the guidance conditions. We begin by expressing the relevant part of the wave function, 7.23, as the following. Euro. Sin 8a sin OAA, y, O at, expi, cent a, pa, plus a, y plus 0, at, expi, cent ia, cent ib. L. Plus 2 cos 8a cos 8ba, y. 7.24. According to equation, 722, the z-component angular mommy and tum of particle A is p.p. equals S/a. Cent ia. And of particle B is p.p8 equals S/a cent ia where S. 150 TLAEU undivided universe is the phase of the wave function. For t equals 0 the wave function is real, so that S equals 0 and both th particles have no angular moment More generally, the z-component angular moment of particle A will be given by, and a similar expression holds for the z-component of the angular moment tum of particle B. Assuming A, y, is real, we then obtain sin fja sin fjb. Re. M. Euro. A, y, at, expi, f, b. A, y plus at, xp, I, pb, jj. 7.25. Because the wave function depends only on the combination pb, it follows that as p cent equals apb equals p cent b. Initially when t equals 0, it is clear that p cent equals p cent 8 equals 0. However, after a short time the contribution of a, y, at, and a, y plus at, no longer cancel and the values of p cent a and p cent 8 will clearly then depend on y, which, as we have been assuming, has a random distribution with probability ia, y, 1, 2. All other quantities being equal, the angular momentum variables for A and B will then separate depend on the value of y. But the net result also depends on A and B, and on PB. It is clear that the behavior of particle B, for example, will depend on the initial values of FJA and PA, as well as on those of the apparatus. So we clearly have a non-local interaction. But it should be added that the net result for particle A will also depend on the initial properties of particle B. In other words, the result we get for an individual measurement of A already anticipates, to some extent, the way in which particle B starts out. That is to say, the non-locality is reciprocal. Because p cent equals p cent 8, we can be sure that eventually when the apparatus packets have separated, one of the particles will end up with a unit of angular moment and other with the opposite unit. The probability of each result can be obtained by integrating the square of the net wave function over all the relevant coordinates in C eluding those of the apparatus, and as is easily shown, this comes out the same as in the conventional interpretation. It is clear then that the assumption, 714, underlying Bell's inequality, is violated. For if we measure B, the result will depend, not only on the variables of particle A, but also on those of the apparatus that measures. Non-locality 151. A. From this it follows, as WEHAVE anticipated earlier, that this experiment involves not simple non-locality but rather a dependence on a naloc AL. Context. SINCE. The statistical results of our interpretation are the same as in the usual interpretation. We can see from the discussion in section 7.2 that the non-local quantum potent IAL cannot be used to carry a signal, if this later has to be detected statistically according to the rules of quantum theory. This means that there is no way to control the behavior of atom B systematically by anything we might do to atom A. 7. 6 LOSSOF non-locality in the classical limit. We have thus far gone extensively into quantum non-locality and have seen that it can arise in a great many contexts. At THIRD side one might be concerned as to whether we will then be able to understand why non-locality is not encountered in our common experience of the WORLD. Basically the answer to this question is quite simple. For our ordinary experience, both in the domain of common sense and in that of classical physics, is restricted to situations in which the quantum potential is very small, so that, in this context at least, it does not produce significant EPR correlations. FOR, as we HAVESEEN, quantum non-locality is entirely the productivity of the quantum potential. Nevertheless, it may be instructive to see in more detail what are the conditions which favor non-locality and what are those which do not. FIRST. Of all, it should be clear that EPR-type wave functions, which involve linear combinations of products of single particle wave functions, will be stabilized by suitable classical interaction potentials V, R, between the particulae. For example, in helium, the electrostatic interaction between electrons brings about a big energy difference between wave functions that are symmetric linear combinations of the one-particle electron wave functions and those that are antisymmetric linear combinations of these wave function S. And the interaction of the system with others which involve energies less than LL. These linear combinations of wave functions will remain stable. At the atomic level, LLE is quite large, and this explains why the chemi-Cal combination into mole CuLES holds together until they are disturbed by, for example, thermal fluctuations with temperatures such that Kt is not too much less than pound. With superconductors we also have the possibility of EPR-type wave functions. But since pound is SMALL, these can only be attained at low temperatures. The EPR experiment is concerned with situations in which there are 152 the undivided univer correlations between free particles for which T equals 0. It may therefore be expected that such EPR correlations may be very difficult to maintain, for example, in the face of collisions and various kinds of external disturbances that could change the spins of atoms. Indeed, if we regard measurement as a disturbance, we can see that it does indeed break the correlations and leaves us with product wave functions. More generally, we might consider what happens in a collision in which the angular momentum can be altered. We shall discuss the case of a molecule of total angular momentum 0 which disintegrates into two atoms, each of which has angular momentum h. While the atoms are flying apart, the wave function is given by 7.20a. Suppose a collision takes place between particle A and another atom, C, whose center of mass coordinates are re and whose internal coordinates are re. To represent the full details of this process would require a complex notation that would not be very perspicuous. We shall here simply outline only the essential results. Let us suppose that atom C has the wave function .pe, rc, ge, re, 1/re, so that the combined initial wave function for all three particles is .pe, rc, ge, rc, l/re, where is given by equation 7.20a, and where .pe, rc, represents a wave packet. In the collision process, the z component of the angular moment will be conserved, thus if I' plus I and j' plus j, then I plus j equals I plus j. In the final wave function there will appear products such as .pc, re, cent, ra, cent b, rb, g, e, rc, ga, ra, yb, rb, ij, I, re, 1/j, ra, lj, underscore, r, b. 726. Where .pc, re, represents a wave packet in which the center of mass of particle C will be moving differently from what it does in its initial state. And similarly for cent A, Ra, particles A and C will end up with energies that depend on their phi nl and initial angular momenta. Therefore, if, for example, particle C interacts with a st8 of angular momentum mh of particle A, its wave packet will move with a different speed from that of a particle that had interacted with an angular momentum of h, or 0. Sooner or later these wave packets will therefore cease to overlap A and D. The system will behave as if particle AHADC elapsed into a definite angular moment while particle B had collapsed into an opposite state. The effective wave function would now be a product of the type 726, and the EPR correlations would have van ished. This shows that even if EPR correlations should happen to arise under natural conditions, they would eventually be destroyed. No NL Ockley 153. 7.7 Symmetry and antisymmetry as an EPR correlation. A very important type of EPR correlation occurs with symmetric or anti-symmetric wave fuencations. H.O. Weaver, this type of correlation has an important feature that is different from those examples that we have thus far discussed. To see WHAT this difference is we phi rst. Note that for equivalent particles, the H Hamiltonian will be a symmetric function of LL the particle variables. It follows then THAT if we have a solution of the wave equation, the interchange of two p particles will generate another solution. We see A and then form linear combinations of solutions involving various permutations among the p particles. Among these the symmetric and antisymmetric combinations are particularly interesting because all Kn particles are either bosons or fermions which have respectively symmetric and antisymmetric wave fuencations. WHAT is particularly significant in the context of our discussion here is that there is WHAT is CALLEDA superselection rule implying that transitions between symmetric and antisymmetric wave functions can never take place, which follows from the symmetry of the H Hamiltonian. Therefore if one of the particles of such a system interacts with some thing LZ, for example, a measuring apparatus, it no longer follows that the unoccupied EDPA at CAN have no further effect on the particles. Rather, there can be such an effect, and THs is indeed what is ultimately responsible for the Pauli exclusion principle. To illustrate this, let us consider a measurement of a single particle. Operator OA with eigenvalues A and eigenfunctions 0 colon ace, Za. Because of the equivalence of particles, another particle B will have a corresponding operator 08 with eigenvalues B and eigenfunctions cent B, Zb, the wave function for the combined system can be expressed in terms of the products 0 colones, Za, cent B, Zb, if, for example, the wave function is antisymmetric, we can write with cab equals CBA. Let us suppose THAT we want to measure the operator 0A. AC according to the theory of measurement that we have given in chapter 6, to do this, we would need an interaction with the measuring apparatus, where y is the relevant coordinate of the measuring apparatus and backslash is a suitable constant. But for equivalent p-articles it is impossible to have such 154 THEV and undivided un ivory. An interaction A.S. This would destroy the symmetry of the Hamiltonian. 2. Obtain a symmetric Hamiltonian we write. If O, Si, is the initial wave packet of the apparatus we will obtain, after interaction. Let us choose a certain pair of eigenvalues A1 and B1. Their contribution to Tp will be O, 11, Ai, plus 0 colones, 11, Bi, 1 slash, A1, Za, 1 slash, B1, Zb, 1 slash, B1, Za, Tpa1, Zb. It is clear that the measurement has left the wave function antisymmetric. Suppose we phi and d that 11 is close to A1. But from this information we cannot tell whether it is particle A or particle B that is left with the corresponding eigenfunction. It follows then that there is no way in such a measurement to distinguish between particle A and partition B. This implies that quantum mechanically equivalent particles are indistinguishable, whereas classically they might, in principle, be distinguishable by putting marks on them. From this it has often been concluded that particles are not merely indistinguishable, but that they are identical. 2. Do this is to go from an epistemological statement referring to our ability to distinguish things, to an ontological statement referring to WHAT the particles are, i.e. one and the same. We recall from chapter 2 that in a positivist philosophy, epistemology and ontology are thus equated. But as we also stressed before, there is no real necessity to do this. Indeed, in our ontological interpretation of the quantum theory, we must say that although the particles are indistinguishable, they are still different, and that each one exists continuously and therefore H as its own identity. In order to obtain the predicted results of the quantum theory, there is no need to assume such an identity, for these results all follow from the antisymmetry of the wave function alone. Indeed, our interpretation gives the same results as those of the conventional ones, whether THP wave function is symmetric, antisymmetric or H as no particular SYMMPTRY. These results follow when we average over the positions of all the particles WITH. The probability density I and configuration space. To illustrate what is meant by the identity of a particle when the wave function is antisymmetric, let us again consider two particles A and B, with two possible wave functions. The antisymmetric wave function for the combined system is proportional to the momenta of the particles are PA equals FJS/OZA and PB equals FJS/OSB. It is clear that PA equals PB and that both particles are moving with the mean momentum, K1 plus K2/2. The probability that the particles are at the same place is 0, and this exemplifies the exclusion principle. The quantum potential is Q equals __L, K1, K2, 2M2. This is a constant and therefore it is consistent with the fact that the particles have no relative motion are equal that what is described as relative kinetic energy in the usual approach is here attributed to the QUA potential. When the time-dependent Schrödinger equation is applied, one will find that these packets move and spread in a way described in Chapter 4. We shall however suppose that this spread is negligible, so that the centers of the packets will move with velocities k(i)m and k2(m) respectively. Even twilly the wave packets will separate and then the wave function will be E proportional to I, ki plus knt. 111 feet 1 inch equals exp 2m x expi k1za plus k2zb exp% za exp% zb expi k2za plus k1zb exp-% za exp-% zb. At this point the two terms in the above wave function will no longer overlap, therefore they constitute separate channels in configuration space. 156 The undivided universe, into one of which the system as a whole must enter and remain thereafter. The unoccupied channel then has no effect on the quantum potential acting on the particles. Therefore the system is behaving as if it is in one of these channels alone, for example, the one in which the particle A has momentum k1 and particle B has momentum k2. In this state, the quantum potential between the two particles is zero as it was in the original state. But evidently while the packets were separating, but still overlapping significantly, there had to be a quantum potential which accelerated particle A to momentum hk1 and decelerated particle B to momentum hk2. The antisymmetric wave function is therefore a particular case of the EPR-type wave function with its non-local interactions. It is clear that once the particles have entered a particular channel in configuration space in which they are distinctly separated in ordinary space, each particle continues to exist with its own identity and continues this identity in its movement. We could in principle measure the position of one of these particles again and again, thus verifying that it continued to exist just as we could if the wave function were not antisymmetric. Although we could not know whether the p-article we observed corresponded to the original label A or B, we ld nevertheless be sure that we had detected the same particle in successive measurements and that the other, far away p-article, qld never become confused with the one that we had measured. Up until now it ld appear that the information in the unoccupied channel in configuration space had lost all potential for activity as it does for measurements in general in the way that we have explained in Chapter 6. Suppose however that We brought two particles BACK together by means of a suitable potential. This potential would also act on the unoccupied channel because of the symmetry of the Hamiltonian. So eventually the two channels ld meet, and we ld then lose the ability to keep track of the identity of each particle by further measurements, even though each particle would still retain its identity. The quantum potential would then be affected by the channel that had been unoccupied as well as by the one that had been occupied. And the particles would display the effects of the Pauli exclusion principle so that ld never be in the same place. As pointed out earlier, reason why the information in the unoccupied channel does not totally lose its potential for activity is because the antisymmetry of the wave function constitutes a superselection rule that is maintained in ALL interactions and therefore in all measurement processes. As WELL. When there is no superselection rule, the unoccupied channel is treated sufficiently differently from the occupied one so that it would be extremely improbable for them ever to interfere significantly again but. With the superselection rule this will, as we have seen, take place. It follows that the Pauli exclusion principle and all other effects of the antisymmetry of the wave Fu and Cetian are really manifestations of non-locality. In fact, this non-locality is so extreme that even particles that are very far apart must maintain unoccupied packets that allow the wave function to be antisymmetric, and it is just this whole set of packets that may later come together in such a way as to guarantee that the particles will obey the Pauli exclusion principle whenever these packets meet a guy n. 780 and objections to the concept of non-locality. We have seen that some kind of non-locality is common to all interpretations of the quantum theory which we have discussed thus far. Nevertheless, there have been persistent and strong objections to the consideration of non-local theories of any kind, usually with the hope that a local interpretation will sooner or later be possible. In ancient times it does not seem that strong objections to non-locality were very common. H.O. Weaver, by the 16th century non-locality did not seem to be an acceptable concept. For example, Newton referred to it as a philosophical absurdity. 18. This sort of view continued to modern times. Thus, as we have already pointed out earlier, when Einstein noticed the possible non-local implications of the quantum theory, he referred to it as spooky action at a distance 5. The general mode of explanation that is currently acceptable in science is either action through contact or else action propagated continuously by fields. Indeed, anything more than this is often regarded as incompatible with the very possibility of doing science. We cannot see any well-founded reason for such objections to the concept of non-locality. Rather, they seem to be more or less of the nature of a prejudice which developed together with the growth of modern science. First of all, the concept of non-locality is perfectly rational in the way that we have used it in our interpretation of the quantum theory. For it has led neither to internal logical contradiction nor to disagreement with any facts. Moreover, there is no thing in what we have done that disagrees fundamentally with the current scientific approach. Some people might object that if everything is strongly and non-locally connected, there is no way to do science, because we will not be able to isolate any system sufficiently to study it. But we have shown that in the context of the large-scale level, in which physical investigations are carried out, non-local effects are not significant. Therefore, our interpretation allows for exactly the same degree of separability of systems that is required for the kind of scientific work that is actually being done. We made non-local inferences about the finer and more subtle aspects of material processes, but these are based on ordinary rational scientific inferences. Indeed, it is just by using the well-established methods of science that we have been led to make such inferences of non-locality. Another objection to non-locality is that it would violate special relativity. We shall discuss this question in more detail in Chapter 1-2, where we shall show that our interpretation is, in fa-ct, compatible with special relativity. For the present we merely know that, as H has been shown in SEC. 7. 2. Quantum non-locality will not allow a signal to be transmitted faster than light by means of the statistical measurements that are basic to the current quantum theory in its conventional interpretation. Since our interpretation leads to the same results as do the conventional ones, it follows that through quantum non-locality there will be no way to exert instant control over what happens at far away places, nor to transmit signals to such places. We have not yet found what we could regard as a valid logical or scientific reason for dismissing non-locality. We are therefore led to ask whether there could not be some other kind of reason. It may well be that one of the main reasons that people dislike the concept of non-locality can be found in the history of science. For in the early period of the development of science there was a long struggle to get free from what may perhaps have been regarded as primitive superstitions and magical notions in which non-locality clearly played a key part. Perhaps there has remained a deep fear that the mere consideration of non-locality might reopen the floodgates for what are felt to be irrational thoughts that lurk barely beneath the surface of modern culture. But as we have argued, there is no inherent reason why this should happen. However, even if there were such a danger, this would not by itself constitute a valid argument against non-locality. Indeed, if one were to accept such arguments, one might equally well say, for example, that nuclear energy should not even be considered for further investigation, because it might lead not only to nuclear war, but also to radioactive contamination and to destructive genetic mutations. While it is necessary to be aware of all these dangers, we still have to be able to inquire freely into all these avenues of research. Chapter 8. The large-scale world and the classical limit of quantum theory. 8.1 Introduction. We have been discussing what may be called quantum reality as existing on its own without needing any observers, but capable nevertheless of containing observing instruments. We have suggested in several places that there is a continuous transition between this total quantum reality and the large scale world of ordinary experience. The question for us now is whether we can explain how this large scale world as a whole comes out of the basic quantum laws, or at any rate, those features of this large scale world that can be described in terms of classical physics. In other words, is classical physics contained in our interpretation of the quantum theory as a limiting case. In order to answer this question, it is essential to show that quantum mechanics contains a classical level which is not presupposed as in the usual approach, but which follows as a possibility within the quantum theory itself. Here we must point out that is by no means self-evident. It is, of course, clear that we will obtain classical behavior whenever the quantum potential is negligible. But as we shall see, quantum theory generally implies the possibility that even for very high quantum numbers, the quantum potential may still be large. The behavior at the large-scale level is therefore in general not necessarily classical. However, we shall show that the general conditions in the universe are actually such as to imply an approximately classical behavior for objects containing a sufficiently large number of particles, which means that there is a classical level that is essentially independent of measuring instruments. This is a distinct advantage of the ontological interpretation, for as we shall bring out later, all other interpretations presuppose a classical level, see Chapter 1.3, or ELSE. Imply the assumption of some kind of change in the basic theory, which makes possible the classical level. Step 1, Girardi, Rimini and Weber. GRW2 and Gel Mann and Hardel 3. The classical level is necessary not only because it is observed to exist, but also because within it, quantum mechanical processes can manifest themselves in phenomena which are essentially independent of further observation. As we shall see, it is this which makes it possible for people To establish and share knowledge of an objective nature in spite of the non-locality of the fundamental laws. Quantum theory. It has commonly been assumed that the classical level arises where h plus 0. But evidently, since h is fixed it cannot go 0. Whatwehavetodo is to derive the classical laws as approximations to the theory in which h is given its current value. But as we have already pointed out, it has to hold under certain conditions, which will be discussed throughout this chapter. With regard to this point, we repeat that it is clear that wherever the quantum potential can be neglected, the classical limit will hold as an approximation. For in the C as E the wave function plays no significant part in the determination of the motion of the particles, which then obey the simple Newtonian law. dp equals \I v dt 8.1. Insofar as this law holds, the ontology effectively reduces to a set of particles, A and D, of course ultimately, fields, as we shall see in chapter 1.1. Obeying the laws of classical physics. Moreover, as stated in chapter 3, there is a well-known approximation. The WKB approximation, which gives rise to solutions describing classical trajectories. As we have already pointed out, this approximation becomes valid when the quantum potential is small compared with the kinetic energy. One can show for that this requirement will be satisfied whenever the potential varies smoothly enough so that the change in de Broglie wave length 6x within a wavelength is small. One can also show that satisfaction of THIS condition will guarantee the smallness of the quantum potential. We emphasize again that this criterion was developed for the special case of a wave going in a definite direction. However, a linear combination of such solutions correspond to waves going in opposite directions will still be a solution of Schrödinger's equation with the same energy. But SUCH. A linear combination will not in general have a negligible quantum potential. 1/6 the undivided universe. Even though each of the functions that makes it up does have a negligible quantum potential. Suppose for example that we have a system that varies only in the z direction and whose properties are uniform in the y and z directions. Suppose further that we have an electron moving in the z direction which is bounded in a space whose edges are defined by a potential v, z, which we assume to vary slowly enough so that we can apply the standard WKB techniques. ONE solution for THE wave function is then, where p, z, equals J2m, e, v, z. Another solution is 1/j underscore, z, equals exp. 1 rp, z, dz. vp, z, o. 8.2. 8.3. Each of these, of course, h as a negligible quantum potential except at z equals a. And at z equals 0, where these are the turning points of the particle at which p, z, equals 0. To find the stationary states of the particle, we take a linear combination of the above two solutions, 8.2, and 8.3, in which iai equals ibi. While the phases of a and b are chosen so that the wave function fits a decaying exponential beyond z equals a and z equals 0. One finds that solutions are possible only for certain quantum numbers, n, representing the number of nodes of a wave function satisfying the Bohr-Sommerfeld condition, c. Bohm 4. The solution inside the box is then iai 1 r 1/j, z, equals JPWSMH 0 PDZ plus cent 8.4. where cent is The appropriate phase factor which brings about The phi t. With this linear combination We obtain a quantum potential which may be quite large. A simple calculation shows that this is Q equals P2, Z, 2m, 8.5. Since the wave function is real, the particle is at rest inside the box and its kinetic energy has been transformed to the energy of the quantum potential. As explained in more detail in Chapter 4. The large SCL world A and D, the CL ASICL limit 163. To simplify the discussion, we may consider the case in which the potent eels become in phi ni tele high at x equals 0 and at x equals a. This is essentially a box of size A and the solutions are T/x equals a sin n1 x a 86. It is clear for THSA solutions that THE velocity of THE particle is 0 and that there are n1 nodes in the wave function at which the probability is 0. The picture according to our interpretation is that the particle is sitting at a particular position so that it is consistent to say that it never reaches a node. For SMALL values of n, this perhaps does not violate our intuition. But when n gets large, we customarily expect that classical behavior will result. Yet we can see THAT, no matter how large n is, we do not go to a classical limit. Einstein 5 objected to this result because he felt that when n becomes sufficiently large, we should always approach a classical behavior in which the particle is moving back and forth with equal probability in both directions. Nevertheless, independently of our interpretation, we can see THAT. This is impossible with the wave function 86, because it has nodes at which the probability density is 0. If THE particles were moving back and forth at uniform velocity, these nodes will not be possible. They might however be possible if the particles speeded up to infinite velocity where the wave function is 0, but this would violate classical intuition even more than our assumption that THE particles are at rest. Einstein's picture co-ULD only HOLD, therefore, if the quantum theory itself began to fail at sufficiently HIGH quantum numbers, for example in the way that could be implied in later suggestions of Rosen 6, as well as by those of Leggett 7 and Penrose 8. As we have already indicated, however, we are exploring the hypothesis that quantum mechanics is universally valid, and it is therefore necessary to see whether this is coherent with our general experience at the CL level. Of course, it is not part of the quantum theory to say that CL ASICL physics always holds at the large scale level, or at high quantum numbers. Indeed, there are strong reasons to suppose that it should not hold always. In this case, to bring this out, one could assume, for example, that The walls of the box did not correspond to an infinite potential, but rather to a finite, though large, barrier of limited thickness which could, therefore, be penetrated. In this case, the system would be analogous to a Fabry-Perot interferometer. Therefore, if electrons were incident on one side of the barrier, they could not only penetrate, but could also show transmission resonances for certain incident momenta, see bohm 4. These are characteristic quantum 164 THEUND1 T11 DEDUNIVERSE. AB. Beam B beam A. Figure 8. 1. Deflection of two different portions of a plane wave by an inhomogeneous field centered at C. Mechanical effects. Indeed, if these effects are not found even at arbitrarily large di stances and for arbitrarily high quantum numbers, we will have to conclude, as Einstein has implicitly assumed, quantum theory itself must fail here. However, it should be noted that Tonomura et al. 9 have demonstrated experimentally with electrons that the quantum theory holds for quite high quantum number BERs. It is necessary nevertheless to explain why such non-classical behavior at the large-scale level is not more commonly encountered. At first SIGHT. One might suppose that this could be understood by considering the fact that our Fabry-Perot interferometer would require extremely accurately machined parts and extremely accurately held positions. Clearly these will not be EFU and D in NA-TOR and will be very difficult to produce in THE laboratory. However, THIS argument is not adequate. THIS basically because the criticism raised by Einstein implies more generally that non-classical behavior will be obtained whenever waves of appreciably different wave numbers CROSS. In the case of the particle in ABOX there are only two such waves going in opposite direct ions. But actually there is a wide variety of solutions in which many waves could cross. For example, we may have a wave foo sensation spreading over a large area with a fairly well-defined momentum satisfying the WKB approximation so that the particle will be having classically. Then by means of inhomogeneous forces occurring naturally, contributions from two different parts of the wave front may come to overlap, as shown in figure 8. 1. The large-scale world and THECL classical limit 165. In the region, 0, of overlap, the orbits will become highly irregular and the p-article will jiggle rapidly because the quantum p-potential is both large and rapidal y varying. Indeed a p-article originally passing through A may be deflected while it is in the region 0 in such a way that it leaves in the beam coming from B. THIS means THAT the non-classical BEHAVIOURIS. Not restricted to the region 0 where THE quantum potential is large. Of course, as we have shown in the previous chapter, the statistical results of measurements will still come out consistently without violating the LAWS of the quantum theory. But the individual processes will have highly non-classical implicatio ns. As we have remarked earlier however, such situations can readily arise in many ways. Indeed, as we shall show, even if we consider systems as large as planets and stars, the wave foo sensation of the center of mass may spread over large areas. As long as contributions coming from different parts of the wave front do not cross the behavior of the objects concerned, will be essentially classical. But an inhomogeneous gravitational field, for example, can bring about just such a cross and G. And when this happens, the stellar or planetary trajectories would jiggle violently and be deflected in non-classical ways. IFTHEPOS OFTHSA objects were measured, e.g. BY telescope, SUCH. Interference would be destroyed. However, it does not seem to be satisfactory in an ontological theory to obtain classical behavior of large scale and distant objects solely with the aid of measurements. 8. 3 large-scale object SINTHE classical limit. It is clear then THAT we need to go foo RT her to develop a THE ori of ACL classical level THAT arises NATU rally in the universe. This should give an ontological Explanation of not only planetary and stellar behavior, but also THAT of large scale objects in general, including, of course, measuring instruments. Large-scale objects in general are described by collective coordinates. Moreover, if the classical behavior of stars or planets would depend on measuring instruments, it would still be necessary to show independently THAT. The ontological interpretation of the quantum theory implies THE possibility of having measuring instruments which will be stable and behave classically. With OUT the need of further instruments to establish THSA properties. This question evidently has to be treated in a cosmological context. It is not necessary for our purposes to go all the way back to the Big Bang. Rather it will be convenient to begin with that phase of the universe that followed the inflationary period. By THIS time protons and electrons have been formed in states of high energy. But as the universe cooled down, it became possible for atoms and molecules to form, the excess energy being given off as radiation, which was disposed of by its spreading through the empty space created by the expansion of the universe. From then on, as the universe cooled further, larger aggregates of matter were formed, leading to galaxies containing stars, planets, and other objects of Ths nature. Later still the temperature dropped so as to form solid matter Th at H at a stable atomic structure, e.g. crystals. Whichever interpretation of quantum theory we use, this result will follow. For as the energy of aggregation is disposed of in the form of field quanta, we will finally be left with The wave functions involving stable configurations OFFAIRLY low energy. A detailed account of such processes will be Fu and D in Chu 10. Once we have stable solid structure STHN, we see an form arrangements of matter which constitute measuring apparatuses, and we have the possibility of leaving an irreversible macroscopic residue which can constitute a record held in this stable structure. In chapter 6 we did THs in terms of THE discharge OF an ion chamber. Another example would be a photographic plate which would respond to a single particle by irreversibly producing a set of grains of silver. It is thus clear THE existence of THE observing apparatus can be understood in terms of our ontological interpretation. Moreover, wherever stable solid matter is formed, each atom is localized relative to the others within a fairly well-defined range of the order of THE interatomic spacing. Because THE spread OF the wave function is so limited, there will not be significant interference of contributions from DIFFER and parts of the wave function. WH was described earlier in Connect Ion with the galaxies, stars, and planets. Thus THR will be no problem in showing the classical behavior of various parts of the Earth relative to each OTHER, and of all the various macroscopic objects THATRATT attached to the Earth H, OF, QRSE, including measuring apparatus, laboratories etc. Evident LYTHIS sort of localization of atoms relative to each OTHER depends on the strong forces of MUT-UAL interaction between THM. However, when it comes to the center of mass of the whole object THR are in general no such strong forces. There is then no reason why the wave function of THE center of mass should not spread OUT over indefinitely large areas SOTHAT. Its various parts may come to cross in the manner described earlier with resulting non-classical behavior. ONE of the basic questions TOBE addressed is therefore THAT of finding out what determines the center of mass wave functions of the various objects in the universe which need not be strongly localized relative to each OTHER. Consider, for example, the case of galaxies, stars, and planets discussed earlier. What determines the spreads of the wave functions of their centres of m and 88? To answer this question we have to go back to the process in which THSA objects were formed from elementary particles. Ideally we would need to know the forms THAT-THSA wave functions took when the particles were phi rst. Crete ed. At present there is no well-defined answer to this question, but we may explore a range of possible answers. Case AIF, for example, the particles are created WITH localized wave func. TONS, the wave packets would spread so that we would be left WITH. Very NEARLY plane waves in EACH region OF space. The quantum potent TIAL would be negligible except when parts of the waves were made to cross as discussed earlier. Case B, the other extreme POSSIBILI is that particles are created as stand ing waves COVERING the whole of the closed universe, WHICH would, for example, be spherical in the C as E of a universe described by a Roby ns on Walker metric. In this situa Ti on the quantum potent TIAL would be ELARGE everywhere and would remain LARGE as the universe. Expa and D ed. EVNIF there were IN homogeneities which broke the sphere. ICAL symmetry, there would still be a great deal of crisscrossing of waves HAVINGDIFF errant wave numbers and directio ns, so that the quantum potential would remain generally large. Therefore we would not have an approximately CLASSICAL level at this stage of evolution of the universe. To CHOWA classic AL left EL may develop in both TH cases. Let us now consider WHATHAPPNs as the particles aggregate to form large-scale OBJECTS. The mean momentum of the center of mass will be the sum of the mean momenta of all the particles that have come together. In the case of AP, approximately plane waves resulting from the spread of the original wave packets, CASEA, we will obtain a well-defined momentum for the centre of mass WHILE. The POSSIBLE positions WILL spread, in principle, over the whole universe. In the case of stand ing waves, CASEB, however, the momentum of the center of mass WILL not be WELL defined, but will have a spread due to the spread of the momenta and the wave numbers of the original particles. If we make the reasonable assumption that the momenta of the different particles com in random ways, the mean spread JOKJI and the wave number K of the center of mass will be JOKI equals Vn loco L, where local is THE average spread in the wave numbers of the individual particles. The quantum potent TIL WIL BOFTHE order of H2H2LOKOL2 Q 2 1 1 low KL2 equals -2 _MO_, where M equals MO and MO is the mass of the origin AL particle S. No matter how large N becomes, Q will L thus remain more or less the same value as IT. 168 THE undivided UNIVERSE would be for one atom. In a large system this is evidently negligible. The wave function will then be close to a plane wave, or more generally to a WKB approximate solution of the form T/JXEXP is /1 in which there is no significant crossing of contributions from different parts of the wave front. To make a quantitative estimate of the spread of momenta, let us consider the extreme assumption that immediately after inflation the protons have a spread of wave vectors corresponding to a wave number MOC/h. With this assumption, even a SMALL object weighing 1 gram would have a spread of velocities of a few centimeters per second, while an object as large as the Earth would have a spread of velocities of 10 to 9 times smaller. Clearly then, both for case A and case B, the overall wave function of the whole system will take the form L equals f x cent x1 xn 1, where f x represents the wave function of the center of mass and cent x1 xn I represents the wave function of the internal state of the SYS tem. Therefore, in general, large-scale objects in free space will have wave function sprea ding over large areas. However, these objects will nevertheless behave classically, except when contributions from different parts of the wave front are made to overlap by the action of inhomogeneous gravitational fields. In this case, the wave function becomes where t/ja x represents the beam coming from A and t/jb x that coming from B. This wave function gives a quantum potential that is not negligible. And we have the possibility of a non-classical behavior of objects as large as stars and planets. We must evidently find further arguments to eliminate this possibility. To prevent interference of contributions from different parts of the wave front, we must have some natural process analogous to the making of an irreversible record in the apparatus as a result of a measurement. Entirely what is required is that the general environment be suchs to allow the possibility of changes in it to take place which remain stable and which are different for different possible positions of the object in question. There are a number of ways that this might come about, but we will discuss just one of these. What we shall show here is that if there is a suitable radiation falling on these objects, we can achieve our objective. To simplify the discussion, we shall begin by considering a planet that is illuminated by light from a single star. If the planet is far from the star in question, the light will be parallel. The planet will therefore cast a shadow, which will be essentially a cylinder extending in the direction of the light. The large-scale world A and D, the classical Li MIT 169. B. May. S.Al. Figure 8. 2. SHA DOWS SA, SB, etc. Arising from possible positions of PLA net A, B, etc. When I illuminate by LIGHT from a distant anti-star. Because of diffraction, some light will enter the shadow. The diffraction angle will be of the order /A, where is the wavelength of the light and A is the size of the object. Then as we move along THECILINDER at WILL beg IN to phi LL with LIGHT and ATA distance OFA2/. This shadow will more or less disappear. Therefore the volume of the shadow is of the order of 4/. With a type PICALPLANET, A, 109 EMS and 105 EMS, the volume is 1032 cubic centimeters. Let us now consider two possible positions of the planet, A and B. Suppose there is a center, C, of gravitation attraction which Ca uses the two parts of the wave function Tion respectively passing through A and B to over LAP. At 0. Without the starlight we would have interfere NCE at 0 with resulting non-classical behavior of PLANET center of mass, see figure 8.2. To see what happens in the starlight we must take the shadow into account. If the PLANET is at A, it will have a shadow SA, but there will be no shadow I and the path B. Conversely, if the particle is at B, it will have a shadow SB, but now there will be no shadow I and the path A. Let us consider the case. When the PLA net is at A, then as it moves, its shadow moves with it from SA to SAY, SA, as shown in figure 8. 2. There will be no shadow associated with the PATHB. In order to see the effect of these shadows on THEQUA atom potential, we know THAT the total wave function must now INCLUDE not ONLY. That of the wave function of THE planet, LP equals TBP, x, cent p, x1, xn, d, but also that of the electromagnetic field as modified by the shadow Ws. We WILL. NOW show that ITISTHE presence of THE wave function OFTHE electromagnetic field that is responsible for the quantum potential acting on the PLA net 2. 170 THTUNDI1J1DEDUNIVERSE. Remain small l. We HAVENOTTHUS far in THIS book given the ontological interpretation of the electromagnetic field. A treatment of the field is H.O. Weaver given in Bohm 1.1, and a more detailed but simplified version. Underscore. Using a underscore scalar underscore field is presented in chapter 1.1. We shall here discuss the basic principles m terms of the scalar field. Let A be THE wave function of the field in THE beam A. This wave function includes the effects of the shadow cast by the PLA net, if it is actually in the beam A. Similarly, let S be the corresponding wave function for the beam B. The total wave function corresponding to the two possibilities shown in the figure is IJR equals 1 FA, X, A1, plus 1/S, X, as 1, cent, X1, Xn underscore I. The internal wave function of the planet is represented by cent, X1, X, N underscore I. We make the reasonable assumption PTI on here THAT the absorption of THIS light by the planet will not make a significant change in THIS wave function because the planet is so large and the intensity of starlight is so small. Evidently, this wave function does not depend on whether the PLA net is at A or at B. With the arguments THAT are given I and the appendix TO chapter 1.1, we can show that there can be negligible overlap between the overall wave functions corresponding to the two beams. The condition for THIS will be E. Seen to be essentially that EACH shadow contains a large number of quanta. When THE beams cross their WILLTHE and be no interference A and DWE will HAVE. A classical behavior. This condition is in fact satisfied WITH the LIGHT from a single star. To see this we note that the number of quanta in a cylinder of volume V is EQUAL to V/C. With our value of V a 4/.x and WITH the estimated intensity from a typical star as 104 quanta per cm2 per second, we obtain a total number of quanta of the order 1025. Clearly the condition for no interference is satisfied for planets and indeed for objects that are quite a bit smaller. Even when the effects of the light from a single star are taken into account. We have thus far assumed that the star which is the source of the light is at a well-defined position and that there will be no possibility of interference with light coming from the star at another possible position. In effect we have been supposing that the wave function of the star is a small PAC ket, which spreads negligibly because its mass is so large. But according to our earlier argument, we cannot guarantee Th at such a wave function will have arisen by evolution from the early phases of the development of the universe. Therefore we must consider the possibility that even the star has an indefinitely extended wave function, which, however, according to our previous arguments must have a fairly wheelie defined wave number. But we can see this will not change our conclusion. Thus according to Figure 8.3, if the distance AD, The change in angle of the light will be the large-scale world A and D, the classical Li MIT 171. A planet. Figure 8. 3. EFFECT of a LIGHT source at a finite distance from planet. Negligee BLE and everything will happen as before. If, however, AD, then the direction of the light will be appreciably different. However, interference between contribute ions from different planetary posit ions is only possible if there is some INH homogeneous force which could bring contributions of the wave fun CTION of THESTAR from A and from A together. But these distances are so large that we see ANNOT any reasons to suppose THAT this co-ULDHA pen to any significant extent. At THIS point it is interesting to as KWHAT will HA pen with LIGHT so URCES. That are CLO ser THA and the stars and therefore correspondingly stronger, e.g. THE sun. Here the light WILNOT be parallel, BUTWILLHAVE assert in range of angles A. The range of the SHA dou is A/A, but there is of course the penumbra THAT extends indefinitely with decreasing intensity. If we consider the shadow alone, the number of quanta in it will be the order of a 3/AC, I, where I is the intensity of the light. In the C as EOFSUN lig HT, A0, 01 radians and the intensity OFLIGHT will be 1010 quanta per cm2 per second d. For an object of the order OF1 cm in size, THIS will give rise to something ing. LIK 1010 QUANTA in THE shadow. Clearly for objects OFTHISSIZE and down to about 10 to 3 EMS, interference will be destroyed and the BEHA VIOUR will be essentially classical. Moreover, once interference CE has been destroyed, then the wave packet will not subsequently spread appreciably because the objects are so heavy. These considerations could thus also be applied to small l objects on the surface of THE Earth that have become free of THE solid structure of the Earth. We have thus far ignored THE possible contribution of the penumbra to the destruction of interference and the resultant establishment of CLSICL behavior. Indeed, further investigation shows that light, for example, from 172 THEUNDLLIDed UN1T1 ERSE. Different parts of the SUN will HAVE its wave function multi-IPLIED BYTHAT of the different atoms THATHAVEEMITT ed IT. The essentially parallel BEAMSTHAT. Have EMA and A TED from each region could then be treated independently and as a result could add to the destruction of interference even WHNTHEYRIN. The penumbra. Evidently there could be many other kinds of radiation THAT. Could produce similar effects. ALL of this could decrease interference still further and could bring about classical behavior for yet smaller objects. We conclude then that with reasonable assumptions about conditions prevailing throughout the universe, THE quantum theory implies a CLSICAL level that is independent of measurements made by human beings. H. O. Weaver, it would be important to do further work aimed at giving a more extensive discussion of these conditions. 8. 4. Illustration of the destruction of interference in terms of streams of particles. In order to give a simple explanation of how interference may be destroyed by a beam of light quanta, we shall here discuss a similar process inwhich. An object is exposed to a stream of particles, e.g. neutrons or protons, from a distance our CE. In The Appendix TOCH Chapter 11 we shall see THAT. Essentially the same kind of reasoning will apply to light quanta. INTHIS example WEWILL evidently have THN a very nearly parallel BEAM of particles incident on the object in question. We will assume THAT if a particle strikes the object it will be absorbed and THAT otherwise THE is no interaction with the object. The incident wave fuencation of the NTHPARTICLE will then be a plane wave \n equals exp nxn. The total wave function of The incident particles will be incident equals 2 exp n xnln. But actually the wave function of EACH particle will be modified BE. Cause the object will leave a fairly well-defined shadow, limited only by THE. Diffraction angle O\A. The location of TH's shadow will depend on THE. Location 11 of THE object. Specifically, THE wave fuencation of the nth part ICLE will be \NEXP NXN except for the region of the shadow where it is 0. The wave function of the nth particle can't HEN be written as where S, 11, is a function that is unity everywhere except in a cylinder of base of the order of A, which latter is centered at 11. Let us now consider the wave fuencation of the object, W which corresponds to THE planet in our previous example as illustrated in figure 8. 2. R. Question is whether contributions 1/JA, Y, and 1/JS, Y, to this WAVE fun CT ion. From two DIFF errant regions A and B C A and BE made to overlap in some region 0 the net wave function representing these two contributions together with THAT of the N1HI incident P article will be 87, where NA is THE wave function of the N1H P article as affected by the object at A and .NB is THAT as affected by the object at B. In order to make a calculation possible, let us suppose that the wave functions NA and NS are limit to some box OF side L, where L is very large. Interference between THE2 contract IButions to W in equation 8. 7 will be possible only for those values of xn for WHICH, NA, xn, and NS, xn. Overlap, BUTWILL not be possible for those values of xn for which one of these functions is 0. SINCE the wave fuenct ions NA, xn, and NB, xn. Spread over very large areas, most of the values of xn will produce overlap. But a fraction of the order of f equals a 3/0, L3 of the possible values of xn will not give rise to overlap. This fun CT ion is essentially the ratio of the volume of the cylinder whose base is the object in question and whose height is the dis tans A/O, equals a 2/.NWITHIN which diffraction will not produce in APPR equable WIDENING of the SHA DOW. It is clear then that if we consider just one single particle there will only be a slight probability 0 equals FTHAT interference will be destroyed, and a corresponding probability equals 1. F. That it is not destroyed. But if we consider NPARTICLES together, the probability THATI interference is not destroyed will be the product. Since F is SMALL, evidently NF is just the number of particles in THE shadow, so IFTHIS number is LARGE enough interference will be destroyed. IFTHE incident number OFP articles PERCM2 PER second ISI and their mean velocity is v, then the total number of particles in the BOX WILLBE. L3I/V. THE probability PNWILLTHENB. We can see that interference will be destroyed if I is large enough so that there is a large number of particles in the shadow. This criterion for negligible interference is basic LLY, the same as the one we give earlier for light quantity 174 the undivided universe. 8. 5. The extent of non-classical behavior. We havealready seen that non-classical behavior could occur for individ UAL particles in many situations in which the QUA atom numbers are large. Even for larger objects containing many particles there may still be non-classical behavior except under conditions INWHICH quantum interference is destroyed, for example, by suitable radiation. In this section we shall go in more detail into the nature of this non-classical behavior. Let us begin by considering the case of a microparticle MOVING in a box. This particle is constantly reflecting off the walls of the box. Even if these walls are smooth and regular, the corresponding wave function will reflect back and forth many times so that a great MA New York waves of LARGEWAVENUM going in different directions will cross. If the walls are irregular, this breakup into smaller waves will be even stronger. Eventually we may expect a nearly isotropic distribution of waves whose velocity fluctuates around a mean of 0. At this point there is little kinetic energy in the particle, and most of the energy will be in the quantum potential. Such a behavior, which is evidently no cycle, can occur with QUITELARGE boxes. This behavior in WHH the microparticle has a small fluctuating velocity is evidently an extension of Einstein's example of a particle in a one-dimensional box. It called dpe raps give an approximate imate description, for example, of an electron in a metal. In order to illustrate this behavior in a simple case, let us consider a particle in a two-dimensional box of side L. We shall simplify further by neglecting the molecular constitution of the WALLS. The wave function can then be built out of a set of eigenfunctions of the energy of the free particle. That is M1Tx, N1Ty, I7, 2, T/Mn equals ASM, Y, SM, L, EXP, 2, MHL2, M2 plus N2, T. Although we are neglecting the molecular constitution of the walls and determining the stationary states, we see and still say that the walls produce a net wave function that is a complex linear combination of eigenstates in WHICH. All the T/Mn are involved. Let us write this as dot slash equals LCMN T/Mn. Mn We have already seen that for a single eigenfunction t/jmn, The particle is at rest t. But this need not be so for a general linear combination. Indeed, the velocity of the particle is h dot slash vt slash t slash vt slash jv equals 2 miles 1 slash t slash. The large-scale world A and D, the CL classical limit 175. With T1 equals P, we see AN right for the component of the CUR rant. PV 2 L I EXP 2 H M2 plus N 2 M 2 N 2 T MN M7RX N7RY MRRX N17RE XM cos L SMYCMNCMNSM L SM L 1M 1 7RX N 1 7RE M7RX N7RE MCMNCMN cos L SM L SM L SM L, and similarly for Vy. It is clear THAT for the general CM, and this does not vanish. Do you understand why THIS is so? We may first note THAT. If we take different eigenvalues of the energy, we will obtain a probability density that is a function of time. This evidently implies THAT there is a net current T. But to obtain such a current T, DIFF errant eigenvalues of the energy will not be needed as long as these are degenerate. For example, we see and consider a system with spherical symmetry, in which there are 3 eigenfunct of the energy corresponding to a p state. If these are taken as real, they are p proportional to x, y, and z. For each of THESE wave fund CTIONS, the velocity is 0, but for the linear combination x plus e, the z component of the angular momentum is h, corresponding to a circulation of the p radical around d, the center. To return to the c as e of a p radical I and the bow x, we see from the above equation THAT the current, and therefore the velocity y, is constituted of a largenumber of terms, each of which is SMALL. As the p radical moves, the sin and cosine terms will change rapidly, especially for large M and N. The situation is in some way similar to that of the Lissajous figures, because VR and Vy will contain many terms of very high frequency which are in complex PHSE relations WITH each other. Although THE wave numbers are in integral relationship here, these are SOHIGHTHAT. We are approaching the case in which the frequencies of the x and y motions are not commensurable. The velocity is thus built of many terms whose phases will have extremely complex relations with each other. Moreover, for a real bow x, there would no longer be a simple integral relationship of the wave numbers of the eigenfunctions of the Hamilton IAN. ANY irregularity would destroy this, as would also a change to a more complex shape of the box. This would imply that the frequencies and wave number BERs were are rationally related, as is well KNOWN, under these conditions, in which a motion is constituted of many submotions with very complex PHASE relationships, the particle will follow an irregular trajectory which can eventually come arbitrarily close to any point in the bow x. Indeed, even 176 the undivided universe. If we restricted ourselves to a linear combination of eigenfunctions of the same energy, this sort of result would still follow. In this way we see that, going only to the two-dimensional case, we obtain for eigenfunctions of the energy a quasi-chaotic movement, as we shall show in the next chapter. This conClusion is strengthened when we go to more complex systems. Even if such objects are suspended in liquids or gases, the possibilities of interference will be limited because their mobilities are so low. It is clear that there will be an interesting area of study in the mesoscopic range between the CLSSICAL and QUANTM domains. It is perhaps significant that in this range the simplest forms of life are to be foo and d. Of course IFWE try to use precise measurement to observe the behavior of such objects. They will be PUTINTO well-defined positions and will behave essentially classically, provided that they are heavy enough so that their wave paits do not spread significantly during the period of the experiment. This means that the study of the mesoscopic region will require more subtle means THANCANBE provided by exact measurements of the usual key and d. 8. 6. The quantum world and its classical SUB world. We are now in a position to give at least the general outlines of an overall worldview that is implied by our interpretation of the QUANTUM theory. Our experience is, of course, of a world that is revealed to us fairly ctly by our senses in relation to our outward actions and inward reflections in thought. The immediate experience in this world is that which is described by what is called common sense, but later, as Bohr has pointed out, this is refined, where necessary, to the more exact description of CLAC. Cal Physic S. Within the domain of such experience it may be said that this world is manifest. According to its Latin root, the word manifest will signify what can be held in the hand. More generally it is what can be held in the hand, the I, and D, of course, scientific instruments. Its basic characteristic is that it contains certain relatively stable structures that make the holding possible. These structures must not only be relatively stable, but also essentially local. Everything in THIS world can be ultimately constituted of such structures which are outside of each other in every sense, and which interact only locally. Without such a world we would not be able to make sense of our observations of matter, nor to assign uses in any orderly way. Indeed it is for this reason that there is a natural reluctance to consider ideas such as non-locality and indivisible wholeness, i.e. non-separability, into independently existent component parts. When we come to the UND early in QUANTM WORLD, we find it has a radically different nature. To be sure we still assume a particle, WHICH at first sight while D appear to be what is also done in classical PHs. BUT. WE now SAY further THATTHISP article is PR found DLY affected BYTHEWAVE. Functionation, i.e. through the QUANTM potential and the GUI-DANCE condition. The action of the QUANTUM potential depends only on its form and not on its magnitude, so its effect may be dominant even when the wave intensity is small. This implies the possibility of a strong non-local connection of di stant particle and a strong dependence of the particle on its general environmental context. The forces between particles depend on the wave function of the whole system, so that we havewhat we may call indivisibile. Wholeness. This means THAT for different wave fu and sections we see anhave radi. Kali different connections between particles, not expressible, for example in terms of a predetermined interaction potential. Thus there is a kind of objective wholeness, re-MINISC and of the organic wholeness of a living being. INWHICH the very nature of each part depends on the whole. ALLTHISBEHA vior is VERY different from what is to be expected CL as SI. Kali. Indeed as we HAVE already explained in chapter 3, CL classical physics. Depends not only on Newton's laws of motion for the particles, but also on the nature of the potentials acting on them. The quantum potential implies so fundamental a difference in the behavior of particles that we cannot regard the latteri in general as remotely classical under most circumstances. Because of non-locality, quantum jiggling under quantum interference conditions and other quantum properties to WHICH we HAVE alluded, we may say that the quantum world is subtle. According to The Dictionary, this means rarefied, highly refined, delicate, elusive, indefinable. Its root meaning is based on the Latin subte slees which signifies finely woven. Clearly the quantum world as we have described it cannot be held inthe hand or inany other way. The very effort to hold it, e.g. in measurement, produces thoroughgoing predictable and uncontrollable changes in it. Each element participates irreducibly in all the others. The absence of mutual externality and separability of all the elements makes THIS world very elusive to the GRSPOFOUR instruments. It slips through the ordinary nets that we HAVE devised to hold it. Nevertheless we are PROPOSINGTHAT. It is real and indeed that it constitutes a more basic reality than does THE classical WORLD. Indeed as WE have shown, THIS classical world comes out of the THEory as relatively autonomous. This autonomy arises WHEREVER. The quantum potential can be neglected so that the classical world can be treated on its own as if it were independently existent. But according to our interpretation it is actually an abstraction from the subtle quantum world which is being taken as the ultimate ground of existence. In the quantum W world there is no way to obtain an object display of results because everything in it is so irregularly mobile, subtle, and mutually interdependent. But in the classical subworld, events can happen that are negligibly affected by our measurements and observations. This sub-W world includes not only particles, but also fields. We HAVE not yet discussed the fields, THUF, as we have already pointed out, THIS will be done in some detail in chapter 1.1. Nevertheless WECANSAYTHAT the movement of classically describable distribution of charge will produce classically describable movements of fields. This world of fields and particles is what conveys information to our senses in a well-defined way. Indeed we know of no other conditions in which this could happen. For example ITIS well can own THAT the ICANBE. Sensitive TOA few quanta ATA time, BUTTHE reception OFASM all NUM burr. Of quanta gives only THE vaguest sense of optical stimulation. Meaningful Perception requires a large number of quanta and therefore, along the line-s. We have already explained this will imply an essentially classical behavior. Meaningful communication between people also requires classically describable processes involving a large number of quanta. Thus it is not that we are assuming that the brain responds only to the states of particles and not to their wave function. Rather we are simply calling attention to the observed fact that meaningful sense perception and communication hsto. Go through classical level in which the effects of th's wave function can be consistently left out of account. But, of course, this does not mean that we cannot learn about quantum world. Instead, as we have shown, for example, through a process of amplification and recording in the stable structure of a measuring apparatus, the over quantum world can manifest itself in the more limit classical subworld. In demonstrating THIS possibility we have not had to assume any kind of cut between these two worlds such as that supposed by von Neumann n. Rather there is only one overall quantum world which contains an approximate immediately classical subworld that gradually emerges under conditions that have been described throughout THIS chapter. As we have said earlier, we do not believe that THIS kind of result has been achieved by other interpretations without making assumptions that go beyond the scope of the current quantum theory. Moreover, it is significant to note that it is just the most characteristic quantum properties such as non-locality and undivided wholeness that bring about the classical world with its locality and separability into distinct components. Thus, for example, in a measurement it is the non-local quantum potential produced in interaction with what may be a distant piece of apparatus that separates the wave function of the observed system into distinct channels that can be treated locally. Similarly, with planets, it is the wave function of the incident radiation with its distant shadow that destroys interference between contributions from different parts of the wave front and thus brings about a simple local behavior. In a certain sense we could say that the overall quantum world measures and observes its ELF. For the classical subworld that contains the apparatus is inseparably contained within the subtle quantum world, es. P shall ly through those non-local interactions that bring about the classical behavior. In no sense is the observing instrument really separate from what is observed. The relative autonomy of the classical LEF-EL that we have already discussed is then what makes it possible for the total quantum world to manifest and reveal itself within itself in a measurement. Thus in contrast to the classical notion of measurement, we should regard a quantum measurement as a manifesting process. How do we understand what happens when the human being perceives the classical world with its implication s, that may simultaneously manifest and reveal the quantum world-7? The first step is through the senses, which as far as physiological sciences now know can be explained classically. Sensory impulses are then carried into the BRN, and even here a great many processes have been studied which likewise can be understood classically. Most neuroscientists seem to believe, however, that the brain can be completely treated in terms of classical concepts. At present this is evidently a speculative assumption. However, some neuroscientists, notably Ecclesiastes 12, have suggested that quantum processes may be important in understanding the more subtle activities of the brain. For example, as has already been pointed out, we know that retinal cells respond to a few quanta at a time and that this response leads to a multiplication of their effects to a classical level of intensity. But the retina is just an extension of the brain. There could evidently be other parts of the brain in which such a sensitivity may exist, e.g. in certain kinds of synapses. If this were the case, then the brain would be a system that could, like a measuring apparatus, manifest and reveal aspects of the quantum world in the overall processes. Such quantum sensitivity would imply that in more subtle possibilities of behavior of the BRN, a classical analysis would break down. All this means that as the processes of perception unfolds into the brain, it may as it were connect to the subtle quantum domain, which latter may in turn reconnect to the classical domain, as outgoing action is determined through amplification of quantum effects. Moreover, it does not necessarily follow that quantum effects will only be of importance in the domain of very small energies. For as we have seen it is just through certain kinds of non locality that locality can emerge, e.g. in a measuring apparatus. Similar non-locality may be required for the brain to have a local and essentially classical subdomain of function. Finally, there is no reason to believe that quantum theory is an ultimate truth. Rather, like other theories, it probably has a limited domain of validity. Indeed, various authors including ourselves have already suggest new theories quanta in quantum theory as an approximation within it, and some of these will be discussed in chapter 1.5. Once again, it may well be that a fuller understanding of the brain will require more extensive theories going beyond the quantum mechanics. See chapter 9. The role of statistics in the ontological interpretation of the quantum theory. 9. 1. Introduction. In our interpretation, the primary significance of the wave function is that it is a quantum field which determines information that is active on the particles in each individual system. However, we also say that the wave function determines the probability density in a statistical ensemble through the relationship P equals LLLT12. But as already pointed out in chapter 3, section 3. 4. This is regarded as a secondary significance of the wave function. In principle, there is no reason why the probability could not be different from L11 TL2. Even THOUGET is equal to L11 TL2 in all cases that we have encountered so far. What we have to explain then is why P should tend to approach L11 TL2. In typical situations that are currently treated in physics, i.e. situations in which the quantum LAWs are valid. In this chapter we shall give such an explanation showing that once you understand how an arbitrary probability density, P, may approach L11 TL2 even on the basis of our deterministic theory, because the latter leads to chaotic motions under a wide range of conditions. We shall then show how the overall statistical approach may be generalized to include, not only what are usually called pure states, but also what are usually CALLED mixed states, which are at the basis of quantum statistical mechanics. Finally, we shall extend this study and show how the approach of P to 11,111 to could further be justified on the basis of an underlying stochastic process in the movement of the particles. 182 The undivided universe. 9.2 Chaotic behavior of particles in many body systems. We have already seen in chapter 8, section 8. 5 that even for a single particle, In a two-dimensional box, we obtain a fairly complex and chaotic motion. With n particles in a three-dimensional box, this will evidently become still more chaotic. To illustrate what happens in such cases, let us consider a cubic box of side L. However, instead of supposing that the walls are impenetrable, we shall make the more realistic assumption that the part ICLESCAN actual Ly touch the walls where THEY could interact with its constituent atoms. We shall not, however, treat these interactions in detail, but we shall merely suppose that, as in Chapter 8, Section 8. 4, they lead to a complex linear combination of stationary wave foo and setions. To simplify CALC-olations, WHICH. A dot RE intended to indicate what sort of thing may happen, we also assume that the wave functions are periodic with period L. For a single part Cle the basic eigenfunctions are exp(x)(z)(exp(I)(w)(kt) where kr equals 27rl/L, k equals 27rm/L, and k equals 27rn/L, and where wk equals k2/2m. For THEN particle system, THE eigenfunctions of THE energy are exp ilnknzn, where zn represents the position of the nth particle and kn is proportional to its momentum. The general wave function can then be written as 2 equals LCK, K, KN exp ILKNZN, exp IEWKT, 91, K1, K, KNN. For equivalent particles, the CS will have to be restricted to anti-asymmetric functions. But here we need not specify what is the symmetry, as this will be included in the values of C. The coefficients C can be very complex, for example I-enteric T-ion with the molecules constituting the walls may produce interfering combinations of wave packets which will involve a very wide range of possible values of K in the manner discussed in Chapter 8, Section 8.3. We may expect that, after the system has been left by itself for a long time, there will indeed be a linear combination. If we write P equals 11/12 and let V be the velocity of the STH particle, we get 1 PV equals 2-1/JV 1/J 1/J V 1/J me 9-2. This then gives the ROLE of statistics in the ontological interpretation 183. PV 2 LLCICL K plus K L L X EXP I KNXN K X EXP I1 WMW T 93, where CFI equals CI I N. It is clear that the above is built out of a very large number of terms, each of which oscillates with a phase that is in effect random relative to those of the others. The point in configuration space corresponding to Z1, Zn, moves in a chaotic way through all the configuration space that is accessible to it. Intuitively we could expect that for statistical averages, this motion would be equivalent to some kind of probability distribution in the configuration space. What would this probability distribution be? To inquire into this, we first note that the function P equals LF satisfies a conservation equation in configuration space, which is dP plus Vn pln equals 0 dTl 94 n. Of course this does not mean that P itself is necessarily The probability. We may therefore write this probability density as P equals Pf. By definition, P satisfies the SAME conservation equation as P. We then obtain 9.5. This means that F is a constant OF the motion. Suppose for example that we started with a distribution which was localized in an element of configuration space n equals z1, z2, zn. This element is chosen to be small relative to macroscopic dimensions, but large in relation to the wavelengths implied by a typical k vector. Because F is a constant of the motion, we can see what trajectories to the element n by following the various particle trajectories on its boundaries. Consider for example two trajectories in initially separated by bz. These will correspond to large phase differences between most of the contributions to the velocity in equation 9.3. Therefore the two trajectories will correspond to very different quasi-random paths that will in general lead them very far from each other. It follows that a simple element n will turn in to a very complex, long drawn out and enmeshed 184 the undivided universe. Given Po int in configuration space, it also follows that in the sense of a coarse-grained average, this thread-like structure will move in such a way. Thread-like structure. Because any trajectory eventually comes near to any as to more or less cover the whole of this space. Therefore in any process that does not depend on the complex and chaotic fine details of the motion, F may be taken as effectively a constant. In such a process we may say the probability is effectively P equals LIP12. There are a very wide range of conditions in which the sort of process described above may take place. These include metals, gases, plasmas etc. So at not only in the laboratory, but also in the stars and interstellar space, we may reasonably expect that quantum theory itself contains processes that tend to produce distributions near P equals LIP12. Therefore it is not necessary to regard P equals LT/12 as an assumption as is done in conventional interpretation. Although our interpretation H as the additional assumption of particles, this is balanced by the fact that it does not require the usual assumptions on probability. So at least on the basis of a formal count of the number of assumption S, we can not say that either interpretation is favored over the other by the principle of a cam-s razor. It is instructive at this point to consider once again our example of electrons emerging from a metal and going through a set of collimating G slits and velocity selectors to enter a slit system in an interference experiment. 2. Simplify the discussion. Suppose we have cold emission of electrons brought about by a strong electric field near the surface of the metal. This combined with the wave function gives rise to a barrier of phi n with which CANBE penetrated. The wave function, 9.1, implies that electrons are constantly striking this barrier and a small part of the wave function penetrates as explained in Chapter 5, Section 5. 1. Some electrons will go rough if their initial conditions are right. If an electron does go through, its wave function can then be regarded as simply the part that has penetrated, multiplied by the wave function of the metal containing the remaining electrons. It is therefore factorized so that the metal and the electrons behave independently from this point on. Let us now consider an ensemble of cases in which electrons have left the metal in the way described above. There will be a distribution of electrons, each of which has its own wave function and its own initial position. Because The electrons are independent of each other and of the metal, we see A and follow the propagation of each of their wave functions according to Schrödinger's equation for a one-body system. This implies that they will move onward and pass through the collimator and velocity selector. When they have done this, all the electrons will have wave functions of practically the same form. Because the distribution P equals LIPL2 is also propagated by Schrödinger's equation, it follows that our statistical ensemble of electrons will enter the role of statistics in the ONTOL logical interpretation 185 slit system with the probability P equals LIPL2, where 1/I is the common wave function of all these electrons. In this way we understand how the ordinary probability distributions arise through the chaotic motions of the particles I and their source, and rough the selection of a common wave function by the apparatus that prepares the experimental ensemble. 9. 3 Statistics of wave functions. In the previous section we have discussed a case in which electrons were selected so that they all have the same wave function. This corresponds to what has commonly been called a pure state. But Th's state is still a statistical distribution, since it refers to an ensemble of particles with different positions even though they have wave functions of the same form. But is it actually appropriate to call this ensemble a stat-E? For this word generally connotes some property of an individual system rather than of a selected collection of systems. In the interests of clarity it would perhaps be better to call this collection of particles a pure ensemble rather than a pure state. Suppose, however, that we have a situation in which electrons are selected by a procedure that does not determine the wave function very precisely. E.g., the collimating slits are wide and the velocity selectors permit a large range of velocities to go through. In this case the wave function itself will in general be significantly different for each particle. In terms of for example of electrons coming out of a metal, we can see th at the wave function in the metal contains effectively a random distribution of eigenfunctions of the total energy. Electrons will therefore emerge with some statistical distribution of wave functions, as well as of particle positions. This will correspond to what is commonly called a mixed state, although we shall, in accordance with our proposed terminology, call it a mixed ensemble. The distinction between pure and mixed ensembles early applies only in a statistical context. An individual system is described neither by a pure nor by a mixed ensemble. Rather it is characterized by specifying the wave function and the positions of all the particles in the system, as well as values of the relevant field variables. Thus, for example, the state of the universe has to be understood in this way because we are not assuming an ensemble of universes. Any quantum experiment always involves a statistical selection of similar subsystems within the universe. Such a selection will give rise, in the way just described, either to a pure or to a mixed ensemble. More generally, under certain conditions a similar selection might even take place natu rally. So THAT, for example, a set of portions of an interstellar plasma might be E186 the undivided universe, treated in terms of suitable mixed ensembles. Our basic concept is, however, THAT for each member of the ensemble the wave function has some definite form to which we see and apply our interpretation of the quantum theory in the usual way. Until now we have been discussing in this book only the CSE of a pure ensemble for which a guess are calculated by integrating the probability density P equals LTIW over A point to the particle positions. However, in a mixed ensemble, the wave function is dis. Tribute over a range of possible forms. The statistical properties of such an ensemble will have to be calculated by averaging over the distribution of wave functions, in addition to averaging over the particle positions for each wave function. The general wave function may be represented by an expression in terms of an orthonormal basis which, for convenience, we shall take to be eigen functions of the energy. In the previous section we did this for free particles in a box, and the wave function was given by equation 9.1. More generally, we may write 111 equals LCEAL slash EA, X, EA, where EI is the energy and A runs over all THE states WITH same energy. Any individual system must have a wave function described by a particular set of values of CEA. It will be useful also to write 9.6. So that 111 equals LREAEXPI cent EAL slash EA, X. 9.7. EA. If we have an ensemble of wave functions, there will have to be a corresponding probability distribution of the REA and the cent EA to describe. This distribution we shall introduce the concept of wave function space. A point in wave function space is determined by all the CEA, or alternatively, by all the REA and cent EA. Each individual system then corresponds to a point in wave function space. Let us now define the element of volume in wave function space. Writing CEA equals UEA plus 4EA, we obtain for this element dq equals TIDUEA dVEA. EA. Do equals TIDPD cent EA. EA. 9/8. 9/9. The ROLE of statistics I and the ontological INTERP re TATION 187. The mean number, dz, of systems in this element is then dz equals p REA cent EA LR2 910, where p REA cent EA is the probability density of systems in wave function space. For a given wave function TF, physical averages will evidently be determined by quantities such as 0 equals JTF, OTF, dx equals JLLC pound 101 CEA, 1 slash 101 pounds 01 slash EA, dx. E1E, A. 9.11. If we have a statistical distribution of wave functions, we evidently have to average over this ensemble TOO. We then obtain 9.12. Let us define 9.13 and 9.14. We then obtain 0 equals TR, Po. 9.15. From THISIT follows that P is the usual density matrix since all averages are obtained from it in the usual way. All that we have said holds both in our interpretation and in the conventional interpretation. For thus far we have not used the assumption of a definite particle position. In both interpretations pH has only an essentially statistical significance. We have to emphasize, however, that in our interpretation the particle velocity in each individual C as E is determined by the actual wave function for this case, which is 111 equals LCE slash JEA, Z. Writing P, Z, equals LL CF, 0 CEO1 slash E0, Z, IJJE, Z. We obtain the following expression FOR the momentum P, Z, at the point Z, where LJ, EO, Z, equals XEO EXPIA EO, Z. Clearly the momentum for EACH case depends on all the coefficients CEA, which determine the wave function for that. Ka-E. The probability density. P. REA. Cent EA. Then evidently implies some corresponding distribution over the momenta P, Z. If we carry out this average we will obtain the average momentum density. PEAEA will therefore give only a statistical average of the momentum over the various wave function coefficient Ts. Although the density matrix is sufficient to determine, not only the average of the moment but all relevant physical averages over the ensemble. It evidently does not determine the probability distribution P. REA. Cent EA. itself. That is to say, physical averages are extremely insensitive to the detail of the distribution P. Indeed it is clear that to a given density matrix, a very wide range of such distributions is possible. Therefore within the framework of the statistical mechanics of quantum theory, the function P is highly ambiguous. Yet conceptually it is, in principle, determined for each ensemble. It is true that in doing any calculations, it is not necessary to say anything about P over and above what is said about the density matrix. Yet both in the conventional interpretation and in our interpretation, conceptual clarity requires the notion of a probability distribution in wave function space. In our interpretation, this is clearly needed because we have to suppose the wave function has a given form 1jj equals re is. Be4 we see and say what is the particle velocity. V equals vs/m. We then consider a statistical distribution of such forms. In the usual interpretation the basic postulate also begins with the wave function and the density matrix is derived from THIS. The density matrix is not a fundamental concept in any of the interpretations of the quantum theory. Some, such as Prigogine 1 and Hooking 2, have proposed new theories which are extensions of quantum mechanics in which the density matrix does play a fundamental role. To illustrate the ambiguity of the statistical distributions unde relying the density matrix, let us consider an atom of total angular momentum. The role of statistics in the ontological interpretation 189. H. In the z direction, for example the three possible eigenfunctions of the angular momentum will be denoted by Lj, J, Z, with J equals 1, 0, plus L. The general wave function may be written as 916. The probability distribution in wave function space can then be written as P. Rj. Cent I. The density matrix is then P, Z, Z, equals JL. P. R, slash. RJ RKEI, cent, 1J. J, Z, IJ. K, Z, MT. JK. 917. If P does not depend on cent, THIS signifies random phases. In THIS case THE density matrix reduces to P, Z, Z, JLP. R. RJIJJ, Z, IJ. J, Z, DO. J. LRJIJ. J, Z, IJ. J, Z. 918. THIS is evidently diago NAL in THE angular momentum quantum numbers. J. If we further assume METHAT the distribution is a symmetric function of Ri. All the RWILLBTHE same and the density matrix will be 919. A very wide range OFP. Ri, Can evidently lead TOTHE above density matrix. This matrix H has an isotropic significance because it takes the same form even if we choose our z-axis in some other direction. This means that the distribution of angular momenta obtained in a measurement will be E. Independent OFTHE orientation OFTHE apparatus. BUT from TH is distribution. We see A not even say that the original P RJ is necessarily isotropic, since, as we have seen, THSA results follow merely from the symmetry under interchange of any PAIR of variables Rj and R1c. More general ly it is evident that from the observable distribution of the results of measurement Ts, we can say very little about the details of the distribution over the Rj. To further bring out the ambiguity of the P R1 SUPPOSETHAT, we had THREE ensembles in each of which the z component of the angle AR momentum was WELL defined to be E, 1, 0, plus 1, respectively. If these are mixed with equiprobability, THIS will give rise to the diagonal density matrix, 9.19. But suppose the mixed ensemble was formed by having a secant, .E in which 190 the undivided universe plus 1 is always followed by 0 and this by 1, which in turn is followed by plus 1, and so on. The mixed ensemble LD still imp ly isotropic averages. So THAT and experimenter LD obtain the same statistical distribution no matter in which direction he measured the spin. Yet if he chose to measure only every third member of the ensemble, he would obtain a non-isotropic result corresponding to a spin in the z direction of plus 1, 0 or 1. BUTTHE. Density matrix itself FORTHE mixed ensemble. Does NOT show any sign OF such a possibility? It is thus THAT many different physical situations may give rise to the same density matrix for the same overall ensemble. Even if the various sub-ensembles are chosen by a random process, this may still hold. For example, one could use a random NUM-BER generator to determine which of the above three sub-ensembles are chosen to be fed into the mixed ensemble. An experimenter who knew the order determined by the random number generator could then obtain a non-isotropic result for THE measurements OFTHE angular momentum. Of course in natural situation NS, we see ANNOT know how such a random selection occurs, and in such cases we will always obtain an isotropic result. But this does not change the fact that a given density matrix leaves open a vast range of physical states THAT could give rise to it. There may be yet are there ambiguities in the physical state underlying the density matrix. Thus in many cases, our ensembles have come from Lagrange systems, such as, for example, the electrons emerging from a metal. In principle there may still be correlations of one kind or another between the electrons of interest and those left in the metal. To be accurate, we should therefore be ASER considerations on the larger system containing both of these. Hence we show ULD start with the probability distribution over the wave function coefficients of the combined system to form a corresponding density mat Rix for this combined system. We may write this as P, Z, 11, Z, 11, where 11 represents the coordinates of electrons left in the metal. As long as we are concerned only with those electrons that have emerged from the meta L, we can simplify the tree Tm by integrating over the coordinates of the electrons THAT are left in the met L, while equating Y with Ti. This will give us a reduced density matrix P, Z, Z, from which the statistical properties of the electrons THAVE left the metal can be calculated. This sort of density matrix H has, for example, been used by Feynman 3. As we have already indicated, the original density matrix may contain correlations of all kinds, including, for example, EPR correlations, but THSA no longer appear explicitly in the reduced density matrix, although their effects are indirectly taken into account. The role of statistics in the ontological INTERP re TATION 191. 9.4 The density matrix as determining all the physically significant results. We emphasize then that the density matrix, in general, contains a condensation of IN formation in which most of the details of the individual system do not appear, but which contains JUSTTHATIN formation which is relevant statistically. In particular, the density matrix determines not only the statistics of all processes of measurement and of all processes of transition in general, but also that of large-scale manifestations of the micro-level, and ultimately all collective large-scale averages, the latter being the basis of the description of the manifest world discussed in Chapter 8. Firstly, we see from equation 915, THAT the density matrix determines the statistical results of all measurements. To show how it determines the statistics of transition processes, let us, for example, once again consider the C as E of cold emission from a metal through barrier penetration. This will, in general, give rise to a mixed ensemble described by a pseudo BLE density matrix in the manner that we have described earlier. With the aid of further selection processes through collimating slits etc. We see an, of course, approach as close as we please to a pure ensemble. Each individual MEM burr of the mixed ensemble corresponds to a well-defined wave foo NCT ion, 1/j. With a further ensemble of P vertice positions P equals 1/j12. For such a wave function, the probability of transition can be obtained by integrating the part of LL/JL2 corresponding to phi NAL state over the PA RTICLE positions. We then have to integrate this over the distribut ion of wave foo NCT ions. The phi NAL result will then be the same as that obtained by starting with the INI density mat RIX and integrating the trace of THE phi NAL matrix over the ensemble CO respond ing to the phi NAL set of possible results of the TRNZ ion process. Another important physical significance of the quantum theory is that IT determines probabilities of large-scale manifestations of microcyst MS. We have already given an example of this in Chapter 6, where we discussed an ion chamber in which a single atom could initiate AC as Ca to lead ding to a current of macroscopic magnitude. Such a process depends on an unstable situation created by the electric field which allowed the cascade to develop and eventually produce a large-scale result. But this sort of process does not require an observing apparatus or any other set of condit ions arranged by human beings. For example, in an interstellar plasma air could be a strong electric field in which individual electrons could initiate such cascades. In all these C as ES, the probability of any given fluid distribution of the macroscopic currents would depend ultimately on the ensemble of p-article positions in the atoms and the ensemble of wave functions of these. 192 The TRNDL11 LDID UNL11 ERZ atoms. However, THIS dependence is SUCHTHAT. The NET statistical result. QLDLWIs be obtained from the density matrix IN the usual way. Let us NOW come to the large-scale averages of the collective variables themselves. As we HAVE already pointed out, the variables will include the energy, momentum, and angular momentum of the whole system and of its relevant subsystems, as well as certain collective Foo NCT ions of the position. SUCH as center of mass and FOUR coefficients of the particle density WHICH. Describe sound waves. Typica LLY at the large scale level, systems will be CLOs to stationary STATES. It will therefore be convenient to express wave functions in terms of eigenfunctions of the energy, 1/JEA, Z. We begin with a pure ensemble. The general wave function for such an ensemble is THN. The mean value of the energy is 920. But a typical large-scale system has to be described by a mixed ensemble, e.g. because it is generally abstracted from a larger context in the way that we have already discussed. Let the probability distribution of wave functions in this mixed ensemble be P. Re. Cent Ea. The density matrix will THN be PEA J. P. Re. Cent Ea. X Rea Re. A. Ei. Cent Ea. Ea. LEI, WEO, WE, T, DO, 921. In general THIS density matrix is diagonal as a function of E, because the phases will be random. We may always choose a representation in which is also diagonal in terms OFA and A. We therefore write. We THN obtain. PEA equals P6, E, 6, A, TR, PE, LEPEAE, A. 9.22. 923. To illustrate how such averages determine physical properties, let us consider a collection of particles in a box constituting a perfect gas, as SUMI and G periodicbo under conditions for convenience. The general wave function for such a system is given by equation 9.1. The role of statistics in the ontological interpretation 193. A typical eigenfunktion of the energy is expilnknzn. The energy corresponding to this eigenfunction is E equals L5 underscore 2m. For a given particle, kx equals 27rl/l, ky equals 27rm/l and k equals 27rn/l. We can apply the above TOC calculate the pressure INABOX, which is with V equals L3, we HAVE equals 8E OL equals 8E V 2/3 PLAV 3OL 924. As THEBOX expands, THE energy decreases, and a simple calculation shows that P equals E 9.25, where E is determined from the density matrix as TR, PE. THE above SHOW typically CAL macroscopic properties WILL follow from the density matrix. For the C as E of EWE do not need to know the precise form of the density matrix to obtain the relationship between P and E that we HAVE JUSTC calculated. But more generally to TREAT thermal properties, we need a more detailed knowledge of P. It is well known THAT for thermodynamic equilibor IUM, P is proportional to E, E/JT underscore if WE right. 926. Where 1 slash is THE normalization factor FORP, WE get 1 slash J equals KTLNZ, 927. WH air, 928. In THE well-known way WECAN up to IN all THE thermodynamic averages from the free energy 1 slash. The problem OFJ justifying that in a state OF thermodynamical equilibrium, Rho M, PXE, E slash KT, is essentially the same in our I interpretation as it is in the conventional interpretation. Various treatments of this problem have already been given. See, for example, Tolman 4. However, in this book 194 TUTM addressed UNI verse. It is not our main purpose to discuss quantum statistical mechanics, but rather to focus on the fact that an ontological interpretation of the basic quantum theory is possible. What we have done in this section is to show the general lines along which one can include quantum statistical mechanics within the framework of our approach. 9.5 The stochastic explanation of quantum probabilities. We have thus far been explaining quantum probabilities in terms of chaotic motions that are implied by the quantum laws themselves, with pure n symbols representing chaotic motions of the particles and mixed ensembles, bringing in also chaotic variations in the quantum phi LD. Whenever we have statistical distributions of this kind, however, it is always possible that these chaotic motions do not originate in the level under investigation, but rather that they arise from some deeper level. For example, in Brownian motion, small bodies which may contain many molecules undergo chaotic velocity fluctuations as a result of impacts originating at a phi NER molecular level. If we abstract these chaotic motions A and D, consider them apart from their possible causes, we have what is called a stochastic process, which is treated in terms of a well-defined mathematical theory. 5. We can have two date to such a stochastic process. The first is that it is a result of deeper causes that do not appear at the level UNDER discussion. The second is that there is some intrinsic randomness in the basic motions themselves. And so far as we apply the ordinary mathematical treatment, we need not commit ourselves to either attitude. But of course, if we are thinking of possible models for the process, then our attitude may make a difference, because the assumption of deeper causes implies the stochastic treatment will break down at the finer level at which these causes are operating. We shall discuss this possibility in Chapter 1.4. A stochastic explanation of the quantum theory along these lines was first suggested by Bohm and de Vigier, 6, who proposed a subquantum mechanical level which would bring about chaotic behavior of the particles. Later a similar theory was proposed by Nelson, 7, which, however, had certain important differences which we have discussed in detail in a subsequent paper, Bohm and hilley. The basic assumption of Bohm and Vigier is that the velocity of an individual particle I is given by Vs, x, v, j equals 1 plus I, t, 929, m, where I, t, represents a chaotic contribution to the velocity of that particle, which fluctuates in a way that may be represented as random but with zero. The role of statistics in the ontological interpretation 195. Average. This means that in the causal form of ontological interpretation that we have given thus far, we should regard vis, xi/m as the average velocity of the particle I rather than as its actual velocity. It is through this average velocity the quantum potential comes in. For as we have Shown in CHA PTER3, if the average velocity v s x m 9.30 and if ijj equals rxpis, then Schrodinger's equation implies that dv dt equals v plus q 931. The stochastic process simply adds the random motion t, so that dvi equals v vq dt dti plus dt 932. However, as WESH all see, in THAT branch OF mathematics known as stochastic theory, it is not necessary to use explicitly the above expression for the acceleration, and it will be sufficient to start with equa ti on 929, from which equation 932 follows in the way described above. WHAT stochastic theory typically does is to be begin with a statistical n symbol of p articles which are assumed to have some probability distribution given by p, x, t. In such a theory, the notion of probability that is used is entirely classical and has nothing whatsoever to do with the quantum mechanical subtleties involved in the uncertainty principle and in the LAPSE of the wave function in the conventional interpretations of quantum theory. What we want to do here is to begin by assuming that our probabilities likewise have no intrinsic relation to the wave function, and that they are simple classical-like probabilities in the kind of ensemble that is treated so widely by standard stochastic theory. However, our aim in doing this is to determine the properties of the random motions described by t, so that an arbitrary initial ensemble with a probability distribution p, z, t, will approach an ensemble with a probability distribution p, z, t, equals p, z, t, equals 1 1 slash, z, t, L2 after a suitable interval of time. We then suppose that under typical conditions obtaining in quantum mechanical measurements, the interval of time will have been long enough so that the probability distribution will be given by 1 1 slash, z, t, slash 2. In this way we understand the fact that while p, z, t, and L it, z, t, L2 are basically independent concepts, THEIR numerical values will experimentally turn out to be equal in quantum mechanical experiment S. In addition, of course, the chaotic 1/9/6 undivided universe processes occurring at the quantum level independently of the stochastic process which we have already discussed in this chapter will then contribute further to bringing this result abuti 9. 6. Detailed mathematical treatment of the stochastic model. To make a detailed treatment of the stochastic process, we shall assume that, whatever its origin may be, it can be represented as simple diffusion. To illustrate what this means, we shall first consider a classical context in which we treat the diffusion of and motion particles in a gravitational field using the simple theory of Einstein. If P is the probability density of particles, then there is a diffusion rand J, D, equals, dVp, 9.33, where D is the diffusion coefficient. If this were all there was, the conservation equation would be up equals, dV2p at, 9.34. And clearly this would lead to a uniform equilibrium distribution. However, as Einstein showed, in a gravitational field in the z direction there is what he called an osmotic velocity. The conservation equation then becomes up mg at equals dv kt zp plus vp. For the equilibrium distribution, up/ot equals 0, so that Vp mg equals z plus const pkt, or, which is the well-known Boltzmann factor, p equals ae mgz slash kt, 9.35, 9.36, 9.37. The picture implied by the Einstein model of diffusion is that the particle is drifting downward in the gravitational field and that the net upward diffusive movement balances this to produce equilibrium. It is worthwhile to provide a still more detailed picture of this process. To do this, let us consider a simple one-dimensional model in which there is a unique free path A and a unique speed v. We assume further that after the role of statistics I and the ontological interpretation 197 collisions, the velocities are randomly distribute in positive and negative IVE directions while the speed is still v. Let us now consider two layers which are separated by backslash. The net diffusion current between thsa layers will be j d equals p underscore p underscore colon up 21 z 2 ounces a 9.38. Between collisions, the average velocity gained from the gravitational field ISG backslash UO equals 2v. The above is evidently the osmotic velocity. The total current is J equals underscore F underscore P underscore colon up backslash equals underscore backslash V J underscore P plus up 2v 2 ounces 2v 2 oz. Writing v2 equals kt slash m and d equals v backslash slash 2, we have J equals d p plus mg up kto and this is just the equation that Einstein assumed. 939. 9.40. It is important to emphasize that, at least in Th's case, The osmotic velocity is produced by a field of force. Without such a field, there would be no reason for an osmotic velocity. For the stochastic interpretation of the quantum theory, we would like to have a random diffusion process whose equilibrium state corresponds to a probability density P equals Li PL2 equals P and to a mean current J equals PV equals P, Vs slash M. Such a state is a consistent possibility if 1J equals .Jps slash satisfies Schrödinger's equation, because this implies the conservation equation. In order to have EP equals LIPL2 as an equilibrium density under such a random process, we will have to assume a suitable osmotic velocity. We do not have to suppose, however, that THIS osmotic velocity is necessarily produced by a force field, similar to that of the gravitational field in our example given above, but rather, as we have already indicated, it may have quite different causes. Thus, as suggested by Nelson, 9, it could be some kind of background field THAT would produce a systematic drift as well as a random component of the motion. At this stage it will be sufficient simply to postulate a field of osmotic velocities, UA, Z, T, without committing ourselves. 198 The undivided UN for ERSE. As to WHAT is its orig in. We therefore assume an osmotic velocity dVp UO equals P and a diffusion current J D equals dVp. The total current will be P dVp. J equals Vs plus dVp MP. The conservation equation is then up VSVP plus Vp plus dP, dVp equals 0, and T MP In the above equations there is a systematic velocity. VSVP. V equals plus d mp 9.41, 9.42, 9.43, 9.44, 9.45. This is made up of two parts, the mean velocity v equals vs/m and the osmot ic. Velocity u0 equals dvp/p, the mean velocity v may be thought to arise from de Broglie-Idance condition. As we have just explained, the osmotic velocity will arise from some OTHER source such as a field, but the mod in point is that it is derivable from a potential d in P where P is a solution of the conservation equation. 946. It follows from equation 9.44, that there is an equilibrium state with P equals PINWHH. The osmotic velocity is balanced by the diffusion current so that the mean velocity is V equals Vs/m. But now we must raise the crucial question as to whether THIS equilibrium is stable. In other words, will an arbitrary distribution P always approach P? Writing P equals Fp we obtain the following equation. JF fit equals dV, PVF equals dVp, VF plus dPV. 2. Y, 9.47. We shall show that F must eventually approach L everywhere by proving that the maxima of F must always decrease and the minima must always. The role of statistics M. The ontological interpretation 199. Increase. Maxima and minima are characterized by Vf equals 0. At SUCH points we have AF2 P at equals dPVF 9.48 ATA maximum V 2. F is negative and clearly F must be decreasing at this point. At a minimum V 2. F is positive and therefore F must be increasing. This can only cease when F equals 1 everywhere. For time is much longer tha and the relaxation time, r, of this process we will therefore quite generally encounter the usual quantum mechanical probability distribution. It is implied, of course, that at shorter times this need not be so and therefore the possibility of a test to distinguish THIS theory from the quantum theory is in principle opened up. We shall discuss the conditions under which such a test may be possible in Chapter 1.4. The mean velocity is, of course, V equals Vs/m. As we have seen in connection with equation 931, this by itself does not determine the acceleration. In addition we need a differential equation for s. Then as we have seen in Chapter 3 and also earlier in the present section, provided 1/s satisfies the Schrödinger equation, S will satisfy the extended Hamilton-Jacobi equation 3.7, which contains the quantum potential. It is thus clear that in the present approach, the quantum potential is actually playing a secondary role and THIS is indeed why it does not have to be included explicitly in the stochastic approach, though it provides a very useful insight into the meaning of the process especially in the non-stochastic approach. But in all cases the fundamental dynamics depend first of all on the guidance condition, and, in a stochastic theory, we bring in also the osmotic velocity and the effects of random diffusion. All these work together to keep a particle in a region in which P equals 1/1/JL2 is large and where its average velocity FLUC twaits around Vs/m. As explained earlier, the quantum potential merely represents the mean self-acceleration of the particle under the influence of the de Broglie guidance conditions, and this will be valid only if I/satisfies Schrödinger's equation. If I/had satisfied another wave equation, the mean accelerations would have been different. In fact, we shall extend this theory in chapter 12 so that the wave function satisfies the Dirac equation, for which a very different mean acceleration is implied. To bring out the physical significance of the stochastic model, let us consider the two-slit interference experiment. A particle undergoing random motion will go through one slit or the other, but it is affected by the Schrödinger field coming from both slits. In the interpretation that we gave earlier, THIS effect was expressed primarily through the quantum potential. In the stochastic interpretation it is primarily expressed through the osmotic velocity, which reflects the contributions to the wave function. 200 the undivided universe v coming from both slits. Near the zeros of the wave function the osmotic velocity approaches infinity and is directed away from the zero s. Thus a particle diff using randomly an approaching a zero is certain to be turned around before itcan reach this zero. This explains why no particle ever reaches the points where the wave function is zero. And, as we have indeed already pointed out, the osmotic velocity is constantly pushing the particle to the regions of highest/sense/2. And this explains why most particles are found near the maxima of the wave function. With OUT assuming an osmotic velocity field of this kind, there will be no way of explaining such phenomena as a result of random motions. For example, a particle undergoing a random process on its own while dhave no way of knowing that it should avoid the zeros of the wave function. To obtain a consistent overall picture we must consider the random background field. This is assumed, as we have already pointed out, to be the source of the random motions of the particle, but in addition it must determine a condition in space which gives rise to the osmotic velocity. Indeed, a single particle in random motion cannot contain any information capable of determining, for example, that every time it approaches the zero of a wave function it must turn around. This information could be contained only in the background field itself. Therefore, the stochastic model does not fulfill the expectations that while d at first be raised by its name, that is to provide an explanation solely in terms of the random movements of a particle without reference to a quantum mechanical field, which may be taken as P and SOR as cent equals /PS/Li. And the interpretation that we have been giving throughout THIS book. This field H as the property that ITS effect does not depend on its amplitude. As we have suggested in earlier chapters, this behavior can be understood in terms of the concept of active information, i.e. that the movement comes from the particle itself, which is however informed or guided by the field. In the stochastic interpretation there is a further effect of the quantum field through the osmotic velocity, which is also independent of its amplitude. We can therefore say that along with the mean velocity field, Vs/m, the osmotic velocity field constitutes active information which determines the average movement of the particle. This latter is however modified by a completely random component due to the fluctuations of the background field. Clearly there are basic similarities between our original essentially causal interpretation and the stochastic interpretation. Nevertheless, there are also evidently important differences. One of the key differences can be seen by considering a stationary state with S equals const. E, G, and S state. In the stochastic model, the particle is executing a random motion which would bring about diffusion in space, but the osmotic velocity is constantly. The role of statistics in the ontological interpretation 21. Drawing it back so that we obtain the usual spherical distribution as an average. But now the basic process is one of dynamic equilibrium. The average velocity, which is 0, is the same as the actual velocity in the causal interpretation. Such a view of the S state as one of dynamic equilibrium seems to fit in with our physical intuition better than one in which the p-article is at rest. 9. 7. Stochastic treatment of the many-body system. The extension of this model to the many-particle system is straightforward. The wave function, t/x, r, which is defined in a 3-dimensional configuration space, satisfies the many-body Schrödinger equation. We assume that the mean velocity of the nth p-article is 1a. Ti, n equals 8x s x r min. 949. In addition we assume an arbitrary probability density p, x, r, and a random diffusion current of the nth particle d underscore d8p j n a xin. 9.50. We then make the further key assumption that the osmotic velocity component of the n1h particle is where p equals /1/2 u o equals d 8p in p8x n. 951. From here on the theory will go through as in the 1p article case, and it will follow that the limiting distribution will be p equals /1/2. Equation 950 describes a stochastic process in which the different particles undergo statistically independent random fluctuations. However, in equation 951, we have introduced an important connection between the osmotic velocities of different particles. For the general wave function that does not split into independent factors, the osmotic velocities of different particles will be related, and this relationship may be quite strong, even though the particles are distant from each other. For this model requires an effectively instantaneous non-local connection which brings about the related osmotic velocities of distant particles, accord ing to mvn equals vn, v plus q. 202. The 1m divided universe. It is clear then that the stochastic approach brings in yet another kind of non-locality over and above that which is present in the causal interpretation, in which, as we have seen in chapters 3 and 4, the acceleration is given by mvn equals vn, v plus q, and q is the generally non-local quantum potential. However, by its very name, the stochastic approach seems to imply a theory in which quantum mechanics could be explained in terms of particles undergoing random processes, and thus one could easily be led to expect that at least in this theory there would be no need for non-locality. For example, Nelson, 9, who has worked intensively on Th's sort of interpretation, has written, but the whole point of the stochastic theory was to construct a physically realistic picture of microprocesses, and a theory that violates locality is untenable. 10. From this it is clear that Nelson expected the stochastic theory to be local, even though he phi nallyc to the conclusion, in agreement with us, that it has to be non-local. To bring out the full meaning of this non-locality, it is useful to discuss the Einstein-Podolsky-Rosen experiment in terms of the stochastic interpretation. To do this we first recall THAT, as shown in Chapter 7, the essential feature of a measurement process is that the p-articles constituting the measuring apparatus can be shown to enter a definite channel, and THAT after this they cannot leave the cha NNL in question because the wave function is zero between the cha NNLs. From this point on the wave function of the whole system effectively reduces to a product of the wave function of the apparatus and of the observed system. It W as demonstrated that thereafter the remaining empty channels will not be effective. It follows that the net result is the same as if there had been a co-LLAPSE of the wave function to a state corresponding to the result of the ACTUAL measurement. It is clear that a similar result will follow for the stochastic interpreted T-ion. Because here too there is no probability that a particle can enter the region between the channels in which the wave function is zero. Let us now consider the EPR experiment in the stochastic I interpretation. We recall that in this experiment we have to deal with an initial state of APAIR of particles in which the wave function is not factory-sably. A measurement is then made determining the state of one of these particles, and it is inferred from the quantum mechanics that the other will go in to a corresponding state even though the H Hamiltonian contains no interaction terms that could account for THIS. In the usual interpretation the behavior of the second p-article was explained by the non-local features of the quantum potential which could provide for a direct interaction between the two different p-articles that does not necessarily fall off with their separation A and D that can be effective even when there are no interaction terms. In the Hamiltonian, as we have seen in connection with equation 931, in the stochastic, the role of statistics in the ontological interp re TATION 203 interpretation all the above non-local effects of the quantum potential are still implied, but now we have seen that there is also a further non-local connection through the osmotic velocities. And when the properties of the first particle are measured the osmotic velocities of both will be instantaneously affected in such a way as to help bring about the appropriate correlations of the results. It is clear that the stochastic interpretation and the causal interpretation treat the non-local EPR correlations in a basically similar way. The ascent IAL point is that in an independent disturbance of one of the particles, the fields acting on the other particle, osmotic velocities and quantum potential respond instantaneously even when THE particles are far apart. It is as if the two particles WERP, in instantaneous two-way communication exchanging active information THAT enables each particle to know W what has happened to the other and to respond accordingly. Of course, in a non-relativistic theory it is consistent to assume such instantaneous connections. We shall, however, sh later how these side rations can be extended to take into account the fact that the theory of relativity has been found to be valid in a very broad context. See chapter 10. The ontological interpreted TION of the Pauli equation. 10. 1 Introduction. We have thus far developed a systematic ontological interpretation of non-relativistic Schrödinger theory for p-articles. In THIS and the next two chapters of the book, we shall be concerned principally with extensions of THE theory to include the non-relativistic Pauli equation field theories considered non-relativistically, relativistic treatment of both particle and field theories. We begin this chapter with the treatment of the non-relativistic Pauli equation. Firstly, we shall discuss some previous suggestions for an ontological interpretation of this equation based on the idea that the particle is An extended rigid object WHICH makes a spin contribution to the total angular momentum 1-2. We then give reasons showing why THIS assumption does not give rise to a satisfactory theory. We are led instead to regard the Pauli equation as a non-relativistic limit of the Dirac equation. When we do THIS, we see ANCTHAT in addition to the straightforward contribution to the current implied by the previous models, cf equation 5-4, there is a further circulating current in WHICH the or by T parentheses in a way that depends on the wave function. This makes a contribution to the total angular momentum, which accounts for that WHICH has usually been attributed to the particle's spin. This means that the spin angular momentum does not arise from an extended p-article structure at all, but that rather it is a further and more subtle feature of the orbital motion of the particle. The ontological interpretation of The Pauli equation 205. It is thus implied that the spin is a context-dependent property of The particle, rather than an intrinsic property. As such it is, as we shalic, readily related to a model originally proposed by Bell 3. We develop our model and exhibit its consequences for a variety of typical situations. We then extend it to a many-body system to provide an explanation of the EPR experiment with two atoms of spin1H alpha, constituting a molecule of total spin 0, thus extending the results of Chapter 7 for particles of spin 1, 10, to the bohm, Schiller and Chiamno model. We now give a sketch of the original Bohm, Schiller, and Chiamno model. BST, for spin 1. We shall give some reasons why we regard this model as ultimately inadequate, but it is nevertheless useful to consider it here as it will help make clear the model that we are actually going to adopt. We begin with the Pauli spinor X equals, which satisfies the Pauli equation /Ni equals y iea 2 ip plus v I j plus u b 1 at 2 mji 101, where R are the Pauli spin matrices, A the vector potential and B the applied magnetic field. We shall put H equals C equals 1 throughout this chapter. To develop this interpretation, we start with the special C as E where A equals 0 and B equals 0. In this case the Pauli equation reduces to two uncoupled Schrödinger equations. It is readily seen that when B is 0, the equations will generally be coupled. Then setting I, J1 equals RJEXP, is J, we obtain and ACI plus, YSJ, 2 plus V, underscore underscore 1, Y2 RJ equals O at 2M2 MRI, ARJ plus Y, R2, Ys, J, equals 0, at JM, 102, 103. We can picture THE meaning OF the above therefore as two independent probability distributions, each of which is conserved and in which the VE loci of the particle are, in general, different. When Bj0, neither of 206 the undivided universe. These probability distributions is conserved by itself BECA use the two wave functions are co-up-led. However, it is easily shown that their sum 104 is conserved. We may then define a mean velocity 10.5, where p1 equals 1 cent 112 and p2 equals 1 cent 212. The conservation equation is then p fit plus \7 pv equals 0. 106. On this basis we can say that the first step in obtaining an ontological interpretation is to assume a particle following a definite trajectory with the guidance condition, 105, which is clearly a generalization of the guidance condition for a particle without spin. The probability distribution of such particles will be assumed to be EP equals P. By a generalization of the argument used with SC Schrödinger's equation, it is clear that one can show THAT if there are chaotic processes in the motion of the particle, then, if P is not initially equal to P, it will approach Pi in the long run, see Chapter 9. Thus far we have not provided enough physical concepts to give a mean ing to the R and S, which constitute four quantities. The simplest physical idea would be to assume, as was indeed done in the original paper of BST1, that the particle is a spinning object whose orientation is specified by the three Euler angles, 8, cent, x. It is well known that a two-component spinor can be put into correspondence with these angles. Indeed we can write cent equals cos expi, x plus cent, slash 2 p is in expi, x dot p, slash 2 10.7. Assuming that the object is spherical, we may propose that b and cent I represent the orientation of the angular momentum vector, while x represents the angle of rotation of the object about this axis. If the angular momentum is 1/2, we can write the spin vector as s equals j 2p 10.8. This spin vector is then easily shown to be in the direction determined by 8 and l/j. It is clear that 109. The ontological interpretation of the Pauli equation 207. The spinor is now fully interpreted. We are evidently regarding the Hamilton Jacobi phase, s, as being equal to the angle of rotation of the rigid body around an axis in the direction of the spin. We can obtain an interesting physical picture here. If we add to the energy of the particle the rest energy m0c2, Schrödinger's equation, in this non-relativistic treatment, can be written as 81/jj1, 22, 8t, equals 2mv. EATPI plus VT/JI plus MOCT/G plus UB T/J 1010. WITHB equals 0 and V equals 0, a particle with zero momentum WILLHAVE the wave function 1 T cos 1 exp I cent/2 O/x exp zm 9/2 1 sm2 exp 1 cent. Thus the angular frequency is x equals m 1011, which is the frequency corresponding to the Compton wavelength. When k is not 0, we get t/jx exp I mc2 plus 2m k2 t expik z os1 exp I cent/2 1 0 1 2 ZSM 1 exp 1 cent/2. This implies a motion in which, while z is increasing with time, the particle is simultaneously rotating around the axis determined by the spin direction. For example, in the case in which the spin is directed along the line of velocity, an element in the spherical structure of the particle executes a helical motion with the screw sense determined by the spin direction. In general, the motion is, of course, more complicated. There will be a generalization of the Hamilton Jacobi equation for s equals x. To obtain this, we first transform the velocity, 105, with the aid of 107, and we find that 1 v equals dash vs plus cos b vqi, ea 2m 1013. It can then be shown, CBSTP 63, that S satisfies the equation 85 and T plus \75 plus cos B \7 cent, EA 21 \72 P cos 0 V \7 cent plus 2M 2MP 1 V plus \70 2 plus sin 20 \7 cent 2 plus SB equals 0 2M 1014 208. The undivided uniors. In the above we have a generalization of the quantum potential WHICH is given by 1015. In additio n, the orbit AL motion dep A and ds on the angles 8 and cent which determine the spin vector s. This is a quantum ch and ICAL spin orbit. Coupling. Evidently it is also necessary that, and cent DEPE and D on the orbit AL. Motion. What happens is that the spin orbit coupling brings about a quantum torque acting on the spin vector, WE shall not go INTODETAILS here, but the relevant equations are given in BSTP.64. We see AN illustrate the meaning ng of these equations in terms of a measurement process INWHICH. We begin with a spin pointing in an arbitrary direction and measure it in the z direction. As the wave packets corresponding to positive and negative spins respectively begin to separate in the z direction, ITIS found d, phi rst of all, THATTHE quantum torque eventually lines the particle spin UP with the corresponding wave packet INTOWHICH. The particle ultimately goes. Where the particle will go depends not only on its INITEL position, but also on the INITIAL values of, and cent. However, WITH the probability YDI stribut ION that has been assumed, IT is easily shown. That the probability that the particle will end UP in a given phi NAL packet T/1, Z, is JLIP1, Z, L2 dx. And THIS, of course, will be the same as one obtains in the usual interpreted ions. The relevant orbits have been worked out for 2C as ES, C Dewdney. ETAL4. In both, one assumes the mass, m, of the particle is so great that we can neglect the spread of the wave packets. In case 1, the spin points initially in the x direction. The trajectories are shown in phi gu re10. 1. While the turning of the spin directions are shown in figure 10. 2. For case 2. Similar results are given for a certain INITIAL spin direction THATYELDS is 75%. Probability for spin up in the z direction and a 25% probability for spin do WN. These trajectories are shown in figure 10. 3. WHILE the spin directions are shown in figure 10. 4. 10. 3. The many-body Pauli equation. As shown in BST1, 2, the model described here works consistently and D provides an adequate ontological interpretation of the Pauli equation FOR. A one-body system. However, this model gets into very serious difficulties when we try to extend it to a many-body system. To show what these Difficulty 8r, let us begin by considering the general wave function for such a system. 11 equals 11, 1. N, Z1. Zn. This H is 2. N. Complex components. Or 2. N plus 1. Figure 10.4, the field of orientations 8, Z, T, associated with figure 10.3. The ONTOL logical INTERP re TATION of the POW LIEQUATION 213. The many-body POULI equation IS then, as SUMINGB equals 0. 8 feet 11 inches. 1 2. L. I 7 feet equals, 2m. Underscore. L comma, V. Plus V, Z1. Zn, 11. 1. N. 1016. From THIS we obtain the net probability density I and the configure Ti on space of all the P articles. 1017. See section 104 for a more detailed discussion of the many BODY wave function. Let us then define the current density I and configuration space as 1018. It then follows from THE POULI equa Ti on THAT plus L, V and Jn, equals 0. 1019. N. The above expresses the conservation of probability I and configure Ti on SPACE. In analogy with what was done in the many-body SCHROOINGER equa Ti on. This suggests THAT we define the particle velocity as 1020. The above can be regarded as a generalization of the guidance co-condition. WHILE the conservation equation, 1019, implies that particles guided in this way WILI have a conserved probability density. Butto complete the I interpretation, we need to define the spin vectors. In agreement WITH what was done with the velocities, the spin of the nth particle, Sn, Hs to be defined as Sn equals 1/j, JLN P. 1021. Where, Jn represents the spin matrix of the nth particle, and Ln represents the unit matrix on the spin indices of all the other particles. This will define at most 3 n functions. We have also THE defy NITION of the velocities. Vn, which will add up to give at most 6 n functions, though not all of these may be independent. These are all the properties belonging to the individual particles alone that our spin model can allow for. However, 214 the undivided universe. As we have already pointed out, the wave function contains, in general, 2 n plus 1 independent real parameters. Thus for the two-body system there are 8 independent parameters. But there are 6 spin vectors and 6 velocity components. Therefore it should be possible to give a physical meaning to all the parts of the wave function for the CASE, in WHICH, of course, not all. The physical quantities need be independent. Dudney et al. 5 HAVE, in FACT, considered this case and HAVE given some detailed results. It is clear however that as we increase n indefinitely, the number of physical properties of the individual particles will only increase as n, while the number BER of independent parameters of the wave function will increase as 2 n plus L. Therefore there is no way to give a physical meaning to all the parameters along these lines. One might consider properties belonging to sets of 2, 3, or 4 particles etc. But it is difficult to see WHAT this could mean physically. SUCH properties would be E non-LOCAL and might be E significant even when the particles are far apart. In any C as E, the simple model of a set of spinning p particles would no longer apply. The above difficulty makes it doubtful a consistent interpretation of the many-body polyequity on CANBEOBTA and in terms of a model of spinning p particles. But THR is a further difficulty even with the one-body Pauli equation, when we consider the fact that THIS must be E the non-relativistic limit of a relativistic theory, i.e. the theory of the Dirac equation. The fact is that we not account properly for the value of the angular momentum for a model of this so RT. Using the relation for the frequency of rotation of a particle that we obtained earlier, we CANE as hilley. See that to have a spin 1/2, we would need an electron of the size of the Compton wavelength. But we know that this cannot be allowed because of the experimental data on SCATT erring. In fact, THIS data implies that the electron cannot be larger than about 10 to 16 cm. To obtain the angular moment h/2, a spinning particle of the size WULDHAVE to have a peripheral velocity very much greater than that of Lagrange T. Since we have to regard the Pauli equation as the non-relativistic limit of the Dirac equation, which is fully relativistic, we cannot allow SUCH velocities. For these two reasons we conclude that this model of a spinning p particle will not be an adequate one. 10.4 The Pauli equation as the non-relativistic limit of the Dirac equation. We can obtain some further insight into what would be a proper model for the Pauli equation by considering in some detail how it comes out as the non-relativistic limit of the Dirac equation. We begin with the Dirac spinor. The ontological interpretation of The Pauli equation 215. Il equals 111 where A equals 1, 2, 3, 4. The Dirac equation is all equals AV, IEA il, IVLLL, IM, 3 111. At where A, 3 are the Dirac matrices. We choose a representation in which 3 is diagonal and right. 10.22. Where 1/1 and 1/2 are two component spinors corresponding respectively to 3 equals plus 1 and 3 equals 1. The Dirac equation becomes Al/1 equals dash J V IEA L/2 I V plus M L/1 A at Al/2 equals dash J V IE A I/1 I V plus M L/2 B at where J are the Pauli matrices. 1023. For low velocities and positive energies, 1/2 1/1 WITH 1/2 XEXPIET. We obtain E V plus M L/2 equals I J V IEA L/1. Putting equation 1024 into 1023a, we find AL/1 J V IEA J V IEA L/1 V 1 equals plus MLI at E V plus M. This becomes AL/1 1 equals 8T V IEA 2 1/1 plus E V XA JL/1 plus V plus M L/1 E, V plus M. Writing E equals M plus L. E and using, we obtain 1 L, E, V. 2M plus L, E, V equals 2M. 2M. JN 1 2. E. B, 1 equals, V, IEA 1/1 plus, 2. J1 colon plus V plus M, T/I. UI 2M. M. 10.24. 1025. 10.26. 1027. 1028. This is clearly the Pauli equation with a constant rest mass term added. 216 the undivided UN for ERSE. To give an ontologic AL interpretation of the Pauli equation considered. As ANON relativistic limit of the Dirac equation, we begin with the Dirac current. WHICH satisfies the conservation equation. Op. O, T plus V equals 1029. 1030. As we have been doing in previous C as ES, we take advantage of the FA-CTTH at. When a conservation equation is satisfied, we see AN always assume a P article. With the velocities satisfying our now generalist guidance condition. J. V equals, P, 10.31. WHICHH as a probability distribution given by P equals P. To do this it is of co-URSE, necessary TH at P be positive defin ITE. BUTP equals 1 cent 12 is clearly positive definite. A alternative definitions of the current density WHICH do not, in general, lead to positive definite probabilities HAVEBEE and considered by de Broglie 6. But evidently we cannot obtain a consistent ontological interpretation if we admit negative probability densities for the P article S. To simplify the subsequent discussion, WE shall from now on restrict ourselves to a free particle. From equations 10.24 and 1027, we THN obtain 1032. LSO assuming energies low enough SO the T E/M can be E neglect D. We then OBTA in 10.33, which read UCES to the sum of two terms, J A plus JB, where 10.34 and 1035 THE velocity correspondingly reduces TO the sum of two parts V equals VA plus VB, where 10.36 the ontological interpretation of the Pauli equation 217 JB VB equals 10.37 P. The first PART of the current IA is the same as it was in the BST inter. Pretation of THE Pauli equation, ANDVA gives the same velocity as in this I interpretation. The second PART, IB, satisfies the identity V. IB equals 0 and this evidently corresponds to some kind of additio NAL circulation. To see what this means, consider the C as EIN, which 1/ is a spherical wave PAC ket of radius A, centered at the origin and falling ng off rapidly at distances of the ord ERR equals A. The term VB equals 1 VX 1/J TC1 1/J 2 MP 1038 represents a velocity in the direction RXS, W here S equals 1/TC1 1/. This implies a circular movement around the direction of spin which H as a maximum velocity NEARR equals A. This additional velocity, Vb, gives rise to a further contribution Uti onto the mean magnetic moment over and above THAT coming from the orbital motion. Indeed, THEAVERH of the total magnetic MOME and T, M, is EL dm equals 2r x dr equals 2rx a dr plus 2rxj bt. The first term I and the above is just. We can write this as 1039, 1040, 10.41. The above is just the orbital momentum of the CUR rant. The second d term is 10.42. We can readily transform this into 1043. 218 the UNDI11 UNI verse. This is the average magnetic moment due to the circulating motion, which evidently comes out equal to the average obtained I and the usual interpretation. We see then THAT, in the Dirac theory, the magnetic moment usually attributed to the SPIN can actually be attributed to a circulating movement of a point particle, and not that of an extended spinning objectile. The total value is, however, independent of the size of the wave packet because, although the velocity of circulation goes down by a factor L/A for LARGE wave packets, the moment of moment contains a further factor R which compensates for this. This implies that the magnetic moment is not an intrinsic loci said property of an extended particle structure at all. Rather, it comes about as a result of the general motion of the particle through space as determined by the Dirac guidance condition, 1031. This means that the magnetic moment, like so many quantum properties that we have discussed in earlier chapters, is a context-dependent property of a point particle. This property depends on the quantum field, i.e. the Dirac spinor, if A, and therefore, ultimately it has to be regarded as a potentiality that depends on the context of the overall environment in a way that we have discussed in chapter 4. In the usual approach, the magnetic moment is regarded as the product OFSPIN and therefore it is implied that whatever movement product magnetic moment should also be responsible for what is generally called the spin angular momentum. It seems natural to suggest, therefore, that there is some relationship between the circulatory motion THAT we have described above and WHAT has commonly been called the spin angular momentum. In seeking this relationship, it is crucial to know THAT, for the Dirac particle, the velocity and the moment are not in the same direction. Indeed, the momentum of the particle follows from equation 10.34. 1/g, Vij, I, V1/g, 1/j1. MVA equals 2ip. From which we can express the velocity as p. V equals, plus Va. M. The orbital angular momentum is low equals Rxp. 1044. 1045. The ontological interpretron of the poly-equation 219. In an isolated system one expects the total angular moment to be a constant. But if we compute Te low we obtain low Rxp plus Rxp. Rxp plus Rxf. Rxp plus T. 10.46. Where FISTHE applied force and TISTHE applied torque. Moreover, even if T equals 0 we will still not have conservation of the orbital angular momentum. FOR the C as EOFA Dirac PA radical. In the USUAL interpretation a similar question arises. Thus the orbital angular mom entum opera TORL equals RXP is not conserved EVN for a free particle beta USEL equals RXP equals O, XPF0. This fact implies THATTH is an additional intrinsic angular momentum operator S and, as is well known, if we choose S equals ER/2 we obtain S equals O, XP so that J equals L plus ER is conserved. Returning to our model we want to show that what H has been usually called spin angular momentum can be attributed consistently to the CIR. Coulatory motion THAT comes out of the non-relativistic limit of the Dirac equation. WHAT is usually CALLED. The mean spin angular momentum density is JUST. S equals T/JT underscore T/J. 2. Let US now consider the quantity E equals RX, \7x. S. 1047. 10.48. WHICHH as the dimension SOFAN angular momentum density. Using THRE index tensors with indices I, J etc. We see AN readily SH out THAT. 1049. So TH we obtain for what is usually called intrinsic angular momentum density. 1050. We see TH and THAT Sj differs from TEJ only by a perfect divergence. Therefore it is clear THAT their averages will be the same, BE cos THEINTE. Grl of a divergence is 0, but in addition, TEI will also be conserved. To see that TH is so we know TH at replacing Sj by TEJ merely adds a term. To LJWHICH is equal to 101A I plus R, S, 6, RKSK 28X, J28X, J, A, 1050. 220 THEUN dronited UN at IERSE. IFTJ is the tensor current density FORTHE total angular momentum density. JJ, the conservation equation for the latter can be written as 81, ATJ plus 0 UTUX ADDING 1050A to TJ leads to F, JJ plus AR plus 1 OSJ 6 IRKOS K equals 0 AT ox 2 ox JF T 8T. It is then clear that the total angular momentum will be conserved if THE angular momentum density OF circulatory motion as DE phi NED through TEJ undergoes detailed conservation. Therefore TEJ is JUST as good as CANDIDATE. For the I entrance I see angular momentum density as /JJ. If we accept TE1 as the I intrinsic angular momentum density, we obtain IN. For THE total angular momentum 1051. In this way we are able to account FOR the intrinsic angular momentum as produced by the circulatory motion. Note however THAT this angular momentum is only HALF that which we might HAVE expected at phi RST side from our expression for the magnetic moment, 10.43. The reason is basically that when VB is not in the direction of the momentum, there are intrinsic torques. These reduce the contribution of THIS motion to the total angular momentum below that which one might HAVE expected from OUR general intuition. THIS latter, of course, does not include such C as ES in which THE velocity and the momentum are not parallel. It follows then, that like the magnetic moment, the spin is also a context-dependent property of the particle rather than an intrinsic property. It might be better to call it a result of the context-dependent circulatory motion of the trajectories which is over and above THAT, which determines the usual orbital angular momentum. To sum up then, the interpretation that flows out of our discussion is THAT. The electron must still be regarded as a simple point p particle whose only intrinsic property is its position. The particle h as a velocity which is determined by the guidance condition, 1029. In the non-relativistic AP approximation, this includes that assumed in the BST MODEL, ALO-NG with an additional circulatory contribution ILX, 1/IUL/1/2 MP. In this approximation, the probability density is P equals 1111 I12. This model is very close to the one that was phi-RST proposed by Bell, 3. Who likewise assumed a point particle, but who assumed that the mean THEONTOL log equal INTERP re TATION of THE poly equa TION 22-1. Velocity is the same as THAT of the BST model, where T/JT/LT/J/LT/JT, T/J V A 2 MIP. The Bell model differs from the one that we HAVEJUST developed, because it does not include the circulatory motion corresponding to the magnetic moment and the spin angular momentum. But since \LJ8 equals 0, both models will give the same probability density. Therefore, as long as we are only interested in probability densities, the circulating spin current can be E neglected, and WECANU Bell's model instead. In the models THAT/HAVE just been described above, we restrict ourselves to determining the motion of a particle through suitable guidance conditions, and we do not attempt to account in detail for the accelerations through something like a quantum potential or some form of spin-orbit interaction. To do this, LATTER will give insight only if the acceleration can be given as some simple function of the relevant physical variables. For example, in the Origin-NALCA interpretation, we find that the acceleration is determined by mi equals \LV plus q. The first of these terms represents the part of the accelerate on THAT can be accounted for in terms of classical forces. THAT are generally local and that produce an effect that is proportional to the intensity of the phi LD. The term \JQ represents the quantum mechanical contribution. THAT depends on the form of the field and not on the intensity, and THAT acts in a way that is generally no local. In the BST model for the one-particle system, THR were additional quantum mechanical terms corresponding to explicit expressions for the spin-orbit coupling. But in the many-particle system, we could not find any except tab-LE physical interpretation for the vast number of terms that entered into the determination of the acceleration. In addition, we found that we could not consistently attribute the spin angular momentum to an extended p-particle. We HAVE therefore reached a point where the attempt to account for the acceleration in terms of various forces no longer provides any useful insight HT. Nevertheless, the theory still works consistently as long as we HAVE a suitable guidance condition. Given THAT there is no extended particle that is spinning, and THAT what we call spin represents only some average property of THE circulating orbital motion. How do we understand what we usually call a measurement of the spin, for example, in a Stern-Gerlach experiment? To discuss TH is We may conveniently consider a neutral hydrogen atom with one orbital electron in an s state. From equation 1028, we can see THAT the operator for the interaction energy of THE electron spin with the magnetic field is E/2m, UB. We neglect nuclear spin here. If B is inhomogeneous, THAT is B equals B, Z, it is readily shown, 7, that this will cause the initial wave packet 222 the trend of 1 DEDUNIVERSE to be REAK into 2 PARTS that move in opposite direct ions along the axis determined by B, O. For example, suppose the initial spin was in the x direction, so that the spin current was circulating around D the x-axis. After interaction with the inhomogeneous magnetic field in the z direction, 2 packets begin to separate in this direction and eventually cease to overlap P. Clearly THE particle must end up in one of these PATs. The results in each individual case depend, of course, on THE precise initial conditions. The probability for each possible result will come out as 1/2, given our assumptions about the probability distribution of the initial conditio ns. If the result corresponds to spin h/2, the current will circulate ℏ the positive direction, while if the result is h/2, the circulation is opposite. In this way we understand what happens in a so-called spin measurement as an essentially participatory process. In this process the net properties of the orbital motion are transformed through this participation in a way that depends on the precise initial conditions as well as on the environment supplied by the measuring apparatus. The value that is attributed to the spin as a result of a measurement process is thus a potentiality whose realization depends on these conditions and on the general environment, including THE measuring apparatus. 105 Extension to THE many-body system. We shall now extend this model to a system of many particles. In doing so we shall prove THAT the non-relativistic limit of the many-body Dirac equation implies that the current for each particle is just the one THAT we obtain for the many-body Pauli equation given in section 103, together with the circulating spin current for each particle. This latter is basically just an extension of the spin current obtained in the one particle SYSTEM. We begin by defining THE Dirac wave function for a system of many particles. The tree TMnt is very similar to THAT of the many-body Pauli equation. The total wave function can be written as 10.52, where each index a runs from 1 to 4. We are not for the moment interested in the question of Lorentz invariance, which we shall discuss in a later chapter. The Dirac equation for the system is THN I equals LO.NVN plus MNF3N plus V, ZN. 1053. N. On represents the velocity operator for the N1H particle. Its matrix LMENTS operate only on the spinor INDXN. Similarly for F3N. The O.N have the ONTOL logical INTERP re TATION of the Pauli EQUATION 223. Anti-commutation relations. A. 1054. And the commute-ation relations. For NFN. B. 10.54. That is to say, the ABE belonging to one particle commute with those belonging to the others. Similarly, C. 1054. And D. 1054. Let us now adopt the representation INWHH all the /3n are diagonal, so that the 1particle wave functions take the form WH air 1/J1K and 1/J2K are two component spinors WHO's indices have been suppressed, and where equals to refers to the small component t. The n-body wave function CANTHN be written as W equals WN, Z1, Zn, I. The Dirac equation will now have two n explicit indices representing the large and small components for each particle respectively. The Dirac equation can then be written as 1055, 1056, 224. The UNDI111 DEDUNI11 ERSE. We now write LJXXP, IET, and assume that all the particles HAVE, POS1T1VE energies. The PA-ULI wave function will THN be approximately F1, 1 foot. 1W. The total energy will be approximately E equals LNMN, INTHIS. Non-relativistic approximation in which V is assumed to be SMALL compared to LNMN. For each particle, n, we CAN solve for W. 2 feet. NI in terms of W. 1 foot. W. N neglecting V for THE reasons WEHAVE given, WE phi ND. 10.57. If we substitute this into 1038, IT is readily verified THAT we OBTA in the Pauli many-body equation. However, what we are especially interested in here is the current of the N1H particle, which is JN1, JFON, /J. LW. 1 foot, N on W. 2 feet. N. 1058. LETUS now use 1057 in 1058. We phi and DTHAT, assuming all THEPA radicals have the SAMI mass Jn 2IL cent foot. This reduces to Jn 2IE cent L 1 foot. N \7n /J L foot N. We have suggested before, we CAN simplify by assuming all the Fn are 1. Corresponding to P06 additive energies for each particle. The remaining wave function is then JUST the PAULI many BODY wave function W. We then get 1061. THEONTOL logical INTERP re TATION of the Pauli equation 225. From this we co-NCLU THATTHE model, 1061, for the n-body system can be obtained by regarding each particle as having two parts to its velocity. And 1/2 miles, L/it, VNL/I, \I01 IT, L/I. LIP1. 2. 1/2 M, VNX, 1/ITTNL/I. LIP1. 2. 10.62. 1063. Therefore our orig INALPIC tour, which adds a circulating current to the VE velocity of each particle, still holds for the many-body system. We HAVE of course been assuming the interactions are weak enough. So THAT all the particles will be within THE non-relativistic limit. In THIS approximation the details of the interaction will not significantly change. This picture 106 THEEPR experiment FOR2 particles OF spin 1/2. We shall now go on to discuss the EPR experiment for two particles of spin 1/2. We sh all phi and d that we obtain a consistent interpretation that is in fact very similar to the one that we gave for the case of two particles of spin 1 forming a molecule of total spin 0, chapter 7. We begin by denoting the coordinates of our two particles by z1 and z2. For the sake of simplicity, we suppose that the2 particles are not equivalent. We further assume that each particle is fairly well localized, with respective wave packets slash zi and g, z2, the centers of which are separated by a distance that is much greater than the width of either of the packets. We also suppose that these packets represent s-states about their respective centers. The wave function for a system with total I entrance IC angular momentum 0 will be where 1 slash j, j, I, 2 equals f, z1, g, z2, l1 slash I, 1. ij equals 1. 0 for I equals j. 1. j2 ip1, 1 for I equals 1, j equals 1. 1. j2. l slash I1. I. For j equals 1, j equals l. 10.64. 1065. 226 The undivided universe t slash j expresses the fact th at the wave function is antisymmetric I and the spinor indices of the two particles. For the wave functions that we have as summed, the part tcles will have no or by tal angular momentum. The intrinsic angular momentum of the first particle is r1x, v1x s1. E1 equals p. And for the second particle it is a, b. 1066. 1066. Clearly the values of E1 and E2 are determined by S1 and S2. We readily obtain and wise S1 equals LVLCR, Ki equals O. IJK. A, 10.67. B, 1067. This means that I and the initial state, there is no circulating current COR. Responding to intrinsic moments. We shall discuss the further significance of THIS in more detail presently. But we may note here THAT this result is very similar to that obtain ed for the orbital angular momenta of two atoms of spin 1 combined to make a molecule of spin 0, where similarly we found THE particles were not moving. Let us now suppose that particle number 1 is subjected to a Stern-Gerlach experiment so that its wave function divides I into two parts, 1 moving upwards along the z-axis by a distance d, and the other moving downwards by this distance. We assume also that d is much greater than the width of the wave packets. The wave function then becomes 1068. If particle number 1 enters the packet going upwards, part ICLE number 1 actually is set in circulatory motion in the positive direction around d the z-axis, while particle number BER2 is likewise set in motion in the opposite direction. And if particle number 1 enters THE packet going downwards, the results for both particles will be opposite. It is clear then THAT we have explained the correlations and the results of the EPR experiment, not only for the case of the spin measured in the z direction, but also in an arbitrary direction. This is because the 2, 3, 4, 5, 6. The ONTOL09 ICL INTERP RE TATION of the polyequation 227. IL1. 1 2. 3. 4. 5. TT. 6. Stern-Gerlach 1 on. Stern-Gerlach 2 off. Figure 10. 5. TR ejectories and correlated spin vector orientations for two Particles initially in a singlet state after the impulsive measurement of the Z1 component of the spin of particle 1 only. 228 The undivided UN4 ERSE. Wave function T/J is a scalar FOR rotations, so that the SME analysis can be carried out for a Stern-Gerlach experiment performed in an arbitrary direct ion. At first sight it may seem very strange to say that the particles had entirely no circulatory motion corresponding to intrinsic angular momentum. But, as also happened for the CASE of two particles of spin 1, the intrinsic angular momentum of a given particle is seen to be very much a contextual potentiality, not only with regard to its direction, but also with regard to its absolute value. This is affected not only by the environment supplied by the measuring apparatus, but also by the presence of other particles, and by the wave function of the combined system. Indeed, a little reflection shows that the only possible way to have a completely isotropic state corresponding to a molecule of total intrinsic angular momentum 0 is to have 0 intrinsic angular momentum for each particle. The Pauli exclusion principle is, however, still maintained for equivalent particles because for these the total wave function is antisymmetric. The way in which the intrinsic angular momentum develops for each particle can be followed in detail using the appropriate guide NCE conditions. Dudney et al. 5 have do nethis for the EPR experiment for the BST mod EL. However, their results for S1 and S2 will still be relevant to R mod EL. Although THEIR velocities differ from ours in that they do not contain the circulatory motion, this difference does not alter the probability distributions, as we have pointed out in section 104. These results are given in figure 105, in which it is clearly seen that .S1 and .S2 gradually increase from 0 to their phi NAL values in each case. 10.7 References. L. D. Bohm, R. S. C. H. Eiler and J. Sciamno, Nuovo CIM. SUPP 1, 48-66. 1955. 2d. Bohm and R. Schiller, Nuovo CIM. SUPP 1, 67-91, 1955. 3j. S. BLL, Speakable and Unspeakable M. Quantum Mechanics. Chapter 19, Cambridge University Press, Cambridge, 1987. 4. C. Dudney, P.R. Holland N.A. Kyprianides, Physics. Let. 119a. 259-267, 1986. 5c. Dudney, P.R. Holland N.A. Kyprianides, J. Physics. A 20, 4717. 4732, 1987. The ontological interpretation of the Pauli equation 229. 6. L. de Broglie, Une interprétation causale etnon linéaire de la MLCANIQUEONDLATOIRE, la théorie de la double solution, G.A. Thiers. Villiers, Paris, 1956. English translation, Chapter 10, Elsevier, A.M. Sterdam, 1960. 7. D. Bohm, Qua Ntum the Y, Prentice Hall, London, 1951. Also avail. Abel in Dover Publications, New York, 1989. C. H. Apter. 1-1. The ontology cal interpretation of boson fields. 1 Introduction. We are now ready to extend our ontological interpretation to THEBOS on field, which in this chapter we consider only from a non-relativistic standpoint. The question of relativistic invariance will be discussed in the next chapter. We shall begin by giving reasons why it is necessary in doing THIS to give up the notion of particle as fundamental and to regard our basic variables as the field variables themselves. To understand what THIS means, we shall approximate a continuous phi ELD by a very dense distribution OF phi ELD points X, where n is the n1h point. The variables will then be the fields at the points in question, e.g. in the case of a scalar field cent, X. These are represented by a point in the configurator Ti on space cent, X. Of all the field variables, WHICH, in the limiting case of con TINUITY, approaches a non-denumerably infinite number of dimensions. This is analogous to a system of infinitely many particles, but the coordinates x of the particles now correspond to the values of the field cent, x, at the specified points at which the field has been assumed to exist. The trajectory of a whole set of part IC and their configuration space is then replaced by the trajectory of the whole set of field variables in their configuration space. This means that the concept of particles does not correspond to a basic variable in our interpretation. How then do we understand the particle-like properties of the bosonic field, e.g. p-photons or bosons with mass? In this chapter we develop an ontological interpretation which shows systematically how this comes about. To do THIS we shall first analyze THE field into normal modes A and D discuss their meaning for excited states of the field, including both Fock states and coherent states. We then discuss the absorption of a quantum of energy by an atom. In this process the field is initially distributed rough out a wide region of space. H.O. Weaver, the equations for the field variables are not linear and local wave equations, such as for example, the D'Alembert and 230 Klein-Gordon equations. Rather they contain an extension of the quantum potential, which we call the superquantum potential of the total field. This is both non-linear and non-local. Because of this nonlinearity and non-locality, energy is swept in from the entire wave PA so that it concentrates on the atom as a single quantum of energy HV. When and whether this will happen depends on the detailed initial conditions of the total set of field variables. But statistically, the probability will be the same as in THE usual interpretation. If there are several atoms, these initial conditions will determine which of them will absorb the full quantum of energy. In this way we are able to answer the criticism raised by Renninger 1, who considered a spherical wave and asked how only one atom out of all the atoms on the wave surface comes to be excited. We thus show that while the field variables are distributed throughout space, they generally manifest themselves in a discrete particle-like way, e.g. as if the field were composed of photons or massive bosons. This explains the wave part ICLEDUA. For it is a wave-like distribution of field variables that determine the discrete particle-like manifestations. This is one of the major differences between our ontological model of particle variables and THAT of field variables. In the C as E of the latter there are no particle variables but only dynamic states of the whole set of field variables, which suggests certain particle-like features in the overall behavior. As an important illustrative example, we consider the photon-like HAVIOUR in a gas arising when a quantum of energy is scattered by the atoms of this Gs. Each scattering process gives rise to a subsequent quantum, which THEN goes on to build up a cascade of ionized atoms that constitute what is usually called the track of the photon. In our approach THE-SCAT, tearing process is described by the absorption of a FU-LL qua NTUM of energy from the overall field in a way that we HAVE already outlined, followed by re-radiation of a quantum of a lower energy. This is then absorbed and re-emitted by a succeeding atom and so on. The typical scattering angle in the Compton effect is of the order of /c, where is the wavelength of the quantum and c is the Compton wavelength of the atom. For HIGH, energy quanta, THIS will be SMALL. Therefore successive collisions will be DIS. Tribute approximately along a straight line with small random variations. The whole process takes place in a definite time sequence as if a bullet-like object has struck the atoms in a series of collisions leaving ionized particles in its wake. Yet in our interpreted TION there is no such object. In THIS connection WE emphasize that photons HAVE never been observed directly but only through the manifestations in particulate matter THATR attributed to them. Since our approach explains all these manifestations, we HAVE no need of the further assumption of a bullet-like photon to account for what is actually observed. 232 The UND 111 DED UNWERSE. In the classical LIMIT, the superquantum potential BE comes negligible. In a way similar to THAT, which we HAVE already discussed for the quantum potential in Chapter 8. The variables then obey simple linear equation NS, e.g. the Dal-Imbert or K-Line-Gordon equation. Their Fourier coefficients correspond to simple HARM on IC oscillators which can, for example, be treated in terms of coherent states that HAVE and essentially classical behavior of the variables for high quantum numbers. The above makes it clear THAT in the CLSICALLIMIT, a bosonic system, does not pro to significant particle-like manifestations. The nearest we can come to a particle in the classical LIMIT is to make a wave PA in the field variables. Insofar as the spread of this PA can be neglected, there is a localized pulse of energy which follows a particle like PATH, C, 4x. Ample, MA 2. BUT in the classical LIMIT, the restriction to transferring discrete quantities of energy to particulates matter plays no significant role. For the representation of the behavior of the field as continuous provides a very good approximation to what actually happens. After thus bringing out the basic concept needed for our ontological interpretation of quantum field theory, we shall extend TH's interpreted TION to explain interference phenomena and the Pythagorean 3 experiment involving the interference of two separated low-intensity LSERS. FINALLY we treat the EPR experiment along with the Compton effect. 1. 2 reasons FORSTRTing with quantum field theories for bosonic fields. In developing an ontological interpretation of bosonic field theories, we have a priori to consider two possibilities. Firstly, we could try to interpret such theories by assuming a set of bosonic particles that would be guided by a quantum field based on a wave function of the whole system of particles. If we could do THIS, the quantum field theory would not require a treatment basically different from that which we have already given for the many body system. In the case of the electromagnetic phi LD, for example, such P articles would represent photo ns, while for meson fields of various kinds, they would represent the corresponding massive bosons. But secondly, we could start as we have indeed already suggested in the introduction, by regarding the field quantities themselves as the basic beables. The wave functional of all these beables would then imply new quantum properties for the fields, and the particle-like manifestations would be explained along the lines discussed in the introduction, as dynamic properties of the whole set of field variables. In this section we shall sketch the principal reasons why the first approach cannot be carried out consistently. We will thus be left with the second approach as the only possibility. And this is, indeed, what will be the content of the remainder of the chapter. Various authors, de Broglie, 4, Cuffaro-Petroni et al., 5, have proposed. For example, we begin with the K-Gordon scalar equation regarded as the quantum wave equation for a single spin zero particle. This is. We will again put h equals 1 throughout this chapter. From THIS it follows that there is a conserved charged current. We could propose the guidance relation J V equals dash A 111 11.2 11.3 but, as we have already pointed out in chapter 10, section 104, in order to be consistent this would require that J0 be positive definite. However, it is clear that J0 as given in 11.2, is not, in general, positive definite. Thus if the energy is well defined and positive, J0 is positive, while if it is negative E, then J0 is also negative. It is therefore already clear that this approach cannot be made consistent. One might perhaps try to get around this difficulty by restricting sent to positive energies. But there is no way, in general, to maintain such a restriction, because in principle a potential can always cause transitions from one sign of energy to the other. Therefore we will always be faced with the possibility of a linear combination of positive and negative energy ES. For example, we can have sent equals /J underscore X E plus IE T 11.4. This gives J O equals sent I X sent plus X sent X sent underscore X plus P X E 2 IET plus C 11.5. This can move between positive and negative value ES. So that even if we began with positive values of J0 we could not guarantee that J0 would remain positive indefinitely. Moreover, in going from positive to negative IVE values J O must pass through 0. This will give rise to infinite velocities. 234 the undivided universe, which do not make sense physically and which would in addition violate the relativistic requirement that v hesitant face, c. Since we see a not make a consistent particle interpretation of the kind given above for the K-Gordon equation, it seems reasonable to conclude that we should adopt the alternative approach of regarding T, L, X, as a field beable. The fact that J0 can be positive or negative is then understood through the notion that there can be positive and negative charges. This implies the possibility of pair production, so that the number of p articles is not conserved. Evidently in this approach there is no way to regard 113 as a guidance condition and the whole attempt to give a particle interpretation to this equation Br equals down. It has been proposed however that there are other conserved quantities, which would give positive definite densities, and THAT these would make it possible to go on with the particle interpretation nevertheless, Wesley 6. And Pr Osser 7. What they suggest is that 1 Tak the energy density, Yo0, and flux of energy, Yo, as a starting point. These satisfy the conservation equation. 2, T degree I. Oxo. Plus. Axi. Equals. Q. One would then define the p-article velocity as Yo v. Ru. Thus in the Klein-Gordon equation we have and yat equals a cent underscore ar slash j 2 ax at 116 117 118 119. Since 7 degree is evidently positive definite, it is argued that a particle interpretation of the Klein-Gordon equation can after all be maintained. A closer inspection shows, however, that such an interpretation would not be consistent with the theory of relativity, although in this chapter we are considering the field theory from a non-relativistic standpoint, it is still necessary that such a theory be applicable relativistically, or else we would contradict a large range of experimental facts. To show the inconsistency of such a definition of velocity, let us now consider the CA.E of a free particle and a special solution of the wave equation. The ontological interp retation of boson fields 235 equals expi, kx, wt. We obtain ri, o, y, oi, and 7 degree 2 equals t03 equals 0, m6 plus k, 2, 1110, 1111. We can always choose a Lorentz FRME in which k1 equals 0 and yo0 equals m6 while j degree I equals 0. This corresponds, of course, to a p-article at rest. If we now transfer Rm to a new Lorentz frame so that the p-article has velocity v equals v1, 0, 0, we obtain y, oo, too equals 1, vi, 1112, if, t00, yo, is to represent p-article density and current, it has to transform as a relativistic 4-vector, otherwise the integral of the probability will not be the same in every frame and the transformation between frames will not be unitary. This will require that the density in the new frame T100 should be equal to T00 / rather than to T00 / 1. V. 2. We emph as ISE. Again THAT the difficulty arises basically because the charge current has to be a 4-vector and not a second rank tensor such as YV. One can demonstrate even more striking inconsistencies in such an AP approach by considering the Maxwell field in free space. For THIS we have the energy density 2 pounds plus H2 Y OO equals underscore 811. The energy flux is given by the Poynting vector, so that OI EXH I T equals 411 1113 1114. Letus consider The special case in which EIS parallel TOH so that E XH equals 0. Assume further E and H are in the direction x1. This means that, under a Lorentz boost in the direction x1, we will still have E parallel to H, and EXH equals 0. It follows that the VF velocity is 0 in a whole range of Lorentz frames. Clearly it will not make sense to say that a PA reticle is at rest for THIS whole range of Lorentz frames. Yet another approach has been proposed for interpreting the KLEIN Gordon equation through a PA reticle model, see, for example, an ambulate. This is based on the assumption of an invariant PA parameter R which represents the order of development of a system. The suggested wave equation IS / equals D OT 1115 236 THEUND 11 IDED UNI 11 ERSE, where 0 is the D'Alembertian. If we look for solution of the form, we obtain F cent I equals to phi 1116. Choosing K equals M6, we see that THIS reduces to the KLEIN Gordon equation. But there is a new feature because we can now obtain solutions with arbitrary values of / and the general solution is 1117. This theory obviously H has room for a whole range of masses. Indeed, if the mass is fixed, no probability ES will depend on R, because the wave function will be proportional to expim2R where A is a suitable constant T. 1. Can obtain a non-stationary state only by a linear combination of terms corresponding to different values of I and therefore of different masses. In this theory, the probability density is defined as the scalar cent I which satisfies the conservation equation. 8, cent I plus L 0 U OT 1118, where J is given in 1 Since cent I is positive defy NITE, WE can consistently define the Gaida NCE condition. 1119. Writing cent I equals Rees we obtain from 1115, the generalist H. A. Milton-Jacobi equation, where LDR Q equals 2R is the generalist quantum potential. 1120. In order to bring out the meaning of these equations, we phi RST note that cent P has to be E taken as the probability density in spacetime for an event at a point x0, 11. For example, in the usual interpreted tion it could be E regarded as The probability in a measurement of finding a particle at the point zin at the time x0, for a certain value of the invariant parameter t. In an ontological interpretation, it would however be E the probability. THEONTOLOGICAL INTERP re TATION of BOSON fields 237. That, at THIS value of t, the particle act UALLY is at this point in spacetime. The velocity v wow ld then be the rate of change of the coordinates of this spacetime point WITHT. This theory evidently goes beyond the simple KLEIN Gordon equation, because its conceptual basis can only be understood in terms of a particle, which may HAVEARANGE of masses. For if THE mass is fixed, the probability is, as we HAVE seen, not dependent on R, so that TH air will be E. No way to discuss the statistics of the development of the system in the parameter R. For THE present WEDO not know how TO determine what should be THE actual mass spectrum. To do this would evidently require some extension of the THE ORI involving further new concepts. For example, THE particle may HAVE some internal parameters and the quantity of these might determine a mass spec TRUM. If this approach were successful, this mass spectrum should be THAT of the part isolate THAT are actually to be found in nature. It is clear TH and THAT the parameter T introduces a new concept which goes together with the range of masses. The meaning of this concept is THAT we cease to regard x0 as determining the time order of development. Rather, x0 plays a role not very different from that of the space coordinates. Thus at a given value of t, the wave function will, in general, spread over a range of 11 and x0. There is no way in general even to be sure x0 will always increase monoto nically with t, for, as we have seen also in the earlier suggestions regarding the Klein-Gordon equation, v0 can take on both positive and negative values. Interaction terms, which we have thus far neglected, can cause transitions between positive and negative values of v0, so THAT an initial wave function representing a monotonic increase of x0. With RCA and develop parts in which x0 goes on indefinitely decreasing with t, i.e. Track's parameter is by t can go bawards in x0. This is evidently a serious difficulty. However, further difficulties arise when one considers how one would treat the many-body system. If xjv represents the coordinate of the n1h particle, The wave function will be sent I11 xjv. A natural generalization of The wave equation would be 1121. Because sent I spreads out over the coordinates x of each particle, it follows. Th at particles considered at a given value of t will not all have the same value of x0. Indeed they will in general not even be all located on a simple space-like surface. Rather they will be distributed over a range of x0, which is, of course, time as meant in the usual sense e. It is not clear how this theory can be made to connect with the usual theory in which all the 238 the undivided un4 erse particles are considered at the same time, or at least onasi angle space-like surface. Various authors, see for example Vigier, 9, have suggested THAT for the 2 particlesystem, this ambiguity can be removed by considering the 2 particles at the same time in their center of mass frame. But with many particles it is not clear which frame sh old be taken as the rest frme. Thus let us divide n particles into 2 parts with n1 and n2 particles, respectively. In each part, all the particles could be taken at the same time in THEIR overall center of mass frame. But since the parts can be chosen arbitrarily, this leaves the whole question undefined. At the very least, this difficulty suggests that such an interpretation cannot be carried out unless the theory is supplemented by her conditions that determine the common time or space-like surface at which the particles are to be taken. For a given t, there is yet, however, another conceptual difficulty. Because The wave functions sent I spread out over a range of times for each particle, it follows THAT. The quantum potential for the many-body system Q equals TLNDNR/R will directly couple particles at different times. Non-locality is THS extended from space to time. In one sense THIS seems reasonable as a way of making the THEORY relativistic LLY invariant. Yet the concept of non-local ACTION over time introduces new difficulties for understanding CA usually in its usual sense. and because, as we have seen, parts of the wave function travel backward in time for a long way, THIS difficulty will not be restricted to short time intervals. To sum up then, we would say that while this idea is an interesting one, we cannot use it confidently on the basis of an ontological interpretation. Until these difficulties and conceptual ambiguities are cleared, up. 1.1. 3a. An ontological interpretation of bosonic fields considered from the non-relativistic standpoint. In view of what has been said in the previous section, we feel that the only possibility for an ontological interpretation that is at present viable is to assume the variables are the fields themselves. In THIS section we shall illustrate such an interpretation in terms of a real scalar field sent, x, with 0 rest mass along with its canonical momentum 7r, x. A more condensed treatment of the electromagnetic field H has been given in Bohm 1.0. As indicated in the introduction, we shall in this chapter restrict ourselves to a non-relativistic standpoint, and in the next chapter we shall discuss how our ideas can be extended to a relativistic context. We begin with the idea OF-THE configuration space OF, the total set OF field. The ontological interp re ion of boson fields 239. Variables. We recall that a good image of the meaning of the set can be obtained by approximating a continuous field by the field variables over a set of discrete but fairly densely distributed points, sent, x, which will ultimately approach a continuous set. The whole set of variables is then sent, x. To formulate the theory mathematically, we introduce the well-known concept of fun ional derivative of any function of the whole set of variables. For sent, x. This is equals Jim. For sent, x, plus 6 cents. For sent, x. 6 cents, x, 6 cent 06p. If 4 depends on the derivatives of sent, x, we may also have quantities like 6 4/6, d cent/dx. We shall not go into a detailed description here of this general notion of functional derivative which can be found, for example, in Schiff 1.1, but we shall use the ideas from now on. For a scalar field, the classical Lagrangian density is 1.122. In a p-article theory, the momentum canonically conjug 8 pounds/x. In a field theory, basically the same concept is used in the sense that the momentum canonically conjugate to p, x, is 6 La cent. 7r, x. 6 un/at 1.23. It is readily shown from an extension of the Euler-Lagrange equation that this classical field satisfies the wave equation. 1.124. To quantize a particle theory, we introduce the wave function 1/j xn. To quantize the field equation, we introduce a corresponding wave functional 4 equals 4, sent, x. Evidently this wave function al depends on the whole set of values ofq \x, at every point in the universe. This then gives 1412 as the probability of a total given field distribution, corresponding to a point in the configuration space of the overall field. In the standard quantum theory, the classical number 7r, x, is replaced by an operator which can be symbolized as n 6 op x minus 1 6 x 1.25 240. The undivided universe. This is analogous in the particle theory to pop equals I 8/8x. 20p, x. Acts on the wave functional 111. F, x. We emphasize again that there are basic similarities between quantum field theory and quantum particle theory, as well as differences, of course. The main similarity is that the field variables at each point play essentially the same role as the particle positions do in the particle theory. This can be made even clearer by considering the Fourier analysis of the field in a cubic box with periodic boundary conditions. The non-denumerable infinity of field variables is replaced by a denumerable infinity of Fourier coefficients. Pt with k, k11, k, restricted to integral multiples of 27r/L, where L is the size of the box. The Fou and Ctinal derivative Thn becomes an ordinary derivative, and the similarity to particle quantum mechanics becomes very obvious. To obtain the ontological interpretation of field theory, we do just what was done in the particle theory, that is, we assume the basic set of dynamical variables f, x, which we take to represent the variables, have well-defined and continuously changing values. As pointed out in the introduction, the trajectory of variables corresponds to a single point in the configured ion space of the total set of field variables. To determine this trajectory, we begin with what we will see all the super-Schrödinger equation, which is where H is the Hamiltonian given by 1 Fj2 H equals 2 plus Vf z t 2 all a pace 6 cent I z t 1126 dV 11.27. We Thn write 111 equals R cent z t. Exp is cent z t, and obtain first of all as1 j sixs 2 at plus 26 cents plus v cent 2 dV plus q equals 1.28, where q is the superquantum potential which we shall define presently. The above corresponds to the Hamilton-Jacobi equation of a particle system. We also obtain as 1 as 2 ft plus 2m l axi plus v plus q equals ap j underscore p sixs dV equals at plus 6 cents 1.29. The ontological interpretation of boson fields 241, where p equals 1111 is, as we have already explained, the probability of a given configured ion of the total set of field variables. This clearly corresponds in particle theory to the conservation equation. We see an right 8p8 85 fit plus L slash zip slash zi equals 0 I 1.30. This is an extension of the guidance condition for the particle case, which is p equals vs. The superquantum potential will be, and THIS is comparable in the many particle system to q mp equals underscore 1 L V R ZJ T 2M R ZJ T I 1131 11.32 1133. From the extended Hamilton-Jacobi equation, 11.28, we obtain the field velocity 8 cents at 8.5 8 cents 1134. Then equation 1129 CL early represents the conservation of probability. The remaining equation of motion is obtained from 11.28 as 1135. Putting 1123 into the above we obtain 1136. 242 the TMD for 1 DEDUNIRSE. In line with the particle C as E given INCH after 7, the classic AL lime IT is AP. Proudhead whenever Q becomes negligible. In this C as E, equation 1136 reduces to the ordinary wave equation. However, in the quantum doma IN, there is an extra term, FJQ/8 cent. In general, THIS is a nonlinear and non-local function of cent. As we shall see, it profoundly alters the meaning of the equation and leads to radically new implication s. We emph as ise again. However, THATINTHE classical limit none of these will be significant. 1.1. For analysis into normal modes and the ground state of the field. In order to discuss the ground state and excited states of the field, it will be convenient to go to a representation in terms of normal modes. To simplify the problem we may, as we have already suggested, consider a cubic box of side L and assume periodic boundary conditio ns. We take L to be finite, but much larger than any dimension of physical ICAL intera st, I, E, in principle. As large as we please. The normal modes will then be trigonometric waves, and an arbitrary field can be expressed as /2 I cent z t equals y v a k t cos k z plus b k t sin k z 1137, where with k 27 tnx x li k underscore 27 tne y li k equals 27 tn l, and where nx, ny, n are integers and v is the volume of the bow x. Because k and k cover the same functions, we should sum only over half the posse. Blee values of k, e, g, nx and New York cover all the integers positive, negative and 0, while n is restricted to values greater than or equal to 0. When ever the sum is taken with the above restrictions, we shall write it as above. L/. We also introduce 7 t, the momentum canonically conjugate to cent, z, t, which satisfies the Poisson bracket relations. Cent, z, t, 7 t, equals fjz, z. 1.38. We Fourier analyze 71, z, t, writing 2 I z, t, equals y vl and 1 c, t, cos k z, plus /3 k, t, sin k z, k. 139. The ONTOL logical INTERP re-TATION of BOSON fields 243. With the aid of 1138, we THN obtain the Poisson bracket relations. With all other Poisson brackets equal to 0. This means THATA1, A1, and by G, form a set of canonical variables S. From 1.27, we obtain the Hamilton IAN 1.40, which in terms of Fourier analysis becomes 1141. It is convenient to go to the complex representation of the normal modes. Writing. We obtain and cent z t equals lqk t exp ik z vvk 11 z t equals l11k t exp ik z vvk 1142 1143 11.44. From the above we see that the reality of cent implies THAT. Qk equals Q. K and that 11k equals 11k. We then obtain the Poisson bracket relations. With all other Poisson brackets being 0. And the Hamiltonian BE comes 1145. We can easily verify that the classical equations of motion are 244 the undivided uni verse. So THAT ik plus K2QK equals 0. We now go to THE quantum theory. We represent THE wave functional in terms of the QK and QK equals Q underscore K. We are restricting ourselves to HALFTHE values OF K. As before. We then write IL equals IL QK QK T. Because THE system reduces to a set of independent harmonic oscillators. The wave foo and CT can be expressed as a linear combination of the prod UCT functions. 1146. Each T/J QK QK satisfies an independent Schrödinger equation representing AHA harmonic oscillator. 1147. Writing T/J QK QJ Jacobi equation RK EXP ISK. We obtain the equivalent HA Milton. 1148. THE above result is similar to THAT obtained in THE causal interpretation of a particle undergoing HA harmonic oscillation. The GROUND state of equation 1147 then represents the zero-point energy. Its wave function is 1149. THE ground state OF the whole SET OF oscillators IS then 11.50. The quantum potential for this state is 1151. Writing. We get the ontology CAL interpretation of Boson fields 245 as equals E at E equals L 0 plus K L K OQK OQK 11.52. Since the wave function is real, 85/OQK equals 85/OQK equals 0 and we obtain 11.53. This is, evident TLY, the usual expression for the zero-point energy, NO. That each K corresponds to two real oscillators AK and BK so that the usual factor is not present. We shall now discuss the meaning of the wave function for the GRU-ND state, equation 1150. FIRSTLY, let us note that although THE quantum potential will, in general, be non-local, in the special C as E of the ground state it reduces to a local foo engine. In fact, it cancels the term LKK2QKQK, WHICH. The space represented ON, corresponds to \L cent. This is evidently a local function, as we shall see later. It is only in the excited states that non-locality appears, although in the classical limit it disappears again. Let us now consider the significance of the probability distribution. Wheeler, 1-2H has considered this problem for the electromagnetic field and H as obtain ed results similar to those that will be given here. HIS analysis is, however, developed in less detail and D, of course, does not consider the role of the quantum potential. We begin by expressing the QK in terms of cent, x, I, e. QK equals JVJ, EXPIC, x cent, x, dV. 1154. We HAVE suppress the core DINAT which will not be relevant in this context. This YILDS, where 1110 equals EXP. JJ cent, x, f, x, dV 1I, f, x, equals 2, KEXPIC, x, VK. 1155. To TURN this SUMIN to AN integral, WE introduce THE density OFK vector, which is V/211. 3. And we OBTAIN. F, x, equals 2. 3J. KEXPIC, x, d. K. 1156. 246 The undivided universe. This is not a properly defined function but WECAN evaluate it by taking a limit in which there is a CUT off in K space. We can represent such a CUT off by multiplying the INTE grand by a factor e, h and allowing a to become as small as we please. These integrations are then straightforward and the result is where R equals LZ, ZL 1 R2, 3A 2 slash R equals 71 feet 2 inches, P plus R2, 3. The probability function is then P equals, if 1 2 equals I FF cent Z cent Z R2, 3A2 dV 1 2 OEXP 71 feet 2 inches, A2 plus R2, 3 11.57 1158. This probability is largest when cent Z and cent Z have different signs. Therefore it is quite clear that for a given value of cent Z, it is highly probable that a neighboring field cent Z will have the same sign within a di stands of the order of a r equal that a is as small as we please e. This point CA and BE brought out more CL early by going to spherical polar coordinate. Nates where R equals LZ, ZI the contribution to the probability coming from a field cent Z, which is on a shell of radius R will be I JF cent Z plus R 2 3A 2 DD L 2 EXP 71 feet 2 inches, R2 plus A2, 2 RRH. Clearly this probability CAN become very small for small a and small r, when cent Z and cent Z plus R have the same sign. It is therefore most probable that the field cent Z is highly discontinuous, the sharpness of the DSC continuity being dependent on the CUT off radius A. Such a discontinuity implies that the most probable spatial form of the field will be chaotic, i.e. in the sense of modern chaos theory 1-3. H.O. Weaver, this chaotic variation will be limited because the variation of the QK will be the order of 1//f as can be seen from equation 1.50. Because 85/OC equals 11K equals QK equals 0, it follows that the field is static. This Result is surprising, as one generally thinks that the 0.0 fluctuations of the vacuum correspond to some kind of chaotic dynamical behavior. We can, indeed, obtain such a dynamical behavior by introducing the further 8.88 assumption that the field is taking part in a random fluctuation in which the mean value of ERK is 0. This would be along the lines suggested in our stochastic particle interpretation given in Chapter 9. However, for the perp 08E8 of the present treatment, we shall confine ourselves to the initial deterministic model, which we emphasize is completely self-consistent. The ground state energy which we ordinarily ascribe to the dynamic behavior will now be attributed to the superquantum potential. This, the ONTOL logical interpretation of boson fields 247, is analogous to the particle case in a stationary state, with P equals 0 and E equals V plus Q, or alternatively Q equals E. V in the classical case, we HAVE. T equals E. V. So Q is in some sense playing a role analogous to T. For example, in an excited state, the energy of the quantum potential enters into the quantum transitions in the same way that The kinetic energy would in the classical limit. And if, as we HAVE suggested above, the energy of the quantum potential is accounted for by further random motion S, then the analogy to our ordinary way of thinking will be very close. WHETHER we take the static or dynamic model, the GRU-ND state is not covariant because it defines a favored FRME in which either QK equals 0 or its mean value is 0. Will THIS be consistent with relativity? We will discuss this question in the next chapter. 1.1. 5. The excited state of The field. There is a considerable range of possible forms for the excited state of the phi-LD. One of these is the well-known set of Fock states in which the number of quanta and the energy are well defined. Another is the set of coherent states, 1-4, which are especially suited to the dissolution of the time dependence of the field and its approach to the classical limit. We will discuss these in detail in the next section. For the C as E, where the mean quantum number is low W, both kinds of states lead to the same results for most purposes. However, as we shall see, for states with high quantum numbers there may be significant differences between the two types of state. Let us begin with the treatment of the Fock state. A typical wave function for the excitation of a normal mode QK with a definite K vector is 1159. The probability function is 1160. What this means is that the actual field in the excited state will in general not look very different from that of The ground state. As a function of Z, we will have pk equals jj cent I, z, cent I, z, expik, z, z, dv dv slash llloi. 2. 1161. The factor slash 111 0 slash 2 will still represent a generally chaotic variation. HOW. Eve R, the integral in front implies a tendency for waves with vector k2. 248. The undivided uni verse be emphasized relative to the original chaotic distribution. From the AC twel value of the field, one could therefore not say for certain whether the state is excited or not, because the same field configuration could exist in either state. Indeed, the degree of excitation is determined only with the aid of the superquantum potential, which involves the state of the whole. As discussed in Chapter 4 in the treatment of the many-body system, a wave functional having only a single normal mode excited is an extreme abstraction. A more realistic representation of the state would in Volve something like a wave packet. To represent such a packet we need a range of wave vectors, /1. In this case the wave packet will take the form 1.62. In the above equation, the sum is over all k and we do not make the restriction that f_k equals fk. Because the wave fluential is, in general, complex. Even though /z is real. Indeed, considering that q_k equals qk, we can also write 111 equals L1 fkqk plus f_d 1110 k 1163, where the lk indicates summation over a suitable half of the total set of values of k as discussed before. For the applications made in this chapter, we may assume that f0 equals 0, i.e. the space average of the field is 0. To obtain the time dependence of 111, we note that the state qk 1110 and qk will both have the same energy k, so that they oscillate as exp, ict. In this case the wave fluential becomes 111, t, equals elftka ikt plus f_k qke ik t 1110 k. It is clear from the above that the qk terms correspond to running waves in the direction plus z, while the qk terms correspond to running waves in the z direction. To simplify the discussion, let us form a wave packet running only in the plus z direction. This will be sufficient to illustrate the general meaning of the superquantum potential for these wave packet s. We obtain where 111 t equals j f z t cent z dv1110 f z t equals comma dot l fkexp ik z ict vv k 11.64 1165. The ontological interpretation of boson fields 249. To interpret THIS, it is convenient to write, in accordance with equation 1137, and define and phi I cent z t equals vv la k t cos k z plus b k t sin kz k, with cent equals if c plus cent. We note that if e and cent are orthogonal. Similarly, we split f z into two parts phi and f, with and f equals rv l colon fke xp ict sin k z. We further note that f is orthogonal to ile and phi to cent. Using these orthogonality relations we then obtain 111 t equals j phi z t cent e z plus f z t cent z dv111a 11.66. This wave fluential will be large in absolute magnitude for fields in which if E equals O, CFE and cent equals O, F, where OE and O are real and positive proportionality factors. This follows because the total inte grand is then a non-negative fluential of both inte grands. Fields that are not proportional in this way will tend to produce a smaller integral because of cancellation, and this is especially true for the fields that are orthogonal to those described above. Introducing R, Z, to represent the part of the field that is orthogonal to FC, Z, T, and F, z, t, we can write I slash, z, t, equals O, j e, z, t, plus O, f, z, t, plus f, z, t. 1167. The most probable state will then be one in which OE and O are as large as possible, but let us recall that within the Gaussian Fu-Ncetian, W0 will tend to limit the variation of the overall VLD. 250 The 1R and D for 1D EDUNI verse. It is therefore most likely that the field /J, Z, T, will have the form of a wave PA. It correspond ding to OCFC, Z, T, plus O, F, Z, T. The functions f, z, t, which are orthogonal to fc, z, t, and f, z, t, will then not affect the factor in front of LLO. This means that their variation will be the same as it is in the GRU and D state. Therefore the generally chaotic variation of the field as a whole will be modified by a statistical tendency to vary UND and average, which has the form of a wave PA as described above. We shall now show that inside this wave PA the superquantum potential introduces non-local connections between fields at different points, separated by a finite di stance, unlike what happens in the GRU and D state. To obtain the quantum potential, we must first write down the absolute value of the wave function in the QK representation. Recalling that we are choosing f_k equals 0 in equation 1163, we write. Then writing we have il equals L fkqk exp 11 0 k g equals L fkqk exp ict k r equals /ilo. The quantum potential is 1168. Let us now evaluate the change of quantum potential, L.Q, from the GROUND STATE. This is L1FKFKL KFKQKEXPIKT. L.Q equals L plus C 4 KGG 2 K G 1169. In a wave packet which has only a small range of wave vector s, the factor k on the right-hand side reduces to a fixed number ko, while the remaining factors reduce to unity. This term then gives the extra energy of the whole field above the ground D state, recalling that only one quantum H has been excited. More generally, this term varies with the time in a rather complex way, but it will be sufficient for our purposes to consider only those wave packets in which the spread of k makes a negligible contribution to this term. The ontological interpretation of Boson fields 25.1. What will be of interest to us is the remaining term. When the QK are expressed in terms of p, z, through equation 1154, the quantum potential then reduces to Q equals L FK 4 KJJF Z T P Z dV 11.70. Clearly this term implies a non-local interaction between p, z, at other points for which the integrand is appreciable. Writing Q equals Q plus QO, where Q0 is the quantum potential of the ground state given in equation 1155, we see and write the field equation 11.36 as 1171. Using equation 11.55 and expressing Q in terms of p, z, by Fourier analysis we obtain f, z, t, x, ff, z, t, phi, z, dv 112 plus c 1172. Re-CALL that in the ground state, the field is static because the effect of the quantum potential cancels out \72/J in the field equation. But now in the excited state there is a further term which causes the wave packet to move. As happens with the quantum potential itself, the field equation is non-local as well as non-linear. This non-locality represents instantaneous connection of the field at different points in space. However, it is significant only over the extent of the wave packet. In the usual interpretation, the spread of the wave packet corresponds to a region within which, according to the uncertainty principle, nothing at all can be said as to what is happening. Therefore the causal interpretation attributes non-locality only to those situations in which, in the usual interpretation, no well-defined properties at all can be attributed. It is important to note that a wave functional of the form it equals q1i, xp, ikt ilfo does not correspond to the usual picture of an oscillation. This can be seen from equation 1L72, because the term \72/J is absent. This result follows essentially because, as explained in a previous 252 the undivided universe chapter, stationary wave functions generally correspond to a static situation, in contradiction to our intuitive expectations of a dynamic state of movement. 1.1.6 Coherent states and the classical limit. In the previous section we discussed how Fock states are to be understood in terms of our ontological interpretation, and we found that although our results are consistent, they do not correspond to our ordinary physical intuition as to what to expect under these conditions. In order to obtain wave functions giving results that are closer to such intuitive notions as well as to give a treatment that applies as we approach the classical limit, we may use coherent oscillator wave functions, generally called coherent states in the usual interpretation 1.4. To illustrate what is meant by a coherent oscillator wave function, let us consider a particle with coordinate z-und ergoing harmonic oscillation. The Schrödinger equation is Jn1 at 2 pk 2i equals plus z1 slash ot 2m us 2. Introducing euro equals vmwx, where w equals, we obtain apw a 2i equals plus ep 8t28 euro 2. The GRU-ND state wave function is. One can show by direct differentiation that a solution for Schrödinger's equation is obtained by writing 1.73, where is a complex number which we can write as I equals L, LE, I9. We can rewrite the above as 1 slash JOCEXPT, euro, 1 cos, WT plus 0, 2. EXPIL1 I sin, WT plus 0, euro. EXP, IL, L2 sin, WT plus 0, cos, WT plus 0, plus TL. L. 2. Sin. 2. WT plus 9. 1174. The latter exponential is a factor that can be absorbed into the normal Ising coefficient. This solution, therefore, represents a Gaussian wave packet. The ontological interpretation of boson fields 253, whose center oscillates HA-RMO Ni Cali with amplitude 1 foot 1 inch and initial phase 8. The mean momentum, in these units, at any time, t, is Hi sin, Wt plus 8. Evidently the PA it oscillates as a unit wave functions of THIS kind, which are, of course, not stationary, are what we have called coherent wave functions. They represent the nearest approximation to the classical BE. HA of an oscillator. If AT represents the creation operator for a quant so that ATA equals N is the number operator, then one can show 1 for that. 175. The probability for the n degree ST8 of excitation is. This is a Poisson distribution and the most probable value of n is n equals 1112. The root mean deviation is 8n.jre or 8n/nl/.jre. 4. Large values of 11 feet 1 inch. Although the number of quanta is indefinite, the fraction deviation of this number BER from the mean approaches 0. This BE HA further shows the classical significance of coherent wave functions of HIGH by, because their energy becomes nearly determinate in the sense that the fractional deviation is SMALL, while the absolute magnitude of the indeterminacy in energy becomes large enough so that one quantum more or less makes no significant difference. Therefore, in interactions with other systems, the oscillator with a coherent state of HIGH mean energy behaves nearly like a classically well-defined object. To further show up the classical significance of such wave functions, we evaluate the quantum potential and compare it with the classical potential. The quantum potential, in THSA units, will be Q equals T/1/cos, WT plus 8, 2 plus T, 1.76. But because of the Gaussian probability function, the range of fluctuation of particle position and therefore of the quantum potential, which is essentially proportional to the argument of the Gaussian, will be of the order of 1. In these units, evidently, as the absolute value of BL becomes large, the total energy, which is kinetic plus potential plus quantum potential, will be correspondingly large and therefore much greater than the quantum potential. Since the quantum potential can be neglected, the dynamics will then be essentially that of classical mechanics. 254 The undivided universe. Of course, the coherent state represents classical motion under conditions in which, in the usual interpretation, we would say that x and p are defined as accurately as possible within the limits of the uncertainty principle. However, more general wave functions are clearly possible which approach the classical limit in the sense that the quantum potential can be neglected but which correspond to much greater uncertainty in x and p. It is evident that we can discuss coherent wave functions for the radiation oscillators in a straightforward way. For low degrees of excitation, the coherent wave function of an oscillator given by equation 1.75 can be approximated as 1.77. This represents a time-dependent linear combination of the ground ST8 and the first excited state. For most purposes, such as calculating probability of transitions, the results obtained from such a state are essentially the same as those obtained from the corresponding Fock state, which is not time-dependent and in which the number of quanta is well defined. The only difference is that the mean field will oscillate harmonically in the coherent ST8 while it does not do so in the Fock ST8. The most interesting case to consider is that of a wave packet in which the mean value of cent I actually moves with the form of this packet even as we approach the limit of high quantum numbers. To obtain this we go back to equation 1.73, writing for the wave function of an oscillator E t/jcj exp 2 plus 1 e w t. It will be convenient here to return to expressing the field cent I in terms of A1 and B1, the real and imaginary parts of chi. This field is EFI z t equals A1 t, cos, kz, plus b1, t, sin, kz. We want a packet in this field whose average behavior is given by a1 equals hi cos w1t plus 61, and b1 equals js1 I cos w1t plus f1. The appropriate overall wave packet will have to be made up of a product of states a2 plus b 2 2 o exp k l 2 exp h exp I 61 plus w1t a1 x exp s1 exp I f1 plus w1t b1 1178. The ONTOL ICL interpretation of boson fields 255. For large RK and SK, this will represent a very nearly well-defined state of movement as a wave packet, corresponding, for example, to the oscillations of an electromagnetic field in a resonant cavity Y. In this state, the average field will have a packet form, and there will be random oscillation deviations from this packet which become negligible when the mean amplitude E is great enough. This means that, as pointed out in the introduction, the particle-like properties fade away and we are left with the field beables as an essentially complete description of the system. Essentially because the superquantum potential produces negligible effects. 117. The concept of a photon. Thus far in discussing wave packets we have not encountered any of the discrete quantized properties of the electromagnetic field. We shall now show how these come in by discussing the process of absorption of energy from the field by an atom which goes from the ground state to an ionized state. IFTHE field ISINA an excited state with a single quantum of energy, then it will interact with the atom. During this interaction, a very complex wave functional of the field together with the atom will develop. The resulting superquantum potential can change dramatically to bring in bifurcation points. When the process is complete, the whole system of field plus particle will then either remain in the initial state or will enter into a new state in which a quantum of energy h has gone into the atom, while the field is left in the GRU and D state. As we have already suggested in the introduction, the superquantum potential, being non-local, sweeps up energy in this way from the whole wave packet and brings it to the atom. The discrete quantized manifestations of the field are thus explained in terms of a theory which nevertheless allows the fields to vary more or less continuously over a wide range of values. The treatment is very similar to that of the auger-like effect which we discussed in a previous chapter. We begin WITH the initial wave functional of the field, which for mathematical simplicity we treat as a scalar field. This is given by equation 1162, which represents a packet of Fock states with one quantum of excitation. The initial wave function of the electron in an atom is 0 colonnes, O, where A represents the coordinates of the center of the atom. The combined initial 256 the undivided universe wave functional is. We assume an interaction H Hamiltonian. H1 equals A J cent x 6 x 0 d 3 z equals A cent 0 equals A LQK EXPIK K 1179. What this means is THAT the p-article I interacts locally, i.e. only at the central point of the atom. As H happened in the auger-like effect, the interaction H Hamiltonian will introduce further terms into the overall wave function. The coefficient QK is the sum of a creation operator and an annihilation operator. In this case, only the annihilation operator will be significant and it will produce the ground state of the phi LD. The quantum of energy will then go into the particle at. We assume that this energy is considerably more THAN. Enough to ionize The atom. The final wave function of the electron can be written as Tpj equals ln/n T, where the Tpn, T, represent PAC kets going in various directions. Perturbation theory then enables us to compute Cn as Fu and Cn of the TIME. The final wave function for the WH-hole system is IL equals 111 1/0 0 plus L N T T L/N C T T DTIJIN JO 11.80, wherein T can be calculated using ordinary time-dependent perturbation theory along the lines explained in Chapter 6. The coefficient O N T is proportional to VNO, which is The matrix element between the initial state 1/0 and one of the final states Tpn of the electron. In more detail, this is VNO equals AJ slash LF KEXPI K plus O 1/n dV K 1181 with E equals O. The term LKFKEXPIK plus O H has arisen by taking the matrix element of the field between its initial excited state and final GRU and D state. WHAT equation 11.80 means is that during a small time interval dt, a contribution to the wave function will be produced which will be described by the integra nd. This contribution is multiplied by The ground state of the field. The ontological interpretation of Boson fields 257. The packet functions T/Jn, T, correspond to particles that move in a direction represented by n and are set in motion at t equals t. These packets will all separate so THEY cease to overlap both with each other and with the initial wave function yo. Returning to the ontological interpretation as applied to the electron, we can say as shown in Chapter 6 that the corresponding particle will eventually either enter one of the outgoing packets or it will remain in the initial state still bound to the atom. After it enters one of these channels, it will remain there indefinitely. Moreover, because the packets do not overlap with each other or with the initial wave function L, the quantum potential in each channel will be the same as if the other channels did not exist. In other words, as explained in Chapter 6, all the effects of the collapse of a wave function will be present without any actual collapse having occurred. Furthermore, as also explained in Chapter 6, when the electron goes on to interact with the thermal environment, the probability that these packets could ever come to interfere again will be negligible. The effective wave function of the combined system then reduces to 1.82, where n signifies the packet actually occupied by the particle. This represents a situation in which the particle now carries away a discrete quantum of energy, while the field is left in its ground state. As we have indeed already indicated, during the period of transition, the quantum potential will be very complex and will contain many bifurcation points, implying a highly unstable movement of the whole system. According to the initial conditions of the particle and of the total field, the whole system will in some cases enter channels corresponding to a complete transition in which a whole quantum of energy has been absorbed by the particle, while in other CSES no absorption will have taken place. These initial conditions are very complex because they include not only the particle position, but also the initial configuration of the entire set of field variables, which are, as we recall, basically chaotic in their distribution. A very slight change in the initial field configuration could, in many cases, change the result from one outcome to something very different, for example from absorption of a quantum to non-absorption. However, when the probability of transition is worked out using the assumptions that the initial conditions have a distribution of field and particle variables corresponding to P equals IT/Ji, then the usual probability of transition will be pt. This probability is proportional to IV no L2, where V no is the matrix ELE meant given in equation 1181. It will be useful to transform this equation. 258 The undivided universe. By first introducing The function I plus O equals LFKEXP, IC plus 0 K. This is essentially the spot TIAL form of the mean wave PAC ket as determined by the Fourier coefficients Fk, which appeared in The origin AL wave functional of the field 1162. It is clear that the wave functional of the field determines a function k, O, which is the nearest that one can come to what the CLSICAL field would be in the corresponding CLSical situation. We may then expand exp, IC, equals 1 plus IC. Because T/0 is generally AP appreciable only in regions considerably smaller than the typical wavelength I and the PACKET. Then noting that T/Jo, F, and T/Jn, F, O, are orthogonal where 1/n, O, is The value of T/Jn at T equals 0, we obtain V no equals A. J. T/J, Lic, FKEXP IC O T/Jn, O, dV. K. A. J. T/J, T/Jn, 0, dV. \1. I, O. 1183. This means that the matrix element depends on the mean field J, through its gradient. The fact that IT depends on the gradient has come about because we are working with a scalar theory. With a vector theory, IT would not depend on the gradient in this way. However, THIS difference is not of foo and da mental sig ni phi cancebe cos it means only that the probability of transition depends on the gradient of the mean field function, SOTHAT, for example, the maxima will occur at points of steepest gradient rather than at points of greatest intensity of the wave. When the GRU ND state is spherically symmetric, the probability of transition, P, will also be spherically symmetric, so THAT 11.84. We thus complete the demonstration THAT, although the field is entirely continuous, the possibility of transfer of energies is discrete and quantized according to the usual rules. Evidently, similar results will be obtained for emission, excitation, etc. by means of a calculation similar to that leading to equation 1172. It can be shown THAT the energy distributed throughout the wave packet is swept up through UGH the non-local and nonlinear effects of the quantum potential. The fact that the amount of energy transferred is quantity said can be understood by noting that in the long run the effective wave function, the ontological interpretation of Boson fields 259 HS totality, the form of an excited state in which the energy differs by a definite and discrete amount from the ground state. Thus far we have considered an excited field incident on a single atom. What would happen if there were several such atoms in different positions? That could be reached by the wave packet? This is essentially the situation considered by Renninger 1, but simplified by taking a plane wave as the limit of a spherical wave of infinite radius. Is it possible then that we would still end up, as experimental fact requires, with a single quantum of energy transferred to only one of these atoms while the others remain unexcited? To treat this problem we would need to introduce not only the wave functional of the field, but also the wave function cent A, x1, 8 colonnes, x2, cent C, x3 of the various particles. If we did this, however, the perturbation theory could still be applied as in the one particle case. The state in which a quantum had been absorbed would contain a linear combination of free states of the various particles. But THs would correspond to having several possible channels of this kind. Our treatment would still go through and the p-article would end up in one of these channels. The channel in which the quantum is absorbed is determined by the precise initial conditions of the particles and of the set of field variables as a whole, recalling that the whole process will, in general, be unstable and chaotic. However, the probability of each outcome will still be the same as in the usual interpretation. Finally, in section 1.1.2, we showed that it is not possible to make an ontological interpretation of the field in which THR would be a well-defined particle trajectory. How then is it possible to understand the observed fact that a one-ray, for example, passing through a gas, not only leaves a trail of ionized particles looking like a track, but also shows an observable development in time which suggests a bullet-like object, i.e. a photon, striking one atom after the other as it moves along? To understand this we must first recall that, as has already been pointed out in the introduction, this bullet-like object is never itself observed. All that can ever be observed are the manifestations of the field in particulate matter, e.g. by ionizing gas atoms, or producing the photoelectric of CT, etc. So it cannot be concluded that experiments have proved the existence of particles of light. The way is therefore open for a different explanation such as that which we are proposing here. This is that basically what is happening is that the electromagnetic field is undergoing inelastic scattering involving definite quanta of field energy in the way we have described earlier. We need not go into detail here, but we shall merely recall that the scattering is brought about, roughly speaking, by the absorption of a quantum of energy which is swept up into the atom and by the re-emission of a quantum of a slightly lower energy moving in a slightly different direction. If the initial energy of the quantum is large compared with that absorbed by the atom, then 260 the undivided univerz. A series of such inelastic SC atoms will determine a distribution of ions resembling a getter track. In order to bring out the time development of THIS track one could, for example, have an initial wave pa that is n compared with the distance nce between the atoms. It would then follow THAT1 scattering process after another would take place, as if there had been a bullet-like p-article responsible for these events. However, even if the wave pa were broad, a similar result would follow. For, as shown in chapter 5, a transition process can take placin time much less than that required for the wave p-acid to pass a given point. When such a process takes place, e.g. The ionization of an atom, THES subsequent behavior follows at a relatively well-defined time in a way THAT is independent of the WIDTH of the wave packet. We conclude that even though our ontological interpretation does not imply any boson particles such as photons, it can still explain all the experimental behavior that H has been attributed to SUCH particles and the USUAL. Interpretation 11.8 Interference Experiment S. 11.8 1. The TREATMENT of INTER NCE. We are now ready to discuss how interference is to be treated in the ontological interpretation of the quantum theory. We shall do this by assuming THAT quanta of the field are detected by atoms that absorb dsc reduNITS of energy in the way described in the previous two sections. We shall that in an interference experiment with two slits, for example, the probability of absorption will be proportional to what would be thought of classically as the field intensity at the point where the atom is located. Of course, THIS probability will vary in just such a way as to explain the observed interference patterns. We shall then go on to discuss the Plagerman-DL experiment, 3 WHICH2 independent L as ER sources are excited in SUCH a way that there is only one quantum of energy in the whole system. A more detailed discussion of this topic can be found in Pol 1.5. If the two lasers can interfere in a certain region of space, this gives rise to a paradox when we try to think of where the photon that is absorbed comes from. In our treatment, this situation presents no serious problem. The energy is distributed throughout the space between the sources, while in the process of absorption, it is swept into the single atom by the action of the non-local, nonlinear quantum potential. The ontological interpretation of boson fields 261. Figure 1.1. L. 2SHT interference. 11.8. 2. The two-slit interfere NCE pattern. Let us now return to a consideration of THE interference in THE two-slit experiment T. To simplify the discussion, we shall assume a resonant cavity with one of its normal modes excited to its first quantum state. Let us suppose T hat two small holes are made in the cavity close to each other, as shown in figure 1.1. 1. We assume that this will make a negligible change to the normal modes inside the cavity. In the classical description, waves will radiate out from the holes 1 and 2, and will interfere in the region A. We will treat this by representing the field inside the cavity by C and the field outside by cent 0. It will be convenient to treat O as THE sum cent I1 and D cent 2 of THE contributions from slits 1 and 2 respectively. The effective normal mode is then equals C plus 1 plus 2 colones. Of course, this is an approximation that will be valid if the holes are small l enough so that the overall wave function will not change appreciably during the course of an experiment. The probability of transition is not determined by alone but depends on Ki and the way given by 184. As we have said earlier, K is the spatial 262 the undivided un at ERSE form of the mean wave packet as determined by the FOUR coefficients F. K. K. O equals LFKEXP EJ. K. As with cent, K can be written as a sum with THREETERMS, K equals Kc plus K1 plus K2 where Kc represents the value of K inside the cavity and K1 and K2 represent the contributions from slits 1 and 2 as propagated from THE cavity. If we place an atom at point A where the contributions of the two slits overlap P, the probability of transition will then be 1/185. This shows the characteristic interference structure. Thus in a statistical ensemble of experiments performed with the same wave function L, the usual fringes will be obtained. As we have indicated in the previous section, the fact that they depend on the gradient of the field is due to the use of a scalar field, W, which would follow also in the usual interpretation. With a vector field, it is readily shown THAT probability is indeed proportional to the field intensity, 1/6, 11/8, 3. The phi EGOR, MANDLX prime NT. Let us now go ONTOTHEPTGRAM experiment 3. We shall treat this in terms of two resonant cavities CI and C2, each with a small hole in it. The beams coming out of the holes will cross at A as shown in figure 1-1. 2. Each cavity will have normal modes denoted respectively by the functions K1 and K2. As in the interference experiment, we divide each of these into a part that is inside and a part that is outside the cavity, K equals K11 plus K01. And K2 equals K1, plus Ko. Suppose that one of these lasers is excited to T.he. First excited Fox state while the other is left in the ground state. It is easy to show THAT a similar result for this experiment would be obtained for coherent states as well. AC according to equation 1:159, the overall wave functional is then where ITO is the vacuum state and where Fic is the Fourier coefficient of K. But if the second laser is excited, then the overall wave function is W2 equals LF2KQK low K 264 the undivided UNIVERSE. However, linear combinations of such wave functionals are possible core sponding to their being in phase or OUT of PHASE. When THEY are in phase, the wave fun CTONAL is 2 plus equals F1K plus F2K Q equal to K WHILETHE out of PHA.SE wave foo NCT ion L is 2 underscore equals LU1K, F2K, QKLLO. K. 1186. 1187. With THSA2 wave foo NCT ionals IT is not possible to attribute THE quantum of energy to either laser. To have two lasers with DE finite PHA.SE relations of this KINDIS, however, essentially the same as considering two wave packets with a DE finite phase relation as discussed in SE session 1-1. 4. It follows from WHAT we SAIDTH air. THAT the energy will be distribute between the two lasers in a way THAT varies statistically. Therefore the usual mode of talking about THIS, NA melee, that the entire quantum of energy is either in one laser or the other, WITH. Equal probability, IS not validity. If we now suppose that an atom is placed at A to absorb a Chu atom. See figure 112. The superquantum potent EL would sweep UP the energy from BOT H lasers to constitute a full Chu atom. However, in a statistical ensemble of experiments of this kind one would obtain the usual interference CE. Pat TERN. In THIS way the ontological interpretation provides a simple means of understanding WHAT, otherwise seems a very paradoxical situation in this experiment. 11.9 The EPR experiment. We now go on to apply our ontological interpretation to THEEPR situation. Because we are working in terms of a scalar field, we see a not DISCUSS the usual example in terms of polarization or spin. Rather, we shall RETURN to Something more like the origin ALEPREXP meant. This example H is thus far been applied only to part TCLES. In THIS case there was a wave fun CT ion 6, Z2, Z1, A, representing a situation in which WHN over part TCLE1 is found. At Z1, particle 2 W'll be found at Z2 equals Z1 plus A. And, of QRSE, W Hanover. The momentum of particle 1 was measured, that of particle 2 would be the opposite. This meant that it was possible to measure either the momentum or the position of particle 2 by making measurements on particle 1 only. In order to transpose this experiment into a field theoretical context, we first replace 6z2, z1, a, by a function s, z2, z1, a, which is sharply the ONT oligicl interperi TAT ion of BO-SON fields 265. Peaked but regular, and can be Fourier analyzed as S equals LKEXPIC, Z2, Z1, A, K. If the width of THE function S is considerably less than A, then CL early the condit ions of the experiment are not significantly altered, but we can avoid THE mathematical difficulties that arise from the 6 function. The experimental situation that we envisage is to have 2 normal modes of the field, each excited with opposite momentum, but in a correlated way and with THE distance between the respective regions of excitation. Of these normal modes approximately equal to A, the detection of the posi T ion of THSA normal modes will be again by means of an atom that absorbs one of the quanta near the position of the atom FO, W if the INITIL wave function of the electron that absorbs the quanta being T/Jo, O, what we have to do is to show what happens to the other normal mode when this process of position detection takes place on the first normal mode. The initial wave functional of the combined system of field and particle will THN be or T/J equals L9KEXPIK, A, QKQ underscore KWOT/Jo, O, K. 188. 1L89. Let us now consider detection OFTHE position OFTHE normal modes IN. More data IL. We see ANC from equation 189 that there WILL be a statistical tendency THAT whenever the field sent is excited at Z1, there is a corresponding excitation at Z2 equals Z1 plus A, and this is, of course, just the experimental situation we wish to consider, to treat the process of detection of position. We introduce the Hamiltonian for interaction between the field and the atom, which we represent as H1 equals backslash LQKEXPIK. K. This Hamiltonian will lead to THE absorption of a quantum of energy associated with SAY, QK, because the two quanta of energy are oppositely correlated in momenta. This will leave the total field with only a single quantum associated with Q underscore K equals QK, and it will introduce a factor IN to the wave functional EXP, IK, 0. 266 the undivided universe. However, as shown by equation 1180, this term will also bring about a transition of the particle wave function from T/Jo, O, to a phi NAL wave function which includes terms such as T/Jn, T. Each T/Jn determines a separate channel, and eventually the electron enters one of THEM, T/Jn, after which the other channels may be dropped from consideration. The final wave function of field plus PA radical will then be 1, J equals L9KEXPIK plus A, Q underscore KWOT slash JN1, T. K. Re CALLQ underscore K equals QK when sent ISREAL. We are left with 1190. 1191. This result is the same as the one we would obtain using the usual quantum theory, which effectively contains the assumption of the collapse of the wave function to THE phi NAL state. However, in the ontological interpretation, there has been no collapse, but an equivalent result H as BEN brought about by the action of the superquantum potential. The field now fluctuates in a region near Z equals plus A. The absorption of The quantum of energy by the atom it has therefore given a more definite NITESHAPEN form to the remain ing field at Z equals plus A. This is, of course, a nonlinear and non-local effect of the superquantum potential. To complete The discussion of THEEPR situation, WE now need ANX. PE remnant in which the momentum is determined rather TH and THE position. One way of measuring momentum of a quantum is through THE Compton effect. For example, if the frequency of the quantum in one of the normal modes is 11, we can measure THIS frequency by scattering the quantum from a very weakly bound electron. The quantum will be absorbed and a new quantum will be emitted with frequency 11.1 and with an angle, relative to the original wave vector. The electron absorbs the energy difference 11 to 11.1 and scatters at an angle sent with momentum p. Using conservation of energy and momentum, We obtain by means of a K noun C calculation. P, L, P2/4M2. 2 equals 2 COS cent, P/M. 1192. By measuring P and cent for the recoil electron, we can therefore find the value of 11. And according to the reasoning behind THEEPR effect, we expect the second normal mode to have the same frequency but the opposite momentum. To make clear how this comes about, let us represent the initial. The ontological interpretation of boson fields 267. State of the electron by T/Jo, euro, 0 euros. This will be very POORLY localized so that the range of momenta will be small. The limiting accuracy of the measurement will be determined by this range of momenta. To treat this problem in detail would involve time-dependent perturbation theory for the scattering process, which includes the absorption of the original quantum and emission of the new quantum in another direction. However, for our purposes here we do not have to go into all the details. It is sufficient to take into account the fact that the initial wave function of the electron T/Jo, euro, 0 euros, goes into a linear combination of packet functions, T/Jn, euro, t, representing the recoil electron. Each of these packets will constitute a channel and The electron will enter one of them so that thereafter the other channel can be neglected. We can out from a more detailed mathematical treatment that these packets are very nearly plane waves with a range of wave numbers k corresponding roughly to The range in T/0, euro, 0 euros. Let us denote The creation operator initially associated with the phi rst normal mode, by qk, while the corresponding scattered quantum will be associated with q k, which has a different direction from qk as well as a different energy. If the recoil electron determines that the quantum origin NALLY and the phi rst normal mode had frequency 11, and therefore momentum k equals 11, it follows that the final wave function will be effectively reduced to 11.93. THIS result shows that after THE Compton effect has taken place, NOT only does the scattered quantum go into a definite state associated with Q, K. But also that the quantum in the second normal mode goes into a definite state associated with QV. In other words, the measurement of the properties of the recoil electron determines that the second normal mode transforms into a wave like form correlated to the results of TH's measurement, even though, according to the usual interpretation, there is no connection between the first normal mode and the second. But, of course, in our interpretation this is brought about by the superquantum potential, and thus the explanation is basically similar to that given for THEEPR situation with particles. 1110. Appendix, the destruction of interference by radiation. In Chapter 8, Section 3, we explained how radiation falling on a large object, such as a planet in space, can eliminate the possibility of interference between contributions of different parts of its wave front. In Section 4 of Chapter 8 we actually proved that this would happen when a distribution of particles falls on such an object, but we deferred the proof that this will happen for radiation until now. 268 The 1 undivided undivrse. The situation we are discussing is shown in Figure 8. 2. Chapter 8, in WHH radiation is assumed to be falling on the planet. We consider two possible positions of the planet, A and B, and the shadows SA and SAD1, which would be cast from the respective positions. In Section 4 of Chapter 8 we saw that particles would cast semi-LAR shadows, and we proved that if there is a large enough number of such particles, the overlap between the total wave function for the planet at A and for the planet at B will become negligible, so that interference in a region 0, see Figure 8.1, will be destroyed. A very similar treatment can be given for radiation. Let us suppose there is a beam of radiation incident in the z direction constituted of quanta having some range of k vectors. A Fock wave function for a single quantum of definite wave vector k can be written as 1194, where O is the ground state wave function for all the quanta as GIVN in equation 11.49. 111 0 equals 2 exp kqzq1j. K. 1195. We are assuming that the planet completely absorbs the quantum if it falls on it, otherwise we suppose that nothing happens. We now write qk equals j dx x pic x cent z, where cent I, z, is the field at z. The contribution to the net wave function when the planet is at AC and be written as 1 equals j dzexp ik x cent I, z, sa, t1, z, plus 1, sa, y, z, to ch, y. Where sa is 0 in the shadow of the planet and is unity otherwise, while a, tl, is the planetary wave function for the region A. The above expresses the fact that the excited state of the field wave function will only occur outside the shadow of the planet, while in the shadow we have only the ground state. The corresponding contribution when the planet is at B is it 2 equals j dzexp ik dot r cent I, z, sb, t1, z, plus 1, sb, y, z, to b, tl. We must NOW estimate the overlap between 111.1 and 111.2. When we treated the case of particle bombardment in Chapter 8, Section 4, TH's was THE ontological interpretation of boson fields 269. Simple as there was no overlap of the trajectories corresponding to the two hilley and dr shadows SA 1 and SE 1. With fields the situate ion is a bit more complicated because what we have to consider is not an overlap of positions, but rather of field variables between the excited state wave function and the GRU and D state wave function. Because the Gaussian ground state H has a finite spread of field variables, there is some overlap between this wave function and the first excited state wave function corresponding to the single quantum. Nevertheless, this is evidently less than the overlap of the first excited state with itself. So there will be some decrease of overlap and will give rise to a fraction f of overlap which will be less that given by f in chapter 8, section 4 for the case of particles. So we may write 3 f equals ff equals O, L3, where f may be estimated to be of the order of 1/2. From here on the proof can be carried through as in chapter 8, section 4. Therefore when we consider n quanta, we will find that the overlap is decreased by a factor expnf equals expnRn3/OL3. We conclude that when there are sufficient quanta falling on the planet, the interference between planetary wave functions coming from different parts of the wave front can be neglected. Chapter 1-2. O and the relativistic invariance of our ontological interpretation. 1-2. 1. Introduction. In this chapter we shall examine the question of how far Lorentz invariance of our ontological interpretation can be maintained. We shall see that it is indeed possible to provide a Lorentz invariant interpretation of the one-body Dirac equation. For the many-body system, we find that it is still possible to obtain a Lorentz invariant description of the manifest world of ordinary Large scale experience which we introduced in chapter 7. In addition, we show that all statistical predictions of the quantum theory are Lorentz invariant in our interpretation. This means that our approach is consistent with Lorentz invariance in all experiments that are thus far possible. When this question is pursued further, however, it is found that we can not maintain a Lorentz invariant interpretation of the quantum non-local connection of distant systems. This is, of course, not surprising. Indeed, we show that there has to be a unique frame in which these non-local connect ions are instantaneous. A similar result is also shown to hold for field theories. These likewise give Lorentz invariant results in the manifest world of ordinary experience and for the statistical predictions of the quantum theory. But where individual quantum processes are concerned, our ontological interpretation requires a unique frame of the kind we have described, both for field theories and particle theories. We discuss the meaning of this preferred frame and show that the idea is not only perfectly consistent, but also fits in with an important tradition regarding the way in which new levels of reality, e.g. atoms, are introduced in physics to explain older levels, e.g. continuous matter, on a qualitatively new basis. 272 The undivided UNL11 ERZ 1-2. 2. The one-particle Dirac equation. We shall begin with the one-particle Dirac equation and show that it is possible with this equation to obtain an ontological interpretation that is invariant in content to a Lorentz-Strauss formation. We have already given the essence of this interpretation in chapter 10. To recapitulate briefly, it follows from the Dirac equation that there is a conserved current density whose time component is positive definite, this is with. We define the velocity as. We start with the identity. This reduces to oj. Tj, tt/2 underscore L IPTAKTJ equals TJ L/3 IP 2 plus IPT 213.R5 IP 2 K 12 L 12.2 123 12.5. The left-hand side of this equation is just P2 L I, and it is evident that the right-hand side is positive definite, so that 6.1. If we denote the density P equals J 0, we obtain for the conservation equation up plus V PV equals 0 at 126. Therefore the velocity 12.3 may be taken as determining the guidance relation for a p-article. If we assume a probability density P equals P for any time, then equation 126 guarantees that it will hold for all time. As we explained in chapter 10, it is not necessary to have a simple relationship for the acceleration analogous to the one in the non-relativistic theory, which expresses the latter as the sum of two terms, one corresponding to the classical potential and the other to the quantum potential. Even on the relativistic invariance of our ontolog 1 cal interpretation 273. Without such a relationship, the path of the p-article is completely determined by equation 123, and the whole theory will eventually go through by an extension of the approach given in chapter 10. It is evident that this theory is Lorentz invariant in content because the Dirac equation is covariant, and because from this it follows that the relationship 126 is also covariant. It is important, however, to ask what would happen if we assumed, as was done in chapter 9, that the probability density P was not initially equal to P. Could covariance still be maintained under these conditions? To discuss this question, we first note that in chapter 9 we have given two ways in which the probability distribution might approach P. Firstly, we might have a complex system consisting of many particles in interaction, e.g., electrons in a metal. We showed that in such a case, the probability P would eventually approach P. To be sure, the situation that brings about this approach is not covariant. For example, the electrons in the metal will determine a process that is uniquely related to the center of mass frame of the metal, yet once the distribution P equals P has been brought about the result will be covariant and will remain so. Thus electrons boiling out of the metal and accelerated to high velocities will still have a covariant distribution with P equals P because this distribution was established before they boiled out. The second way of bringing about the distribution P equals P is to assume an underlying stochastic process. No one has yet found a way to give a coherent description of a covariant stochastic process, although attempts have been made, Lair and D. Park 1, Fenwick and Vigier 2. The principal difficulty is that the probability of a given velocity would have to be uniform on a time-like hyperbola. This would mean not only that almost all the particles will be going very close to the speed of light, but also that there is no way to normalize the probability distribution, essentially because the Lorentz group is not compact. There is no need, however, to have such a Lorentz invariant stochastic process. Indeed, as long as we have a stochastic process that leads to P equals P in any particular frame, this will be enough. For it follows that from then on we will have a theory that will have a Lorentz invariant content. Thus, for example, we could introduce equations for osmotic and diffusion velocity. Along the lines of equations 9.38 and 9.39, to give plus backslash 7p, v plus d, d backslash 72p equals 0. 1 2, 7. Where v equals cent t. A tf slash 1 cent 12. And the osmotic velocity is evidently d backslash 7 p slash p. This equation would hold only in a certain frame and would evidently imply a 274 the undivided universe non-covariant process of approach to equilibrium. An evert helix along the lines that we have described, it will lead to an equilibrium distribution. That is Lorentz invariant T. This would be enough to bring about a covariant ontological interpretation of the 1-part-Tle-Dirac equation. The osmotic velocity u0 equals d, vp slash p, may be infinite where p approaches 0, and this would imply speeds greater than that of light. We shall however discuss this point in section 1-2-6 where we show that it leads to no inconsistency ies. 1-2-3 The ontological interpretation of the Dirac equation FORA. Many body SYS TEM. In chapter 10 we have given the main features of the extension of the ontological interpretation for Dirac particles to a many-body system. We begin by summing up what was done. Firstly, we define the wave function for the many-body system to be W equals Wi, in Z1, Zn, I. Note that we are, at least for the moment t, taking all the p-articles at the same time t. We introduce the operators, on, which operate only on the 4 indices, in, belonging to the nth particle, similarly for J1n. The Dirac equation for the n-body system is then I degree equals IONVN, IAN, ZN, T, plus, BNM plus, CLN, ZNT, W. 128. Where CLNA represent the electromagnetic potential S. From THISIT is readily shown that 129. Where in THE above we sum over all THE indices OFALL THE particles. Defining the density P, Z1, Zn equals 1111 12 in the configuration space of all the p-articles and the guidance relation for the velocity of the nth particle, tin. Vn equals Wton-Wip. We obtain the conservation equation in configuration space. Op. Oi. Plus. L. V. N. PTLN equals 0. 1210. 1211. If P equals P initially, it follows that this will hold for all TIMI. Along the lines that we have given in previous cases, we can see that the above provides a consistent ontological interpretation of the many-body Dirac equation. This consistency is evident in the particular frame that we have chosen. For the represented tion of the beables of the system, which are xn and tin. On the relativistic invariance of OUR ontological interpretation 275. The question then arises, however, as to whether this interpretation H has a covariant content, i.e. one that has THE same meaning in every Lorentz frame. THUS, for example, the many-body Dirac equation, 128, considers all the particles at THE same time, and it is not immediately evident that one could make a Lorentz transformation in which all the particles would be considered at the same value of the transform time t equals t, vx, slash. Nor is it evident that the Vn defined in equation 1-10 would be obtainable from some 4 vector v. And finally 1can ask what is to be done with the negative energy states. Let us first consider the meaning of the negative energy states. This is usually treated in terms of fermionic creation and annihilation operators, satisfying anti-commutating relations, which, of course, describe p-radicals that satisfy the exclusion principle. The most obvious anti-commutating relations for the operators il t x and il x would be 111 t x LLL x L plus equals O x x. If we Fourier analyze il as y ikz xz equals L ak plus e plus ak underscore e, this leads to the anti-commutation relations al ak plus L al ak underscore L al ak underscore L plus 0 1212 1213 1214, while all the ak and the al anti-commute among themselves. The state OFNO particles would be E1 containing neither particles with positive nor negative energy. Therefore it would be possible in general for interactions to produce particles with negative as well as positive energies. To avoid this, standard treatments in field theory effectively interchange annihilation and creation operators. That is to say THEY right and